was correct, you know. It's possible that individual galaxies are also held together by the mysterious substance that Zwicky dubbed dark matter. Galaxies rely on dark matter as a kind of protective framework that keeps them from collapsing and moving about. Now, scientists have discovered that dark matter does more than just bind galaxies together. It may have also triggered their evolution. Scientists believe that after the Big Bang, dark matter started to cluster, and these dark matter clumps evolved into the galaxy's nucleus. However, the nature of dark matter is still a mystery to physicists. Weird things happen with dark matter since we don't know what it is. Obviously, it's not constructed from the same substance that humans are. You can't push against it. You can't feel it. However, it is likely everywhere. It's a ghost-like material that will pass right through you as if you didn't exist at all. Although our understanding of dark matter is limited, it seems to be abundant across the cosmos. That means there must be at least 6 times as much dark matter as regular matter, what humans are comprised of in the cosmos. And the way the cosmos seems to function depends on it. Observations of its effects on light have led to its recent indirect detection in deep space. Through a process known as gravitational lensing, it warps the light. The existence of dark matter may be tested using gravitational lensing. As a ray of light from a distant galaxy travels towards us, its course will be bent around a huge collection of dark matter due to the latter's greater gravitational attraction. Some distant galaxies indeed seem stretched and warped when seen via the Hubble telescope. The picture distortion is due to the presence of dark matter. We can determine the density of dark matter by carefully examining the forms and degrees of distortion of these galaxies. Now more than ever, the importance of dark matter to the cosmos is undeniable. It's what makes galaxies form and stops them from collapsing. Even though it's invisible and undetectable, dark matter rules the cosmos. These galaxies seem to be completely alone. It's true, they are trillions of miles apart. But actually, they live in groups called clusters. And these clusters of galaxies are linked together in superclusters, containing tens of thousands of galaxies. The Milky Way's place in the cosmos remains a mystery. If you look at the overall image, you'll see that our galaxy is associated with a smaller group of galaxies, including about 30 members in total, and that our galaxy and Andromeda are the 2 largest members of this group. Further observation reveals, however, that our galaxy is embedded inside the Virgo supercluster. Researchers are now making maps of galaxy clusters and superclusters to better understand the cosmos. Galaxies are the immense star empires. The shapes range from enormous balls to intricate spirals. The problem is that they are always evolving. When we stare out into the cosmos, it's easy to assume that our galaxy hasn't changed in eons. It's not. The Milky Way is a dynamic galaxy. Over cosmic eons, its basic nature has been changing. Galaxies don't only evolve, they move as well. And sometimes they run into each other. The 2 galaxies will merge over millions of years when they collide. This kind of collision occurs all the time in the cosmos. Our own Milky Way is no exception. We are on a collision course with the galaxy Andromeda, and that's terrible news for the Milky Way. At a speed of around 250,000 miles per hour, our Milky Way galaxy will collide with Andromeda in about 5 billion to 6 billion years. It's all over for the Milky Way galaxy. If you could look out into space, you'd see the whole Andromeda galaxy hurtling toward us, at a tremendous rate of speed. As the two galaxies interact, they both become more and more disturbed and closer together. There will be a dance of death between the two galaxies. Whenever galaxies collide, they release clouds of gas and dust in all directions. As galaxies collide, their combined gravity rips stars from their orbits and launches them into the void. As we approach doomsday for the Milky Way galaxy, it would be spectacular. The two galaxies will ultimately pass through one another and merge into a single one. The Milky Way and Andromeda as we know it will cease to exist, and Milkomeda will be born, and it will look like a whole new galaxy. There's no escaping what's going to happen. The question is, what's it mean for planet Earth? We may either be thrown out into outer space when the arms of the Milky Way galaxy are ripped apart, or we could wind up in the stomach of this new galaxy. Stars and planets will be pushed all over the place, so this may well be the end of planet Earth. Galaxies all over the universe will continue to collide. But this age of galactic cannibalism will eventually pass, because there is an even more destructive force in the universe, a force that nothing can stop. It will eventually tear the cosmos apart by stretching everything to the point that galaxies are pushed apart from one another. Researchers have identified a new cosmic power. It's called dark energy. Unlike dark matter, dark energy has the opposite effect. It pushes galaxies apart rather than bringing them together. Dark energy, which we've only discovered in the last decade and which dominates the universe, is significantly more enigmatic. We don't have the slightest idea why it's there. What it's made from, we don't really know. We are aware of its presence, but beyond that, our understanding of it is limited. Dark energy is really weird. Things resist and are pushed away from one another as if space itself contained tiny springs. In the far future, scientists predict that dark energy will triumph over dark matter in the cosmos. And with that triumph, galaxies will finally begin to drift apart. Galaxies will eventually die off due to dark energy. It will do this by accelerating the expansion of the universe, forcing all galaxies to recede farther and further away from us until they become invisible and travel faster than the speed of light. Therefore, everything else in the cosmos will vanish before our own eyes. The remainder of the cosmos won't vanish today or tomorrow, but it may after 1 trillion years. Galaxies will be left alone in the void. However, this will not occur for an extremely lengthy period. The cosmos is doing well right now, and galaxies are creating favorable circumstances for life to exist. Without galaxies, I wouldn't be here, you wouldn't be here. Maybe not even life itself would exist. This is fortunate for us. The only reason why life has evolved on Earth is because our minuscule solar system was formed in the correct region of the galaxy. If we were any closer to the center, we wouldn't be here. Life in the center of a galaxy may be extremely hazardous. In point of fact, the proximity of our solar system to the core of our galaxy would render it so radioactive that it would be impossible for life to continue in any form. Too far away from the center would be just as bad. Out there aren't as many stars. We might not exist at all. We are therefore, in a sense, in the Goldilocks zone of the galaxy, neither too close nor too far away, but just right. There may be millions of stars in the cosmic Goldilocks zone, where conditions are just suitable for life. Furthermore, if our galaxy can support life, then other galaxies should be able to as well. The cosmos is very large, and the really incredible part is that we continue to learn new things about it. Every time we believe we've figured out a solution to an issue, we uncover that it's really part of an even greater one. That's awesome. Our Milky Way galaxy and the galaxies beyond it are rife with mysteries and unanswered questions. Who would have guessed 20 years ago that we would be able to identify the black hole at the center of the galaxy? Who would have predicted 20 years ago that the astronomical community would accept the existence of dark matter and dark energy? We should be astonished to be alive at this particular moment in cosmic history, on this particular planet, on the fringes of this particular galaxy, with the ability to ponder questions and seek answers across the whole cosmos. Galaxies are born, they evolve, they collide, and they die. The Milky Way is a fortunate home for intelligent life. Our fate is intertwined with that of every galaxy. Ultimately, our fate rests in their hands since they are the ones who created us and are shaping our identities. We used to only know about the planets that circled around our sun. But now we know that there are rocky worlds and huge gas clouds that circle other stars. They have a great story to tell. The early history of these planets would have been very, very violent. Planets are made the same way everywhere. They come from the dust and other things that are left over after stars are born. So, if they're all made the same way, what makes them so different? As it turns out, the universe is full of galaxies, gas clouds, stars, and planets. There are 8 worlds in our sun system. But now we know that they are just a small part of the huge family of planets in the sky. It's a very important moment in the history of science to be sure that there are other systems of planets out there. And in our Milky Way galaxy, which has 200 billion stars, there are probably dozens of planets. NASA sent the Kepler Space Telescope out into space in 2009 on a 6-year mission to find new planets that orbit other stars. So far, they have found more than 400. Some are huge, spinning balls of gas that are 5 times as big as Jupiter. Others are huge, rocky worlds, many times larger than Earth. Some follow wild, erratic orbits, so close to a star they're burning up. One thing is clear. No 2 planets are the same. Each one is unique. But most of these new worlds are very far away and hard to study. Most of what we know about how planets work comes from the 8 that circle our sun. Our own planets come in 2 main types. There are 4 rocky planets in the inner solar system: Mercury, Venus, Earth, and Mars. And in the outer solar system, there are 4 giant gas planets: Jupiter, Saturn, Uranus, and Neptune. Each of the 8 worlds is very different from the other 7. When our solar system was born 4.6 billion years ago, they started to develop their own personalities. When the sun ignited, it released a massive cloud of gas and dust into space. All 8 planets, including the metal planets closer to the sun and the gas planets farther away, came from this cloud of space debris. All of the worlds in our solar system are made of the same materials. They're made from the same cloud of gas and dust, but they formed under very different conditions. Some of them formed close to the sun, where it was much hotter, and some formed far away, where it was much colder. And since the situations were so different, the things that came out of them were also different. So, at the beginning of the solar system, there was a pretty even mix of silicates, water vapor, hydrogen, a lot of hydrogen, methane, and other things. These elements in the dust cloud are like ingredients in a cake. They cook in different ways based on how the ingredients are mixed and how hot the oven is. And you'd mix the ingredients just like you did with the cake. Then you'd put it in the oven and bake it, and it would change. So basically, this is what happened in the solar system. Overall, the planet cooks in a slightly different way, depending on how close it is to the sun. Near the sun, where it is hot, gases are burned off and water boiled away. Only materials that stay solid at high temperatures, like metals and rocks, can survive. This is why only rocky planets form close to the sun. As a planet moves farther away from the sun, it cooks in a different way. But what kind of planets will form depends on what's in the cloud. Based on what kind of cloud a solar system forms in, it might not have any rocky planets because it didn't have enough materials to make something like Earth. Instead, it might have more gas giants and none at all. If you want planets that are made of rock, you need a cloud full of metals and rocks. The next step is to turn down the heat. As it cools, some of the things in it that have a high boiling point start to condense out as solids. And these very small mineral grains can start to form. These tiny pieces of rock and minerals are the beginnings of a new rocky world. They start to stick together over time. If you had one dust molecule and another dust molecule, and they would basically hit each other and make one slightly bigger dust molecule, and they'd keep getting more and more. This process is called accretion. As these things got bigger, they became basically rocks. Then rocks slam into other rocks and form boulders. Boulders smash together to form bigger boulders. At some point, you'll have something big enough that its weight is strong enough to start pulling things towards it. So instead of just crashing into things and getting bigger that way, it was actively pulling things in. At first, there were a lot of young planets in our own solar system, maybe 100. Most of them didn't make it. If you go to the asteroid belt and look at the asteroid 4 Vesta, you can get a good idea of how big a hard planet has to be before it can pull itself into a sphere shape. Vesta is only 329 miles across, which isn't quite big enough to be a sphere. To become round, a growing planet needs to be 500 miles across. Then, it has enough gravity to crush it into a sphere. Any smaller, and it stays in irregular shape. Every time a round baby planet crashes into something, it makes it hotter and hotter until it starts to melt. Gravity is now starting to sort the heavy things from the lighter ones. Lighter things tend to float up and form a crusty layer, while heavy things, like most metals, fall down and form a much denser core at the planet's center. Finally, the young planets are starting to look like planets. But now, they have to make it through a time of violence and destruction, a cruel time that will decide which planets will live and which will die. After the sun was made, all 8 of our planets came from the same cloud of dust and gas, but they turned out to be very different. There was no real plan for how each of the new planets should be made. They did follow the rules of physics and chemistry, but most of what happened was just a matter of luck. About 4.5 billion years ago, our sun was surrounded by about 100 young planets. It turned into a demolition derby. Planet hit planet. Most were wiped out. The early history of these planets would have been very, very violent, with many of these collisions happening in the last stages of each planet's growth. As these collisions happened and things ran into each other, some of the planetesimals started to grow at the expense of the others. And these things that would eventually become planets grew and grew. As they got bigger, they sucked up all the smaller planetesimals around them, which caused a lot of space debris to hit the surface of the protoplanet. After it was over, there were only 4 different rocky planets left. Because of the things that happened to each planet in the past, they are all so different from each other. Mars is a frozen wasteland. Earth flows with liquid water. Venus is a place full of volcanoes. And Mercury is small, empty, and very hot because of a huge crash. Mercury, for example, has a very thin crust and is very dense. So it could have been a bigger planet in the past. Then something hit it at an angle, which tore off the lighter crust and left only the dense center. Also hit hard was the young Earth. At the end of the Earth's development, it was hit by something else, which tore apart its mantle and sent the pieces into orbit around the Earth, where they regathered to form the Moon. Something also seems to have crashed into Mars. The crust of the Earth is thinner in the north than in the south. One idea about what might have caused this is that the northern hemisphere of Mars was hit by something early in the planet's history, which blew off a lot of its crust, and that crust started to build up again in the south of Mars. There were two effects of all these collisions. They cut down on the number of baby planets that were still alive, and they brought more ingredients to the survivors. If you had a collision with something that was metal, rich, those chunks would tend to descend down into what was becoming the core, where if you collided with something light or icy, they would tend to just float about and form part of the crust instead. Near the Sun, there were 4 rocky planets that were almost done. They were made of a solid core of hot iron surrounded by a layer of liquid iron and a shell of molten rock. On top of that is a crust on the surface. All of these rocky planets were made the same way from the same basic materials. But each of them was very different. Different sizes and very different destinies. Space may look empty, but it's not. It's full of stuff blown out of the sun. Strong magnetic fields are made by the sun. These fields rise up in giant loops above the surface. When they hit each other, a storm of very hot, very charged particles shoots out into space. The name for it is the solar wind. Astronauts can see it from space, but only when they close their eyes. When you close your eyes, you sometimes see a little flash. And that flash of light is caused by an energetic particle going through your head and interacting with the fluid in your eye, and you see one of these every few minutes. Solar wind could kill the astronauts if they were exposed to a lot more of it. During the Apollo program, there was an explosion on the sun between 2 moon missions that would have killed the astronauts if they were there. So, radiation in space is a big deal. But here on Earth, the solar wind doesn't pose much of a threat because we are protected by an invisible magnetic field that comes from the center of the Earth. You can make magnetic fields from motion by converting the energy of the motion into magnetic energy. Deep inside the Earth, the same thing happens. As the Earth spins, the hot liquid metal flows around the solid core, turning its energy into a magnetic field that comes out of the poles. It keeps the solar wind from getting into the atmosphere of the planet. And if the planet has a magnetic field, the magnetic field will send the solar wind around the planet. The solar wind is pushed away from Earth by the magnetic field, which protects the atmosphere and everything on the surface. Big storms of solar radiation can sometimes mix up the magnetic field. Then, big light shows called auroras happen over the poles. Without a magnetic force field, Earth's atmosphere and water would be blown away by the solar wind, leaving a planet that is dead and dry, a lot like Mars. Mars was made the same way Earth was, but today it's cold and dry and there's not much going on. So why have the 2 planets changed so much? NASA sent 2 robots to Mars in 2004 to find out what was there. The Spirit and Opportunity rovers looked at miles of the surface of Mars. They proved that Mars is a dry, dangerous desert with only the atmosphere of Earth. But they did find signs that water used to be there. Mars wasn't always a dry, barren place. We have found strong evidence that water was once below the surface, rose to the surface, and evaporated away. In a few places, we can also see ripples that are made when water flows over sand. So, not only was there water under the ground, it had flowed across the surface. If Mars used to have water, it probably also had a lot of atmosphere around it. So what happened? We can see that there were volcanoes on Mars in the past, so it had a hot interior at some point. And because it was made of the same stuff as Earth, it would have had a hot iron core surrounded by liquid metal in the middle. It should have also had a magnetic field. The question is, where did it go? Early in the planet's history, Mars apparently had a strong magnetic field. And it was probably caused in the same way as it is on Earth. But Mars is a smaller planet than Earth. Because of this, it will lose heat more quickly. And that means that a liquid core can become solid when it freezes. If you completely freeze the core, the convection will stop. The flow stops, and the magnetic field disappears. As soon as the magnetic shield stopped working, the solar wind blew away the atmosphere and the water evaporated. Mars turned into a cold, empty place. The rocky planets, Mars, Earth, Venus, and Mercury, all formed within 150 million miles of the Sun. But 4 times farther out, the Sun baked a very different kind of planet. These monsters are very big, made of gas, and have no solid surfaces at all. So far, astronomers have found more than 400 new planets in solar systems far away. Almost every one of them is huge and made of gas. Our solar system has 4 of these so-called gas giants: Jupiter, Saturn, Uranus, Neptune, all of which have thick, soupy atmospheres with lots of hydrogen, helium, and methane. Why are these outer 4 made of gas when the inner ones are rocky? It's very cold here, 500 million miles from the Sun. At the start of the solar system, there was some dust, but mostly gas and water, frozen in ice grains. It was cold enough to make solid snow where the big planets began to form. And we think that we were able to make ice snowflakes, and that these were able to stick together to form the cores of the giant planets. We think that's why the big planets might have grown so big. Because there was so much ice and gas, their cores grew to be about 10 times the size of Earth. A lot of gravity came from these big cores. They had so much pull that they sucked in all the gas around them and made thick, soupy atmospheres that went down tens of thousands of miles. The more gravity they made, the bigger they got. More and more dust and debris kept getting pulled towards the planets, and this is what made up their moons. Each of Jupiter and Saturn has more than 60 moons. The gas planets have something else that makes them unique: rings. Saturn is different from the other planets because it has these beautiful rings. It turns out that Jupiter, Uranus, and Neptune also have rings, but they are very weak and hard to find. But they are there. There are rings around all 4 of the gas giants, but Saturn's are the most obvious. From far away, Saturn's rings look like a single flat disk, but in reality, they are made up of thousands of small rings that are only a few miles wide each. When the Cassini probe flew by, it found that billions of pieces of ice and space debris were moving around inside the rings at up to 50,000 miles per hour. These pieces of ice and rock hit each other all the time. Some of them turn into small moons. Some of them fall apart. But they never grow bigger because Saturn's huge gravity pulls them apart. Scientists are just now starting to figure out how the rings came to be. The idea is that a comet hit a moon and knocked it out of its orbit, bringing it closer to the planet. Saturn's gravity tore it to pieces. all of that stuff got stuck in rings that went around the planet. But the real mysteries of the gas giants are deep inside them, tens of thousands of miles below the clouds. Here is where things really get going. It's a place so extreme that it goes against the natural laws. Most of the new planets we find orbiting faraway stars are huge gas planets. They are so big that Jupiter seems small next to them. But nobody knows what happens inside gas giant planets, whether they are in our solar system or far away. We know that Jupiter's thick atmosphere goes down 40,000 miles, and we can see bands of gas moving at high speeds that make violent storms on its surface. But we don't know what's happening inside, far below the storms. NASA sent the Galileo spacecraft on a 14-year trip to Jupiter to find out. December 7, 1995, Galileo sent a probe into Jupiter's atmosphere, which it did at a speed of 160,000 miles per hour. As it fell through the thick air, the parachute slowed it down. It saw lightning in the clouds and 450-mile-per-hour winds. The probe transmitted data back to Earth for 58 minutes. What happened to the Galileo probe that we dropped in? It didn't hit anything. It just kept falling into Jupiter's environment, and the pressure kept going up and up and up. As it fell, it measured pressures 23 times higher than on Earth and temperatures over 300 degrees higher than on Earth. When you're in the environment of a gas giant and you go deeper and deeper into this soup of hydrogen, which has no solid surface, it can still be very heavy. And so eventually you would be crushed by the overlying weight of the material that's there. Even though the probe only went 124 miles down before it was crushed, it showed scientists what Jupiter's inside looked like. But the dark heart of the planet still remains a mystery. Like some rocky planets, the gas giants have a magnetic field too. Jupiter's magnetic field is 20,000 times stronger than Earth's, and so big that it goes all the way to Saturn, which is more than 400 million miles away. Like on Earth, Jupiter's magnetic field keeps the solar wind away from the atmosphere and keeps it safe. When scientists looked at Jupiter's magnetic field, they found that it affected the moons of Jupiter. The volcanic moon Io orbits only 217,000 miles from the planet. Every second, Io's volcanoes send a ton of gas and dust into space. It gets even stronger because of Jupiter's magnetic field, which makes powerful belts of radiation. And this makes the area around Jupiter very busy in a lot of ways. If you point a radio antenna at Jupiter, you can hear how the planets and the magnetic field interact with each other. Jupiter and Saturn can make auroras without the solar wind. They make their own magnetic fields because they're so big. These auroras show that planets with gas also have magnetic fields. But how do magnetic fields get made on gas planets? On Earth, the job is done by a very hot liquid metal that spins around the planet's solid iron core. Most likely, gas planets do about the same thing. But gas planets don't have iron cores that get very hot. They formed around frozen cores of dust and ice. So we don't really know what's going on inside. We really don't know what makes up the deepest parts of Jupiter's interior. So it's possible that Jupiter has a solid core at its center, or it could just still be liquid. We might never know. No probe could ever go the 44,000 miles to the center of the planet to look into it. Galileo was destroyed before it could reach the center of the planet. Gravity and heat shape how planets evolve from their inner cores to their outer atmospheres. They're the great creative forces in planet building. But there's one more thing that has a big effect on how planets turn out, and that ingredient is water. Planets may look like they are fixed and don't change, but they are always changing. One planet in our solar system lost its atmosphere and turned into a desert. Another planet got too hot and changed into the planet from hell. Planet Earth has also changed, and it was water that changed the game. When you look at Earth from space, you can see a lot of water. We are, after all, the blue planet. That means it must be very wet, right? At first glance, our world seems to have a lot of water. After all, 3/4 of it is made up of oceans. Not true. Only 0.06% of the mass of the Earth is water. Some water is on the surface as oceans, and some is stuck in the mantle. But actually, the Earth is a relatively dry rock. All of the inner rocky planets formed very close to the sun, so they started off dry. Any water they might have had either evaporated or was blown away when things hit. These massive collisions that formed the Earth were so energetic that if there had been water here, it would have evaporated and left the Earth. So where did all the new water on Earth come from? It's now here. When you look at Jupiter, Saturn, Uranus, and Neptune, you can see that they have a lot of water locked up inside them. And even more dramatically are the moons. At least half of the water on the moons of Jupiter, Saturn, Uranus, and Neptune. A lot of water was out there. So how did some of it get to planet Earth? And the answer is almost certainly that there were some asteroids and comets left in our solar system that were far enough from the sun that they could keep their water. There were millions of these watery asteroids and comets that flew into the inner solar system. Some of them crashed into our planet. Over time, the Earth got the water that used to be in the asteroids. This is what makes up the mass of water that now covers almost all of the Earth. Without surface water, there would have been no life. What about water that is too much? The oceans would be much deeper and cover the continents and even Mount Everest. And it's likely that the exact amount of water that the Earth has is what made it possible for us, Homo sapiens, to evolve into a technological species. About 4 billion years ago, a blizzard of comets and asteroids brought just the right amount of water to Earth. This is how the world we know today came to be. And it's possible that the same thing is going on somewhere else in the universe right now. There is a lot of water out there, that much is certain. The most common atom in the universe is hydrogen, and oxygen is one of the next most common. H2O will definitely be a very popular molecule, which is exactly what is happening in our universe. So, water is everywhere in the universe, and we're finding that planets are too. But we haven't yet found another planet where water is liquid. More than 400 new planets have been found by scientists. Our world doesn't look like any of them. What we haven't found yet is a planet around another star that is about the same size, mass, and chemical makeup as Earth. So, it remains an extraordinary holy grail for humanity to find other abodes that remind us of home. But we'll keep looking. We know that our galaxy alone has around 200 billion stars, and up to 40 billion of them could have their own planets. We are entering what will be called the golden age of planetary exploration in the future. We'll start to really understand for the first time how different things are out there. I think this is going to be a very exciting time. The laws of physics and chemistry tell us how planets are made. Many scientists think it's only a matter of time before we find another planet like Earth, one that formed from the same materials in the right place with the right amount of water. One thing is certain: there are billions of planets out there waiting to be discovered. Ladies and gentlemen, welcome to today's topic, aliens. Are they real? Do they exist? And if so, what do they look like? Today we will dive deep into the topic of aliens, exploring various theories and facts about these mysterious creatures. If you are interested in amazing videos about the universe, be sure to subscribe to our channel to stay updated. Here are a few theories about aliens. Extraterrestrial life exists. This is the theory that life exists elsewhere in the universe, perhaps even within our own solar system. Microbial life could potentially exist on Mars, or some of the moons of Jupiter and Saturn, for example. More complex life forms, such as intelligent civilizations, could also exist on planets orbiting other stars. The Fermi paradox. The Fermi paradox suggests that if intelligent life is common in the universe, why haven't we detected any evidence of it? Some theories suggest that intelligent civilizations tend to self-destruct, while others propose that they are too far away or have no desire to communicate with us. Ancient aliens. This theory suggests that aliens have visited Earth in the past and have influenced human history and culture. Proponents of this theory point to ancient artwork and texts as evidence of alien visitation. UFO sightings. Unidentified flying objects are often cited as evidence of alien visitation. While many sightings can be explained by natural phenomena or human-made objects, some remain unexplained and could potentially be evidence of extraterrestrial visitation. The simulation theory. This theory proposes that our entire reality is a computer simulation created by an advanced civilization. While not specifically about aliens, this theory suggests that the creators of the simulation could potentially be an extraterrestrial civilization. To start with, let's address the most basic question: do aliens exist? Well, according to the Drake equation, which was developed in 1961 by astronomer Frank Drake, the probability of intelligent life existing elsewhere in the universe is high. The equation takes into account factors such as the number of stars in our galaxy, the number of planets that could potentially support life, and the probability of life forming on those planets. Using these factors, the Drake equation estimates that there could be millions of intelligent civilizations in our galaxy alone. But the question remains, have we ever encountered these civilizations? Many people believe that we have, and there are countless stories of alien sightings, abductions, and encounters. However, there is little concrete evidence to support these claims. So, let's explore some of the most popular theories about what aliens might look like. The traditional image of aliens as small, green, big-eyed beings is a product of popular culture. However, it is unlikely that aliens would look anything like this. In fact, it is impossible to predict what aliens might look like, as their appearance would depend on the conditions of the planet they evolved on. For example, if an alien species evolved on a planet with high gravity, they might have shorter, stockier bodies. If they evolved on a planet with a harsh, radiation-filled environment, they might have evolved to be more resilient to radiation. It's also possible that some alien species might not even have bodies as we know them. They might exist as pure energy, or as a hive mind collective. But why would aliens visit Earth? There are a few possible reasons. Some scientists speculate that aliens might be interested in our planet because of its unique location in the universe. Earth is in a Goldilocks zone. It's not too hot, not too cold, and has the right conditions for life to thrive. Aliens might be interested in studying our planet to learn more about how life can survive in these conditions. Another reason aliens might visit Earth is to make contact with us. If there are millions of intelligent civilizations in the galaxy, it's possible that some of them are trying to communicate with us. However, if this is the case, they might be communicating in ways that we can't even comprehend. their methods of communication might be vastly different from ours. So, what should we do if we ever do encounter aliens? Many scientists believe that we should approach any encounter with caution. We should avoid making any sudden movements or aggressive actions, as these might be misinterpreted by the aliens. Instead, we should attempt to communicate in a peaceful and non-threatening manner. If we do make contact with aliens, it could have profound implications for our understanding of the universe. It could challenge our beliefs about our place in the cosmos and force us to confront some of the big questions about life, the universe, and everything. Now that we've explored some of the theories and possibilities of alien life, let's consider the idea of the Fermi paradox. This paradox asks the question, if there are so many intelligent civilizations out there, why haven't we seen any evidence of them? Why haven't we detected any signals or observed any spacecraft from other worlds? One possibility is that advanced civilizations tend to self-destruct. With technology comes the potential for destruction, whether through environmental damage, war, or some other catastrophe. It's possible that many intelligent civilizations reach a point where they are unable to sustain themselves and ultimately fail. Another possibility is that intelligent civilizations have no desire to make contact with us. Perhaps they are simply not interested in Earth or in communicating with other species. Or perhaps they are too far away to detect our signals and we are too primitive to detect theirs. Regardless of the reasons, the Fermi paradox remains a mystery and a subject of much speculation. But let's turn our attention to the possibility of life in our own solar system. While we haven't found any evidence of intelligent life, there are some promising signs that microbial life might exist on other planets or moons. For example, NASA's Mars rover has detected methane on the planet's surface, which could be a sign of microbial life. And scientists have found evidence of subsurface oceans on some of Jupiter and Saturn's moons, which could potentially support life. If we do find evidence of microbial life in our own solar system, it would be a major discovery and could have significant implications for our understanding of life in the universe. Let's consider the potential implications of discovering intelligent life. If we were to make contact with an alien civilization, it could have profound impacts on our society and our understanding of the universe. For one, it could challenge our existing beliefs and worldviews. We might need to reevaluate our ideas about our place in the cosmos, our religious and philosophical beliefs, and our understanding of the origins of life. It could also raise questions about the ethics of interacting with other intelligent species and the responsibilities that come with such interactions. Another potential impact is on our technology and scientific progress. If we were to encounter a more advanced civilization, we could learn from their technology and knowledge, potentially accelerating our own progress. On the other hand, it could also pose a threat if the aliens have hostile intentions towards us. It's difficult to say for certain whether aliens, if they exist, would be dangerous to us. We have no concrete evidence of intelligent extraterrestrial life, and so any speculation about their intentions or behaviors is purely hypothetical. Some people argue that aliens could be dangerous if they are more technologically advanced than us and have the ability to conquer or destroy us. Others point out that any civilization advanced enough to travel through space would likely have a more sophisticated understanding of the universe and may be more peaceful and cooperative. It's also possible that aliens could be indifferent to us, simply observing us from a distance without any intention to interact with us at all. Overall, while it's fun to speculate about the potential dangers of alien life, the truth is that we simply don't know enough to make any definitive conclusions about their intentions or behaviors. The search for extraterrestrial life should be approached with an open mind and a healthy dose of curiosity rather than fear or paranoia. Regardless of the potential impacts, the search for intelligent life continues. We are constantly developing new technology and refining our techniques to search for signals and evidence of other civilizations. And while the chances of finding intelligent life may be slim, the pursuit of knowledge and discovery is a worthy endeavor in and of itself. That's all for today's topic of aliens. We hope you've enjoyed this discussion and learned something new. If you have any questions or comments, please leave them in the comment section below. Thanks for tuning in, and we'll see you next time. Nothing existed at the outset. After then, the cosmos began to take shape some 13.7 billion years ago. How this came to be, or if there was ever a time before, time is still a mystery. Yet, physicists have pieced together an approximate timeline of significant events in the cosmos's existence using telescope data and models of particle physics. From its beginning to its inevitable demise, we examine key points in the evolution of our universe here. Welcome to the endless universe. If you're interested in amazing videos about the universe, be sure to subscribe to our channel to stay updated. The Big Bang. The Big Bang is a moment in time, not a location in space, from whence all else unfolded. To be more precise, it's the first second of time, the point in history from which all other seconds have been measured. The Big Bang, despite its common name, was not an explosion, but rather a time when the universe was incredibly hot and dense before space began to expand outward in all directions simultaneously. The Big Bang scenario suggests that the universe was an infinitesimally small point of infinite density. However, this is merely a convenient way of expressing that we don't know for sure what happened at that time. We now understand the cosmos to break down at the Big Bang because mathematical infinities don't make sense in physics equations. Cosmic inflation era. The next cosmic confab was to rapidly expand in size. The universe may have expanded exponentially after the Big Bang, tearing off previously colliding parts of space. This period, known as inflation, is still mostly theoretical, but it has gained favor among cosmologists as a possible explanation for the striking similarity between distant parts of space. Attempts to detect this expansion in light from the early cosmos were reported in 2014. Nevertheless, further investigation revealed that the true culprit was nothing more than interplanetary dust causing interference. Quark-gluon plasma. The temperature of the early cosmos was between 7 trillion and 10 trillion degrees Fahrenheit, or 4 trillion and 6 trillion degrees Celsius, just a few milliseconds after the Big Bang. Quarks, elementary particles ordinarily contained within protons and neutrons, were free to move about at these temperatures. These quarks were combined with gluons, carriers of the basic force known as the strong force, in a primordial that pervaded the whole universe. In particle accelerators on Earth, scientists have replicated these circumstances. In both terrestrial atom smashers and the early cosmos, the challenging to achieve condition only lasted for a few fractions of a second. The early epoch. The subsequent period of time, beginning perhaps in the neighborhood of a few thousandths of a second following the Big Bang, was a period of intense activity. The universe chilled as it expanded, creating an environment conducive to the merger of quarks into protons and neutrons. The cosmic neutrino background, which has not yet been detected by scientists, was created 1 second after the Big Bang, when the density of the cosmos decreased sufficiently for neutrinos to sail across space without interacting with anything. The first atoms, protons and neutrons, fused together during the first 3 minutes of the universe's existence, creating the isotope of hydrogen known as deuterium, along with helium, and a trace quantity of the next lightest element, lithium. Yet, this procedure ceased as the temperature dropped. As temperatures settled down 380,000 years after the Big Bang, hydrogen and helium atoms could join with free electrons to form the first neutral atoms. The cosmic microwave background, a remnant of this epoch first identified in 1965, was created when photons that had previously collided with electrons were able to flow without being disrupted. The Dark Ages. There was a lengthy period of time when nothing in the cosmos emitted any light. The cosmic dark ages refer to this time frame of around 100 million years. Because practically all of what astronomers know about the cosmos can be gleaned by studying starlight, this era remains exceptionally challenging to study. It's hard to piece together what happened if there are no stars to guide us. The first stars. The first stars were formed when hydrogen and helium began to compress into massive spheres some 180 million years after the Big Bang, creating hellish temperatures at their centers. After the neutral hydrogen atoms in interstellar space were broken apart into protons and electrons by the intense photons generated by early stars and galaxies, the cosmos entered a period known as cosmic dawn or reionization. It's hard to put a time limit on reionization. As it happened so soon after the Big Bang, its signals had been masked by subsequent gas and dust. Thus, the most that scientists can determine is that it was finished by around 500 million years after the Great Bang. Large-scale structure. Almost a billion years after the Big Bang, supermassive black holes developed at the cores of merging early galaxies. Intense quasars, visible from 12 billion light-years away, switched on and began emitting their bright beams of light. The universe's middle years. Throughout the subsequent few billion years, the cosmos underwent more evolution. Denser regions in the early cosmos drew more material due to gravity. A gorgeous filamentary cosmic web is the result of them slowly expanding into galaxy clusters and lengthy strands of gas and dust. Birth of the solar system. A yellow star with rings around it formed from a cloud of gas around 4.5 billion years ago in one galaxy. These accreted rings eventually became the 8 planets of our solar system, as well as numerous comets, asteroids, dwarf planets, and moons. Either the third planet out from the sun retained a lot of water via this process, or it received a deluge of ice and water from comets later on. Earth and humanity. Little primitive bacteria appeared on that third watery world between 3.8 and 3.5 billion years ago. These organisms arose and progressed into amazing marine monsters and enormous dinosaurs that fed on leaves. Some 200,000 years ago, upright beings emerged, capable of contemplating the vastness of space and learning about the universe's origins. The end, or not. It isn't the final chapter, of course. The future of the cosmos is still a mystery to physicists. It is dependent on our ability to accurately quantify the characteristics of dark energy, the unknown factor thought to be accelerating the expansion of the universe. All the stars in all the galaxies will have burned out, and even black holes will evaporate into nothing if the universe continues to expand forever, leaving behind a lifeless cosmos saturated with inert energy if this scenario comes to pass. Alternatively, the Great Crunch, a reversal of the Big Bang in which gravity triumphs over dark energy's expansionary force, will occur. The Great Rip, in which the cosmos rips itself apart, is another possibility if dark energy accelerates everything apart to greater and greater distances. Thanks for watching, and don't forget to hit the like button, subscribe, and turn on notifications for more content like this in the future. Our solar system is a harsh environment. Volcanoes are destructive everywhere, from the ice volcanoes of Saturn's moon, Enceladus, to the immense lava fields of Jupiter's moon, Io, to our own planet Earth. It is truly true that we would not be here if there were no volcanoes. Volcanoes influence and alter our climate. Volcanoes are both the creators and destroyers of existence. Today's spacecraft and observatories have revealed volcanoes on planets we once believed to be dead. The discovery of volcanoes on an object smaller than the moon was a major surprise. If there are volcanoes on other worlds, could there also be life? Volcanoes are among the most potent natural occurrences on Earth. They create new land, destroy the old. They emit gases that alter the atmosphere we breathe. Deep in our oceans, volcanic heat fuels bizarre new forms of life. Volcanoes help sustain life on Earth. Now we look for signs of life on other planets. We understand that life requires water. We are aware that it requires energy. And this is where volcanoes come in, as they generate tremendous quantities of energy. If we locate volcanoes on other planets, we may discover life. The search begins with this planet, which orbits the Earth closest. Venus, a planet that closely resembles our own. Venus and Earth have similar masses. Earth and Venus were very similar 3 billion years ago, with new land, new oceans, and an atmosphere. Both planets was conducive to life. On Venus, however, something went awry. Something caused the history of Venus to diverge drastically from that of Earth. Venus took a definite turn to the dark side a long time ago. Venus is hell, our malevolent twin planet. Today, the surface of Venus is like a furnace. The surface is 900 degrees Fahrenheit hot. It is actually heated enough to melt some metals, so you have no chance. Venus is a greenhouse world. Its atmosphere contains a high concentration of carbon dioxide. It absorbs solar heat like a blanket. Actual images of Venus's surface reveal a desolate, extremely hot desolation. The planet was annihilated by dense CO2 atmosphere. The CO2 was produced by volcanoes. Spacecraft in orbit provided the initial clues. Radar broke through Venus's thick clouds and showed volcanic formations all over the planet. These formations look a lot like the shield volcanoes on Earth. Round and flat, shield volcanoes derive their name from their shape. These volcanoes ooze, but they ooze for thousands of years. Once we were able to map the entire surface of Venus using cloud-penetrating radar, we began to examine its landforms and discovered that many of them were quite familiar. In particular, we observed enormous shield volcanoes that resembled the shield volcanoes in Hawaii. The radar images of Venus were identical to those of Hawaii's shield volcanoes. In the past, Venus was home to volcanoes. We were astounded to see a picture of Venus for the first time. We discovered a cratered volcanic surface. There are at least 1,000 large volcanoes and possibly tens or hundreds of thousands of lesser ones. Lava plains cover 3/4 of Venus's surface, evidence of an ancient catastrophe. This could have been a home for life. It was instead consumed by flames. Numerous trillions of tons of carbon dioxide were expelled by Venus's volcanoes into the planet's atmosphere. The temperature rose dramatically. The oceans evaporated. On Earth, carbon dioxide is able to absorb into the rocks. It can be absorbed by the ocean. On Venus, however, there is no water, and the temperature is so high that carbon dioxide cannot even combine with the minerals. Volcanoes released carbon dioxide into the atmosphere eons ago, and as time passed, fewer and fewer methods existed to remove it from the atmosphere. Volcanoes sanitized the entire planet if Venus ever supported life. Earth is the only known planet with life. That may alter. This is the gas giant Jupiter, with its moons believed to be frozen and lifeless. A mystery surfaces as a cloud hovering over a cold and lifeless world upon closer inspection. On Venus, volcanoes transformed a planet similar to Earth into a hyperheated inferno. Volcanoes on a planet similar to Earth were not a surprise, but the discovery of volcanoes on the Moon was an astonishment. In March 1979, the Voyager 1 spacecraft provided us with our first up-close look at Jupiter's minuscule moon Io, a world we once believed to be frozen and lifeless. And they witnessed something odd. They observed this arc next to the moon, and it almost appeared as though there was a second moon behind it. We scratched our minds and asked, what could that be? Everyone is aware that Io is lifeless, dull, and uninteresting. And then people realized, oh my God, it's a volcanic eruption. We discovered that the area is engulfed in volcanoes. It is geologically extremely active. There are constant volcanic eruptions. And what they're erupting is a great deal of sulfur, which becomes extremely heated. And sulfur changes color as its temperature changes. It may be red, orange, yellow, or even black. As a result, these images of Io's visage resemble a pizza with various types of cheese and olives where the small black spots are. Io is not dead. It is alive and growing. There are more than 400 active volcanoes. The largest, Pele, erupts from a gigantic lava lake. It extends approximately 400 kilometers into space. It would be an extraordinary sight if we could stand on the edge of that lava lake and observe that plume shooting off into the void of space. Pele's eruptions are so massive due to Io's diminutive size. There is nothing holding the lava back, as there is virtually no atmosphere and little gravity. These enormous eruptions make Earth's volcanoes resemble fireworks. How can a moon so small be so volcanic? The answer is Jupiter. Similar to how the moon raises the tides in Earth's oceans, Jupiter raises solid rock tides on Io. The orbit of Io around Jupiter is not circular. Sometimes it's closer, sometimes farther away. Jupiter exerts a gravitational force on Io. Jupiter's gravity stretches and squeezes Io. In every 2-day orbit, the ground rises and falls by nearly 300 feet. This pummeling generates extreme heat and enormous pressure. Wherever there are weak spots in the crust, lava erupts. Volcanism is therefore planet scale. In contrast to Earth, where certain portions are active around the plates or in weak areas, this is an entire moon. That's one active hotspot. Io is the most volcanism-active planet in the solar system as a result of the immense power of gravity. Volcanic activity on Io has taught us something new. It taught us that internal energy sources can drive volcanism in a manner distinct from that on Earth. Io is a lava world that is extremely hot and violent. It is difficult to conceive of anything surviving there. We have discovered strange eruptions on numerous planets and moons, but so far, the only world where volcanoes are linked to life is ours, or so we thought. This is Europa. It orbits Jupiter at a distance of nearly 500 million miles from the Sun. and is a 2,000-mile wide sphere of ice. From afar, its surface appears to be polished. Up close, it's a different story. Europa is pummeled by Jupiter's immense gravity, just like its companion Io. The surface rises and bends, forming ridges and deep fissures. When we first obtained close-up images of Jupiter's moon Europa, they seemed vaguely familiar, and it turns out that they resemble Arctic ice flows. And it turns out they are the same. A global liquid ocean lies beneath Europa's several-mile-thick icy crust. Magnetic measurements indicate Europa's ocean is an astounding 60 miles deep. The gravitational impact of Jupiter heating the rocky interior and melts the ice above. As the core is stretched by tides and heated, possibly melting, it is not preposterous to believe that there is a boundary between a hot core and a liquid water ocean. Underwater eruptions on Earth are surrounded by life. The same may occur on Europa. Here, the darkness is complete. The pressure, a crushing 2,000 Earth atmospheres. A harsh environment, but perhaps a cradle for life. If there is evidence of life on Earth, why not Europa? An energy source, volcanic activity, a universal solvent, liquid water, and a complex hydrocarbon chemistry are all present. Life would be difficult, but not impossible on Europa. There is life at every extreme on Earth, including searing heat, crushing pressure, and absolute darkness. Life on Europa may resemble our own in unanticipated ways. If life exists beneath Europa's ice, it would be aquatic, but without eyes, because there is no significant light. Organisms that essentially feed off the energy of the volcano would most likely utilize sonar to make sense of their surroundings. Volcanoes on Europa could be the genesis of new life. It is even conceivable that Europa is typical, that this is the norm for planets with life. Earth may represent an exception. Consider that Europa could serve as a model for the billions of moons in the universe with liquid oceans. So, all of a sudden, our horizons have expanded several billion times by looking at the moons of Jupiter. Our solar system is home to more than 170 moons. Multiply this by the size of the universe, and that's a lot of potential habitats for life. Only liquid water and a source of energy are required. Potentially, both are provided by volcanoes, and they are ubiquitous. This is Saturn, twice as far from the Sun as Jupiter. However, it also has volcanic moons, and similar to Europa, these moons could support life. Saturn is one of the odd planets in our solar system, with a 600,000-mile-wide ring system, an astounding 62 moons, and one with a secret. Enceladus is one of the lesser and more distant moons of Saturn, and it's been known for a long time that it's covered in ice due to its extremely brilliant and reflective surface. However, when the Cassini spacecraft visited the planet, it made a remarkable discovery. Not on the planet itself, but on Enceladus did the Cassini probe disclose a remarkable discovery. A massive plume, backlit by the sun and erupting into space, is conclusive evidence of volcanic activity. Cassini's sensors zoom in on the south pole of the moon to capture these enormous craters scarring its surface. At the south pole of Enceladus, there are extraordinarily large fissures, which open and close as Enceladus orbits Saturn due to the tides. Now, these fissures are enormous. They extend for hundreds of kilometers. And when they begin to open, you would see a large crevasse opening at approximately 100 miles per hour along its length. It'd be incredibly spectacular. Huge gravitational forces cause the surface to open and contract with incredible velocity. This helps produce the heat necessary to dissolve ice and form oceans beneath the surface. The conditions of the water beneath the surface of Enceladus are ideal for life. It is at the ideal temperature. It would be beneficial for life. Liquid water would be just like seawater here on Earth. And the chemistry of the water we observe erupting from these fissures suggests that it contains salt. It contains organic matter as well. Therefore, we have identified a location in the solar system where there is a strong possibility that there is life right now. In the ice particles, Cassini has detected complex carbon molecules. In conjunction with liquid water, they suggest that perhaps life could exist deep within this mysterious moon. Enceladus is possibly not alone. Another of Saturn's moons might also harbor life. Titan, one of the largest moons in our solar system, the only moon with a thick atmosphere, a frozen world, ice as hard as rock, lakes of liquid methane. Yet, we may also discover evidence of volcanoes and the tantalizing possibility of extraterrestrial life on this planet. Volcanoes are one of the most destructive forces in the universe, as evidenced by Io's raging conflagration and Triton's ice and nitrogen explosions. Even on Saturn's enigmatic moon Titan, however, destruction can lead to the prospect of life. It has a diameter of 3,000 miles, making it larger than Mercury. It has the thickest atmosphere of any moon in our solar system. There is weather, including cyclones, winds, rain, and even lakes, but the temperature is so low that liquid methane replaces water, and it's loaded with essential compounds for life. Titan has proven to be one of the most fascinating locations in the solar system. It's an active world. It is the only moon with a dense atmosphere, an atmosphere very similar to that of Earth due to the presence of nitrogen and, as it turns out, organic molecules. High in Titan's atmosphere, methane gas reacts with sunlight to produce compounds essential to life. But if sunlight consistently converts methane into organic compounds, why does methane not run out? Methane is abundant in the atmosphere, but we know that it is quickly eliminated by sunlight, so it shouldn't be there. There must exist a source of methane. Something on Titan emits methane in a continuous stream. Cassini has spotted what appears to be a crater. Infrared cameras disclose that the crater is surrounded by various types of materials. Scientists believe the green areas may be volcanic, possibly plains of lava ejected from Titan's interior. On Titan, the boiling liquid emitted by volcanoes could be either ammonia or water. Methane and ethane are emitted by Titan's volcanoes, and this is likely the cause of the planet's extremely dense cloud cover and orange atmosphere. This atmosphere likely originated from the outgassing of Titan's volcanoes. Even on a globe as frigid as Titan, volcanoes require heat. On Titan, there are two sources of heat. Radioactive substances heat the interior, and Saturn's enormous gravity caresses the moon, similar to Enceladus. These two forces produce sufficient heat to transform ice into water and liquid methane into gas. Could volcanoes on Titan give life a chance to survive here? The chemical reactions necessary for life as we know it require an atmosphere, a solid surface, liquid water, and heat. Volcanoes could provide everything on Titan. If life does exist on Titan, it would be truly alien. It would breathe hydrogen instead of oxygen and possibly swim through methane reservoirs at 300 degrees below zero. There may be oceans of ethane. Possibly, there are tidal pools as well as volcanic and hydrothermal activity. Perhaps volcanic heat could produce enough energy to support life on Titan. That's a speculation, but it can't be ruled out. However, We may not need to travel so far to discover signs of life. We may discover it on Mars, a volcanism-rich world much closer to home. Volcanoes are ubiquitous throughout the solar system. Planets such as Io, Titan, and Triton are intricate, volatile, and violent. Once, we believed that Earth was the only planet with both volcanoes and life. Now, we find volcanoes everywhere, but alien life has yet to be discovered. Volcanoes exemplify the absolute force of creation and destruction. They go hand in hand. It is literally true that if there weren't volcanoes here, we would not be here either. Volcanic cauldrons are the birthplace of life. Volcanoes create new landscapes, seed the atmosphere with complex chemicals, replace the old with the new. If volcanoes are linked to the processes of life, where is life on other planets? Perhaps the origin of the answer lies in ancient times, when the solar system was immature on a planet similar to our own. This is the planet Mars. 3 billion years ago, volcanoes were active. The greatest volcano in the solar system still stands. The cliffs leading up to it are greater than 6 miles in height. Even Mount Everest would be comfortable in their shadow. This is the formidable Olympus Mons. It covers an area the size of Arizona. Its crater alone is 53 miles wide. A structure of this magnitude takes millions of years to construct, a period of time that volcanoes on Earth never have. The Earth's crust is constantly in motion. In the depths of the Earth, a solitary hotspot forces magma to the surface, creating a new volcanic island. While the hot point remains stationary, the surface is in motion. The new island moves away from the hot location and is replaced by a new volcanic island. Mars is different. The crust is locked solid. On Mars, there is simply no tectonic activity. The crust is one big solid plate, and so if there's a hot spot, it just sits there and builds and builds and builds. And you get a larger and bigger volcano. Therefore, Olympus Mons is so enormous. Today, Olympus Mons is an icy remnant of a distant, warmer era. Olympus, an extinct volcano on a fading planet, is now a veritable colossus due to Mars's diminished atmosphere. However, the ancient volcanic terrain of Mars could one day support life. The evidence is readily available on Earth. Volcanoes on Hawaii have formed enigmatic tunnels known as lava tubes, which are formed when rivers of molten rock rush into the ocean. Lava tunnels are formed when there is an underground river of basaltic lava, magma, and molten rock at 2,000 degrees Fahrenheit. Imagine it as an icy river with a crust of ice forming on the surface. It's the same, except here, the crust is solid rock and the river continues to flow beneath, creating this cave, this lava conduit. Recent images imply that Mars volcanoes may have also created lava tubes. Any rocky planet with basaltic volcanism will likely contain lava pipelines. Now, after possibly millions of years of inactivity, these lava tunnels could revive life on the red planet. This existence will be our own. Radiation will be one of the obstacles that future humans will face when attempting to live on Mars. And especially during solar cyclones, the incoming cosmic rays can be lethal. The tunnels and caverns of Mars's extinct volcanoes could one day serve as an ideal home, retaining air and shielding us from harmful radiation. A long-dead volcano could help fill a world with new light. Volcanoes are capable of both destruction and creation.
For example, If the Big Dipper is shaped like a spear, you are in the Middle Pleistocene. We can also request that the computer move a constellation forward in time. Take the sign of Leo the Lion. The zodiac is a band of 12 constellations that wrap around the sky in the sun's apparent annual path as it travels.
Supermassive black holes are one of the major players in the evolution of galaxies.
With no supermassive black holes, you have no Milky Way galaxy, no sun, no Earth, no you.
They're the driving force at the heart of nearly every galaxy in the cosmos.
They are the most monstrous and scary and bizarre aspects of our world, which just fascinates me.
Now, a new mystery has emerged about the oldest supermassive black holes.
We see supermassive black holes in the very early universe, and we don't understand how they grew so large so quickly.
We have clues about their formation, but can we solve the mystery of this supermassive growth spurt? In 2017, scientists gazing deep into the distant universe discover something completely unexpected. A vast supermassive black hole dating from the earliest days of the universe.
This was 690 million years after the Big Bang. The universe was about 5 or 6% of the age that it is now.
Finding a supermassive black hole in the early universe is like finding an NFL defensive lineman playing in Pee Wee football. Something that big shouldn't exist that young.
The supermassive black hole wasn't just super early, it was super big. 800 million times the mass of our sun.
In just a few 100 million years, the universe has somehow been able to collapse nearly 1 billion suns worth of material into a giant black hole. And we honestly just don't know how that's possible.
We measure black holes by the mass of our sun, solar masses. Regular or stellar black holes are a few to 100 solar masses. Supermassive black holes weigh from 100,000 to billions of suns. And scientists have now found over 100 of these monsters in the early universe.
We were shocked to find even one of them existing so early after the Big Bang. It was kind of freakish, to be honest. But then to find that there's whole populations of these things that exist and are well in place at the earliest times that we can look at was truly shocking.
We believe supermassive black holes might help explain the evolution and the destiny of the universe. Astronomers are striving to understand them.
Understanding the origin of supermassive black holes and how they could form so early in the universe's history is something that would change all of astronomy and astrophysics.
How do you get something that massive to form in such a short amount of time?
It's a big question. To begin to answer it, we have to start small by asking how regular stellar black holes form.
Black holes form through the collapse of stars. Everyone knows that. You have a big enough star and it'll collapse to form a black hole.
A really massive star dies in a violent supernova explosion, and if they have sufficient mass, what's left over collapses into a black hole.
The bigger the star was, the bigger the black hole is to start with.
Were the stars of the early universe big enough to collapse into supermassive black holes?
The very early universe was much different than the universe you see around us today. It was filled entirely with hydrogen and helium gas.
This gas amassed into giant clouds, which collapsed under their own gravity. Nuclear fusion ignited the dense cores, and the first stars were born.
Now, we think that these earliest clouds of gas probably made bigger stars than clouds of gas do in our local or today's universe.
It was possible to get huge, giant stars that we call population 3 stars that were just utterly massive.
Population 3 stars are the oldest category of star. Like stellar dinosaurs, they dominated the universe a long time ago. Now, they're extinct.
They'd be weird stars. They would be incredibly bright in the ultraviolet and have very unique signatures that are very different from stars today. But precisely because they're so big and so bright, they would be very short-lived.
These first stars lived fast and died young, exploding in supernovas, leaving behind black holes. But were they supermassive black holes?
When a star blows up, when it goes supernova, most of the mass is ejected away. It just goes flying out, leaving a dense neutron star or perhaps a black hole, but it won't have much mass because most of that mass was blown away.
Even though population 3 stars in the infant universe were very large, they weren't big enough to leave a supermassive black hole behind when they exploded.
Perhaps if we can skip the supernova step, that might be one pathway to understanding how supermassive black holes formed.
Could a dying star's entire mass collapse into a black hole? A clue may lie in a galaxy nicknamed the Fireworks Galaxy.
The Fireworks Galaxy has that flashy name because when you look at it, there are all these supernova explosions going off and making quite a show.
Recently, astronomers were keeping an eye on one extremely bright star in the Fireworks Galaxy.
This star is exactly the kind that we know explodes as a supernova. Astronomers expected it to explode, but then it did something even weirder.
Astronomy is so wonderful because sometimes you see things right in front of your eyes that you can't explain. We saw an entire star just disappear.
In 2007, the star looked like this. By 2015, it had completely vanished. There was no flare or debris from a supernova explosion.
So what the heck is going on?
It turns out that not every massive star blows up with all the fireworks of a normal supernova. You can get what's called a failed supernova.
A supernova fails when the shock wave generated inside a collapsing star can't escape.
In some cases, when the star is very massive, the shock wave never has a chance to get all the way out of the star by the time the star itself collapses into a black hole. Then you have a failed supernova.
The Fireworks Galaxy star may have been massive enough to smother its own explosion before collapsing to form a black hole.
Everything collapses into the black hole. You can actually have a black hole with all the mass of the original star.
Back in the early universe, could the enormous population 3 stars have died as failed supernovas, leaving behind supermassive black holes?
These population 3 stars don't seem to me to be a good contender for the precursor to supermassive black holes. They just would not have enough mass.
Even the most massive stars are only a couple of 100 times more massive than our sun, whereas a supermassive black hole is millions or billions of times the mass of our sun.
Early supermassive black holes can't have formed from collapsing stars. Even giant stars aren't massive enough. So is there some other path to being supermassive? Were stellar black holes cosmic bodybuilders on a fast-track bulking program? We ruled out the idea that they were created from the collapse of very large stars. Maybe they started out as smaller stellar mass black holes and grew to be supermassive by eating.
Black holes are not fussy eaters. They'll consume anything that comes in their path. You know, gas, planets, stars, it doesn't matter. And everything that they consume adds mass to the black hole.
We've spotted a stellar mass black hole currently eating in our Milky Way galaxy. 15 times the mass of the Sun, Cygnus X1 is steadily feeding off the material that swirls around it.
Some black holes are fed through things called accretion disks. It's kind of like the rings around Saturn. There's this thick or thin disk of material around the black hole that feeds it.
Cygnus X1's accretion disk gets constant refills from a nearby source. A vast star, 20 times the mass of the Sun, called a blue supergiant. The black hole has been feeding on gas from this star for about 5 million years.
So if you ask how do black holes eat or consume gas, the answer is gravity. These are very massive objects, and anything that comes within their sphere of influence can be consumed by the black hole.
The more mass a black hole gains, the greater its gravity, and the more food it attracts.
A black hole growing is a little bit like a snowball rolling down a hill. The bigger the snowball gets, the more snow it can accumulate, and so the bigger it gets. It's a runaway effect.
But even if Cygnus X1 follows this runaway growth trajectory, it still may never reach supermassive status. The black holes of the early universe must have fed at a much faster rate.
The biggest issue is, how do you have enough time in the early universe to go from a small black hole that's born from a star to something that's supermassive?
GRS 1915 is another stellar mass black hole. It's a greedy eater, accreting at up to 40 times the rate of Cygnus X1. And when something gobbles food that quickly, it can begin to overheat.
The black hole is accreting a lot of material, and as it's eating, the accretion disk really heats up to very high temperatures. And at those high temperatures, you can get a lot of light coming out of the system.
So the more material that a black hole eats and swallows, the brighter it shines.
This stellar black hole sometimes eats so much, so quickly, its accretion disk pushes out radiation almost 1 million times brighter than our sun. But this brightness has a serious consequence. It stops the black hole from eating and growing larger.
If you wanted me to gain as much mass as possible, as quickly as possible, you would just keep feeding me hamburgers nonstop or whatever. But black holes have a problem that when they eat a lot, they tend to just gobble up a lot of the food in their neighborhood, and then also they start shining out so much stuff that it pushes away much of the food.
The brightness, or luminosity, gets so intense, it pushes away incoming material, a sort of safety valve called the Eddington limit.
So in many ways, the Eddington rate could be a kind of a speed limit for the growth of black holes. It could be a governor that prevents black holes from growing even faster by just dumping more and more gas onto it. Eventually, you're going to hit that Eddington limit, and that more gas that you're dumping on won't actually reach the black hole.
This cosmic method of portion control means that stellar black holes in the early universe couldn't have gained weight fast enough to become supermassive.
Black holes need time to grow. They need to feed, they need to eat. Maybe you need to skip a few steps. Maybe you need to start at a medium size or bigger in order to get to supermassive by the time we observe it.
So was there another type of black hole in the early universe? Something big enough to grow supermassive in the time available? In 2017, astronomers studied a dense star cluster called 47 Tucanae on the outskirts of our own galaxy. They detected 25 pulsars, bodies that spin and emit radiation like cosmic lighthouses.
These pulsars are all orbiting a central object. And even though we couldn't see the central object itself, we could watch the behavior in the orbits of all these pulsars around it, and we could figure out how big that central object was.
Well, when you do the math, you come up with something that is about 1,500 to 2,000 times the mass of the Sun. That's actually hidden in the heart of that globular cluster.
So what is the invisible object?
Whatever's lurking at the center of 47 Tucanae has to be big and it has to be black.
Astronomers think it's a large black hole. At 1,500 times the mass of the Sun, the object is much bigger than a regular stellar black hole, but too small to be supermassive. Could it be what's known as an intermediate mass black hole?
It's extremely hard to find any of these intermediate mass black holes.
This rare category of black hole ranges between 100 and 100,000 solar masses. At that size, they may have been large enough to become supermassive very quickly.
Intermediate mass black holes could be what give supermassive black holes a head start in life.
Astronomers search for intermediate mass black holes. They may have been large enough to act as seeds for the first supermassive black holes. Yet so far, they've escaped discovery.
They're like the missing link. And I mean that for real. They're missing.
Imagine you're an alien who's arrived on the planet Earth, and you know very little about the human species. And when you look around, you only notice tiny, tiny little children and grown adults. You don't see any adolescents, right? And intrinsically, you know that the tiny little children grow up to be full-size adults, but you don't see how they got there, right? You don't see the intermediate stages of growth. That would be really, really weird, right? That is the case for supermassive black holes. So it's like a universe without teenagers.
Or that's how it looked until September 2020. Scientists studying gravitational waves picked up the signal of an extreme event in the distant universe.
What researchers are looking for are things called gravitational waves. They're like ripples in space itself. Most signals sound a little bit like a chirp. It's a noise that's very characteristic. It goes a bit like sort of whoop. But this particular event was so extreme and so sudden, it just sounded more like a thud.
This faint thud from halfway across the universe is music to the ears of intermediate black hole hunters, because its pitch can mean only one thing.
This could only have been created by two really massive black holes colliding into each other and producing a combined black hole with a mass that's 142 times the mass of our Sun. So that is, for the first time, getting into this intermediate mass black hole regime.
This is the first confirmed observation of an intermediate black hole.
Finding direct evidence like this for an intermediate mass black hole is absolutely fantastic.
Now that we're certain intermediate black holes exist, could they help explain the origin of supermassive black holes in the early universe?
These intermediate black holes really could be the first seeds of the supermassive black holes. You would need something like that to form really big, really early, to even begin to explain these very massive, supermassive black holes that have formed just a short time after the Big Bang.
How do intermediate black holes form in the first place? The recently discovered one came from the collision of two smaller black holes. They may also form in giant clouds of gas.
It could be that in the earlier universe, you can just have large clouds of gas that can lose enough energy quickly enough to just spontaneously collapse and form a black hole of this size.
The enormous cloud of gas contracts and gets denser and denser, the way it would if it was starting to form stars, but it's somehow able to remain coherent and collapse into one giant object that forms an intermediate mass black hole.
A giant gas cloud undergoing a direct collapse down to an intermediate mass black hole would be a rare sight.
You think it would go giant cloud, slowly collapsing black hole. But instead, it's more like giant cloud, black hole.
So one day you see this massive gas complex, and then you blink, and it's collapsed, and now you're face to face with a big black hole.
At least, that's the theory.
Getting a black hole to form from the direct collapse of a gas cloud is very tricky.
Gas clouds tend to split up and collapse into a multitude of stars. Collapsing into one object would take unique conditions. One possible scenario involves two neighboring galaxies. The first, a young proto-galaxy, a gas cloud yet to form stars. Next door sits a larger galaxy. It's forming so many stars, radiation is bursting out all over its young neighbor.
Because they're in close proximity, the energy from the large galaxy prevents the smaller galaxy from forming its stars. So that means that it'll continue to collapse in cloud form before moving to star formation.
The gas cloud becomes large and dense enough that gravity eventually pulls it in on itself. When it can't ignite into stars, the collapse creates an intermediate mass black hole.
I think this idea is very intriguing. I don't know if it's physically possible, but then again, there's a lot we don't know about the early universe.
2017. Scientists simulated another way that intermediate mass black holes might form in the infant universe, under the influence of dark matter.
Dark matter was absolutely critical for the evolution of structure in the early universe. Without dark matter, there would be virtually nothing.
Dark matter is mysterious. We know it has a gravitational pull on ordinary matter. One idea is that it helped form very large stars in the early universe, stars that later collapsed into intermediate mass black holes.
The idea is something like this. About 100 million years after the Big Bang, dark matter, which dominated the gravitational early universe, was forming big clumps. Then there might have been these supersonic streams of regular matter after the Big Bang, and they were directed into these gravitational cores where dark matter was gathering everything together.
When scientists simulated this, they found that dark matter's strong gravity could pull in huge clouds of gas.
You could actually accumulate as much as, say, 34,000 times the mass of the sun into one gigantic star-like object. That's big enough, it would just collapse into a black hole.
A black hole of 34,000 solar masses would sit squarely in the intermediate mass category. It would be large enough to potentially become a supermassive black hole.
It's possible that dark matter directing streams of gas together about 100 million years after the Big Bang was the seed for these supermassive black holes.
Whichever way intermediate mass black holes form, they seem like a good way to start explaining supermassive black holes in the early universe.
The question is then, how do they grow? How do you start from this seed and end up, with something that's 1 billion times the mass of the sun?
Maybe early intermediate mass black holes had enormous appetites, gorging themselves to a supermassive state, feeding on the biggest meals our universe can serve up. Astronomers want to know how the earliest supermassive black holes got so big so quickly. Could they have started as intermediate mass black holes that devoured supersized meals?
It's possible that these intermediate mass black holes could form in an exceptionally rare environment where it can accrete new material at an enormously high rate.
So far, we only have direct evidence of one intermediate mass black hole, and we can't yet detect how it eats and grows. But we could look at much larger black holes for clues. In 2019, astronomers searched for supermassive black holes that are actively feeding. They pinpointed 12 quasars from the beginning of the cosmos.
Quasars are among the brightest objects we know of in the universe, and they're what happens when a supermassive black hole at the center of a galaxy is swallowing up gas and dust, and that generates a tremendous amount of energy and luminosity that we can see.
Surrounding these early galaxies are enormous gas reservoirs called hydrogen halos.
This is great because that acts as fuel for those supermassive black holes. Cold gas can stream into those black holes and feed them.
These huge halos of cold gas are also the building blocks of stars.
These enormous, pristine halos of hydrogen around early galaxies, they're going to be reservoirs to power star formation.
Star formation is a violent process that can create turbulence in a galaxy.
That turbulence makes the gas fall toward the black hole, and then that makes the black hole even bigger.
Hydrogen halos might have spoon-fed early supermassive black holes. This process may have also helped intermediate mass black holes grow quickly. Could the largest black holes show us other, more drastic ways to put on weight? In October 2019, astronomers used telescopes to explore a remarkably clear galaxy called M77.
Because this galaxy is so near to us, we can study its central engine in really exquisite detail at very, very fine resolution.
Not only do you see the bright core, the bright nucleus, but you can see spiral arms, you can see structures in the galaxy, you can see how the whole galaxy is arranged.
When we examined M77's central supermassive black hole, we saw something extraordinary. Its food was coming not from one, but two accretion disks spinning in opposite directions.
Normally around a black hole, all of the gas is spinning in roughly the same direction, and that creates kind of a slow infall of gas and slow feeding. Here we've got a case where some of it's going one way, the other's going the other way. This is very unstable and can create opportunities for lots of gas to get gobbled up by that black hole.
The material in the disks is one enormous, ready-to-eat meal. But dinner will not be served until the outer disk slows down.
If there's a black hole at the center of a galaxy and you're orbiting around it fast enough to maintain your orbit, you're never going to fall in. You're just going to orbit forever, and you're just going to spin around, just like the way the Earth is going around the sun. What needs to happen if you want to fall in is to slow down your speed.
The outer accretion disk will gradually slow down and orbit more tightly against the inner disk. Dangerous collisions of the counter-rotating material will start to occur.
The double accretion disk is like drinking from two soda fountains at the same time. It's great while it lasts, but you're building up some serious gas that is just going to blow the whole thing away.
In just a few 100,000 years, the double disks will catastrophically collide, and their entire contents will fall into the central supermassive black hole. It will devour everything in one gulp, generating a colossal cosmic burp. In February of 2020, in the Ophiuchus galaxy cluster, we saw the damage a cosmic burp can do.
The Ophiuchus galaxy cluster is a collection of a huge number of galaxies all bound together by gravity. And there's gas in between these galaxies. And when astronomers looked at that gas in detail, what they found was a huge arcing structure in it that they realized was the edge of a cavity.
There's a massive hole in the gas that is over 15 times bigger than the entire Milky Way galaxy. Something frightening had to happen to carve this void out.
The size of this bubble is kind of stomping my brain. We are talking about a hole in this gas that is over 1 million light years wide.
The burp that created this cavity must have been astoundingly powerful.
There are a lot of ideas about this, but there's only one that really can explain it, and that's a supermassive black hole.
A supermassive black hole that suddenly got very greedy.
In order to drive an energetic event like this, the black hole needs to eat. Not just one meal, it needs to eat thousands of meals at the exact same time. It needs to go to an all-you-can-eat intergalactic buffet.
Sometime in the distant past, this black hole must have had a huge episode of just gorging on material falling in. That got super hot, blew out a tremendous amount of material in jets, beams that shot out from the poles of the disk, and that's what basically pushed its way out of that gas, forming this enormous cavity.
The colossal cosmic burp pushed food far away from the supermassive black hole, ending its all-you-can-eat binge and stopping its growth. If an intermediate mass black hole was this greedy, it would come to a similar end. It's no way to gain weight and become supermassive.
This is probably not the way the earliest supermassive black holes grew to such enormous size.
Is there another way supermassive black holes could have formed in the early universe without having to overeat? Maybe black holes smash their way to being giant-sized. November 2018. Astronomers scanning hundreds of nearby galaxies in infrared light spot something extraordinary. Some galaxies had not one supermassive black hole, but two. Are these pairs a clue to how supermassive black holes in the infant universe got so big, so fast?
Seeing these infrared images showing pairs of supermassive black holes at the centers of galaxies and showing that this could be very common just is mind-blowing to me.
The reason we see pairs of supermassive black holes is because two galaxies merge together.
In our picture of how the universe works, galaxies start off as smaller galaxies and grow by merging with other galaxies. So they'll be whooshing around each other and tearing each other up. It's actually quite violent.
When galaxies merge, we think their central supermassive black holes also merge, smashing into each other and combining to build a larger black hole.
Galaxy-scale mergers can be one of the most efficient growth mechanisms for supermassive black holes.
Maybe in the early universe, black holes of stellar or intermediate mass merged repeatedly, getting heavier and heavier until they became supermassive.
We don't really know how common supermassive black hole mergers were in the early universe, but we think they were more common than they are today because galaxies were closer together.
It would have taken millions of mergers to build up the largest supermassive black holes we see today, which could have been a tall order. If that many mergers did take place, then something else seems strange. The black holes we find in the universe are almost all stellar mass or supermassive.
You would imagine that if supermassive black holes form from smaller black holes coming together, then you'd find black holes with masses that range from the smallest to the largest. But we don't. We don't see intermediate mass black holes. My question is, where are the 10,000 solar mass and the 1,000 solar mass black holes?
There's another problem too.
We've never witnessed a supermassive black hole merger in the act. We've seen supermassive black holes on their way to merging, and we've seen ones that we think had gone through mergers, but we haven't caught one in the moment.
As supermassive black holes start merging, they spiral around each other, getting faster and faster the closer they get. But for them to finally merge together into a single black hole, they need to lose what astronomers call orbital energy.
The merger of supermassive black holes means that their orbits have to decay for them to get closer and closer together. So in order for an orbit to decay, that orbital energy has to go somewhere.
To lose energy, the merging supermassive black holes start disrupting the orbits of nearby stars, throwing them off their paths.
So something small and puny that weighs just one sun, like our own star, will often get in the path of these two and just get rocketed out, potentially unbound and flung out of the galaxy entirely.
Each time the supermassive black holes fling out a star, they lose more orbital energy. They get closer and closer.
But eventually, they've kicked out all the stars. There's nothing left.
The merger stalls. Like two sweethearts at a high school prom. The supermassive black holes dance as close as they can, but physical contact is not allowed.
So these two black holes could end up spiraling around each other for billions and billions of years.
This is called the final parsec problem.
In 1980, there was a famous paper which addressed this issue that supermassive black holes can only get to within about 1 parsec, or 3 light years of each other, before they can't merge or they stall.
We believe that supermassive black holes must merge. We know that galaxies merge, and so if the black holes didn't merge, we'd see lots of black holes floating around, and we don't. There's always one in the middle. So how do they merge?
Scientists are also investigating invisible forces at the beginning of the universe. Did something we can't see boost the size of the first supermassive black holes? One of the greatest mysteries in cosmology is how the first supermassive black holes got so large so quickly. We suspect mergers could help explain their size. And we know all types of black holes can grow by feeding. But we need more clues.
There's still so much we don't know about the early universe.
The further out we look in the universe, the less familiar the universe becomes. And so the more and more interesting and new physics you need to involve in order to explain these very strange observations.
The puzzle of fast-growing supermassive black holes in the infant universe now takes physicists somewhere new, to the little understood realm of magnetic fields.
The thing about magnetic fields is they're hard. They're hard to calculate, they're hard to understand. They're sort of the elephant in the room for astronomers. We know they're there, but we'd really rather not talk about them.
It's only recently that people are incorporating magnetic fields into their models of galaxy formation, and therefore, maybe it's under the influence of these fields that somehow these supermassive black holes are formed.
To investigate how magnetic fields influenced early supermassive black holes, we must look back at the very beginning. Soon after the Big Bang, the first particles form, cool, and become electrically charged.
Things were very different, radically different than they are now. Particles were whizzing by each other, everything was charged. It was just a very different landscape.
There are no stars yet, not even atoms. But some scientists think moving, charged particles created the first magnetic fields.
Magnetic fields were essentially everywhere in the early universe.
Those magnetic fields would have extended extremely large distances, like a very finely spun web all through the early universe.
Gradually, atoms form and gather into clouds of gas. These will become the first galaxies, and they're supermassive black holes. During this time, magnetic fields change. They bunch together around the forming galaxies, but we don't know how.
The thing with magnetic fields is they're extremely hard to predict, and you need to do really hard calculations that even now we're only just starting to do.
2017. Scientists design a groundbreaking computer model that simulates patterns of magnetism developing over time. The images show lines of magnetic force getting stronger and more focused across a vast region of space. Some astronomers think these emerging magnetic field lines help shape early galaxies and the supermassive black holes at their cores.
Magnetic fields have this ability to push material around. So one possibility is they could actually help push or funnel material in towards a growing black hole and help it grow faster than it would do otherwise.
In today's universe, we know magnetic fields around planets can deflect dust particles. On much larger scales, matter may also have been channeled into the centers of galaxies of the early universe.
Were the magnetic fields of these early galaxies a conduit that you could get matter dumped more and more into the middle and maybe build up a really big black hole?
Scientists are just starting to figure out the effects of magnetism at the beginning of the universe. But it could have been one of several mechanisms that influenced the size of early supermassive black holes.
We have lots of ideas for how you might be able to form supermassive black holes, but until we see actual mechanisms in action, we just can't really say which of them are the most important routes.
Maybe some other mechanism we haven't even thought of explains how the early supermassive black holes got so big so fast. Hopefully, one day, these monsters of the cosmos will reveal their secrets to us.
Supermassive black hole research is utterly mind-blowing to me. I mean, this is so cool.
It's important to explain how these early supermassive black holes formed in order to have a really concrete understanding of how the universe works.
Supermassive black holes are the great engines of cosmic change. They're enormous points of matter, and because they're just so massive, they can sculpt the evolution of galaxies.
They're the master key to most of the unsolved mysteries in physics.
We have a chance here to understand supermassive black holes so that we can understand the formation of galaxies, the generation of stars like our sun, and maybe even the appearance of life.
Tell that Greek was being used. On the prow of one of the earliest starships, perhaps a dodecahedron would be emblazoned with the inscription, Starship Theodorus of the planet Earth. Glacial pace throughout our world's history. We are continuing to prepare for the arrival of the stars. However, in another century or two, when the entirety of the solar system has been mapped out, we will also have organized our planet. We will have the motivation, the resources, and the technical know-how to travel to other star systems. We will have investigated various other planetary systems from great distances, some comparable to ours, while others dissimilar to ours. We will be able to determine which stars to travel to. The children of Thales and Aristarchus, Leonardo and Einstein, will then skim across the light years, accompanied by our machines and their descendants. There appear to be many planetary systems, however, we still count them all. Jupiter, Saturn, and Uranus are the 3 planets closest to us out of the 4 in our solar systems.
Dark matter itself has been around since the beginning of the universe. Without dark matter, we wouldn't be here.
But if you can't see dark matter, and if you can't touch it, does it really exist? The Hyades star cluster. This family of 700 stars is 150 light years from Earth. At the scale of the universe, it's in our backyard.
Hyades is actually close enough to Earth that you could see it with your naked eye.
When you look up at the night sky, Hyades is in that V shape in Taurus the Bull.
For most of its 650 million year lifetime, the Hyades enjoyed a peaceful existence. But something is breaking the calm.
The Hyades cluster is one of the most well-studied clusters of stars we have in the entire sky. And yet there's something very deeply mysterious going on.
2 star tails extend from the cluster's center. They should be roughly equal, but one tail is hemorrhaging stars.
Something is disrupting it. There's something exerting a force on it that's ripping stars out of their orbits.
Something with immense gravitational pull has passed by the cluster and robbed it of stars.
In order to be gravitationally pulling stars out of an object like Hyades, you need to have an incredibly massive structure, as much as 10 million times the mass of the sun.
This monstrous cosmic mugger should still be visible. But when we point our telescopes to where it should be, that region is empty.
There is nothing there. And I mean nothing.
And not a little bit or something dark or something small, but there's literally nothing that we can see.
We know something is out there, invisible and powerful. And whenever we witness these unseen assaults, a prime suspect gets called in, a phantom of physics. Dark matter. So, what can we confidently say about this mysterious cosmic substance?
It does not emit light, it does not reflect light, it does not absorb light.
The only thing we know about dark matter is that it has gravity. We're not even really sure it's matter at all. It's just that that's the only thing we know that has gravity.
We may not be able to see or touch dark matter, but we are very good at finding its fingerprints all over the universe. We can see dark matter's use of gravity to break and bind structures, and we've been spotting its handiwork for decades. Let's rewind back to 1933. Swiss-American physicist Fritz Zwicky tracks strange movements in a far-off collection of galaxies called the Coma Cluster. He knows he's not seeing the whole picture. Some galaxies are speeding around the cluster at inexplicably fast rates.
Zwicky's looking at these galaxies, and if the only mass that was there were the other galaxies you can see, you would expect these galaxies to be moving at about 50 miles a second, then they would stay bound to each other and not fly apart. Instead, he sees them moving at 1,000 miles a second.
At these velocities, galaxies should be flying off the cluster like sparks from fireworks. Zwicky realized there had to be extra stuff. In his words, dunkle materia.
Dark matter.
Dark matter.
Dark matter.
It becomes clear that Zwicky's Coma Cluster isn't an isolated case. Astronomers begin seeing the same dynamics within galaxies themselves. Astronomer Vera Rubin was the first to notice in 1977. She studied the Andromeda Galaxy, the Milky Way's next-door neighbor. Rubin was looking at Andromeda's stars as they orbited the center. She was trying to compare their speed.
So if you've ever been caught speeding by the police, I have just a few times, they usually have a radar speed gun, and that can tell them how fast you were going. What Vera Rubin did is that she had something even better than one of these radar guns. She had a spectrograph. And when she turned that towards the Andromeda Galaxy, she found speeding stars. They were going too fast.
In systems governed exclusively by gravity, objects farthest away from the center would take the longest to complete an orbit. But in many galaxies, stars on the outside are orbiting at almost the same rate as those in the core.
It's almost like a phonograph record. Every part of that record spins around like a solid disk. The stars are going too fast to stay bound to the gravity of the galaxy. They should just fly right off into space.
Physicists come up with an explanation. Galaxies sit in a giant halo or ball of invisible dark matter. And it's that extra mass that allows the stars to turn fast all the way out to the galactic rim.
Think about actually taking a disk of dough and spinning it to make a pizza. The more you spin it, the more those outer regions go farther and farther away.
Eventually, the dough just goes flying everywhere. That's what would happen to a galaxy if it weren't for dark matter. But as you spin pizza dough and you spin it faster and faster, it does hold itself together because there's all this yummy gluten that's acting as a glue. Dark matter is the gluten of our universe.
By calculating the mass needed to bind those speeding outer stars to the galaxy, physicists are able to estimate how much visible matter there is compared to dark matter. The results are staggering.
All the stuff we thought existed was just maybe 15% of our universe. That's like if you go to a restaurant and realize that the measly 15% tip, you know, that's all we are. We're not even the majority substance.
We may not be able to see it, but dark matter makes up some 85% of all matter. Wherever we look, we can see its gravity having effects. It glues galaxies like our Milky Way together. And a close look reveals dark matter can also bend light itself. It's called gravitational lensing.
If you look out all over the night sky with very powerful telescopes, you will occasionally see things that you weren't expecting to see.
It's amazing to see these distorted, elongated, twisty, snaking shapes in a galaxy. You're like, what in the world is that?
Take the example of galaxy cluster Able 370. Smears of light appear to reveal the existence of some cosmic flying reptile.
It might look like a dragon winding its way through a galaxy, but it's not an actual dragon. Just not an actual dragon.
Scientists are pretty sure that Able 370 does not contain a fire-breathing monster. The dragon is a galaxy that appears twisted out of shape.
When you see light stretched out like that, you might think, oh, it's a galaxy, something's hit it and punched it and stretched it out. That's not what's going on here. Instead, the galaxy is actually normal, but the path that light has taken to get to our eyes has been bent out to create these crazy shapes.
And massive object can bend space and time, and light must follow the curves of that space and time.
Gigantic clumps of any matter create a gravitational lens. Dark matter showed its space warping power in a trick it played with a gigantic explosion in a far-off galaxy cluster. Supernova Repsol was first detected in November of 2014.
Supernova Repsol is actually one of my favorite recent results in all of the astronomical literature. That result blew me away.
So a star explodes. Light is emitted in all directions, and some of it makes its way towards the Earth. So far, so good. This is very standard.
So the flash appears, and then another flash appears.
We see it again, and again, and again.
We see the explosion go off in 4 parts of the sky, and then a year later, a 5th explosion goes off in a totally different part of the sky.
What's going on?
Analysis proves that these multiple explosions are the same supernova. But between this one dying star and our telescopes sits a giant mass of dark matter, a huge gravitational lens.
What that means is that some of these rays of light will take much longer, more complicated paths through this region of space-time.
The dark matter lens turns one supernova into a fireworks display, lasting an entire year.
Dark matter affected the trajectory of light from the supernova so much that for some of those trajectories, it added a whole light year. It took a whole extra year for light to reach us.
Something is very definitely out there, distorting our view of the cosmos. It's a potent clue that dark matter is real. Now, new evidence suggests that without it, we might not exist at all. The cosmos is filled with an unseen substance. Its mass even bends starlight. Gravitational lensing suggests dark matter holds our entire universe together. For decades, this specter of space has haunted us. We've never been able to pin it down. In 2021, an international team ran a virtual experiment to try to predict where dark matter should be by letting computers map out where we think it lives.
Because we think we know how it behaves, we can model what it should be doing in supercomputer simulations.
The team taught the computer how dark matter bends light, then applied computational power to 17,000 unexplored galaxies. The model created a dark matter map.
I think a lot of people, when they imagine the universe on the largest scales, think it's sort of boring, everything's uniform. But that's not what we see.
What's amazing is that on the larger scales of the universe, we see a very particular pattern.
When we zoom out, we see this magnificent structure, this cosmic web that's created by dark matter.
The interweaving tendrils of dark matter stretch for thousands of light years across the cosmos. At the junctions, where matter is concentrated, we find galaxies form, illuminating the dark scaffold. If dark matter exists, scientists believe it makes up 85% of the matter in the universe and also controls the remaining 15%. Regular matter, like stars, planets, us. If they're right, dark matter played a critical role in actually building the universe we see today. 2021. Astronomers using the Sky Mapper Observatory in Australia trained specialist optics on a dwarf galaxy called Tucana 2. The Sky Mapper's filters split up the starlight into a spectrum of wavelengths, revealing some very ancient light.
One of the best clocks that we can put on the universe is the progress of chemistry, right? The buildup of more complex elements over time. Stars are nothing if not factories of chemical complexity. They slam particles together and create heavier elements, right, through a process called fusion. The later the generation of star, the more chemically complex it is.
Tucana 2's spectral signature reveals its stars contain very few of these heavy, complex elements. A clue that lets astrophysicists calculate the age of the galaxy.
These are very, very old stars from the very early days of the universe when the gas in the universe was not that chemically complex. Tucana 2 might be one of the oldest known structures that we can see in our local universe. It could be as old as 13 billion years, almost as old as the universe itself.
This grand old lady of a galaxy is a tiny thing, barely 3,000 stars. And yet, way out on her galactic rim, stars hurtle around at breakneck speed.
When you look at the mass of this ultra-faint dwarf galaxy, it only has a few thousand times the mass of the sun. That's really small. And at the speed it's moving, it should fly apart.
Tucana 2 doesn't break up because it's glued together, apparently by an incredible amount of dark matter.
When you look at a galaxy like our Milky Way, it's about 85% dark matter, which is a lot. But with Tucana 2, it's more like 99%.
Tucana 2 is old, among the oldest galaxies in the universe, and it is packed full of dark matter. Simulations suggest this dark matter played a key role in shaping Tucana 2 and other very early galaxies right from the beginning, gathering regular matter into clumps and building the first galaxies.
The importance of dark matter really can't be overstated. It has actually controlled the way matter has evolved since the beginning of the universe. It brings matter together. You need this underlying structure of dark matter to make it all happen.
Scientists think that for billions of years, as the early universe grew, dark matter called the shots. Without its gravity, structures like the Milky Way wouldn't have formed. We've seen dark matter's light-bending effects. We've even deduced where it should be. Dark matter really does appear to exist. But this evidence is indirect, circumstantial. To get conclusive proof that dark matter exists, don't we need to find some?
If we could find a lump of dark matter, that would be one of the greatest discoveries in all of nature, in all of our history, right? Because we would understand one of the most fundamental components for how our universe works. Drop in the title, they love that.
It's time to hunt for dark matter itself. Could it be hiding in the darkest place of all? Black holes. Scientists believe an invisible substance is pulling the strings in our universe. But until we see it, sense it, perhaps even touch it, dark matter is just a theory. Sometimes, though, ideas dreamed up by scientists come true. Like black holes. Once the stuff of science fiction and children's nightmares, black holes today are confirmed reality.
So black holes and dark matter have a ton of similarities, right? You know, an unseen collection of matter that creates an enormous gravitational field. Check.
It bends light and causes gravitational lensing. Check.
Test the boundaries of known physics. Check.
It seems crazy to even ask, but could our search for dark matter end in an idea more than 100 years old? Could dark matter be black holes? Black holes appear when stars explode, and their remaining mass crunches down into a sphere so dense even light can't escape its gravity. But that's where the black hole dark matter theory stumbles.
We know that black holes happen, we know how they form, and we also know that there's nowhere near enough of them to be dark matter.
Not enough stars have lived and died in the history of the universe to create 85% of the matter in it. If dark matter is made up of black holes, they would have to be an entirely new type.
It's possible that these black holes are of a type that we've never seen before. They could be primordial black holes.
Primordial black holes are an idea, a theoretical concept at this point that we've never seen, but they could exist.
If primordial black holes are real, then the universe is flooded with black holes.
The smallest could have the mass of Mount Everest packed into the size of one atom. The biggest could be hundreds of thousands or millions of times the mass of the sun.
Stephen Hawking first suggested that primordial black holes could be dark matter back in the 1970s. The idea centers on what happened during that intangible moment 13.8 billion years ago, the Big Bang.
Theory says that primordial black holes formed in the first fraction of a second of the early universe. It's that time between when the universe goes from a pinprick to this giant inflating ball of gas.
In these first moments of the universe's existence, matter is packed incredibly tightly, but it's not quite evenly spread. Even the tiniest fluctuations in density could trigger gravitational collapses. In other words, black holes would be forming everywhere. Theoretically, in huge numbers.
By the time 1 second has passed in our universe, you're already making black holes thousands, hundreds of thousands of times more massive than our sun.
The collective mass of these objects could be vast, but could they be 85% of the universe's matter?
If primordial black holes really do exist, there might be enough to explain the dark matter.
It's a tantalizing possibility, but there's one pretty big problem. For most scientists, the physics of the very early universe is incomplete and hard to trust. Generations of physicists dismissed primordial black holes as myths, fantasies, astrophysical unicorns, until that is, an earth-shaking crash in space. May 2019. A violent cosmic event rocks the USA. How violent? Well, The physical distance between Louisiana and Washington State is stretched by nearly the width of an atom, which is bigger than it sounds. The Laser Interferometer Gravitational Wave Observatory detects this wobble in space-time.
This is the biggest gravitational wave event that LIGO has seen.
This cosmic disturbance seems to come from colliding black holes, but crucially, not the ordinary dead star type.
In this LIGO detection, one of the black holes is 85 solar masses. There's no way that a star could have made that black hole.
Physicists believe there's a range of masses where dying stars can't collapse into black holes. Instead, stars in this zone become insanely hot and rip themselves apart, leaving nothing to crunch down into a black hole. 85 solar masses sits right in the middle of this so-called forbidden mass range. The black hole that LIGO detected can't be a dead star, but in theory, it could be primordial. Could this discarded theory of dark matter be back in fashion?
The LIGO detections come up and everyone says, oh, right, primordial black holes. Maybe we should pay more attention to that.
Primordial black holes can be really appealing because they would solve the dark matter problem. But unfortunately, it's not that simple.
The thing with flooding the universe with primordial black holes is that you expect a lot of collisions. And so LIGO shouldn't have seen one, it should have seen 1,000 of these collisions, and we don't.
Many scientists doubt what LIGO saw was a primordial black hole. To them, these beasts remain fairy tales of physics, red herrings in the quest for solid evidence of dark matter. Does dark matter exist, or are we chasing shadows? Some scientists think it's not only real, but that dark matter is within our grasp, and that it's flying through our bodies right now. We think 85% of the universe's matter is dark. And yet, we've never found a speck of it. We can't prove dark matter exists. Regular matter is made up of everyday particles, like electrons and protons. Scientists wonder if dark matter is also a type of particle.
One of the leading candidates for dark matter are these things called weakly interacting massive particles.
They're massive particles, like protons and electrons and things like that, but they don't interact well with normal matter, so they're weakly interacting.
And they just have this name because it's awesome to call them WIMPs.
For decades, scientists have struggled to find these shy, theoretical particles.
The very first physics research I ever did in my life was about actually measuring directly dark matter particles, these so-called WIMPs. And if they exist, then there will be a flux of millions of them through my hand right now just by holding it out right here.
If dark matter is actually made of WIMPs, if these particles exist, then we're actually living basically in a sea of them. It surrounds and penetrates us, and it binds the galaxy together.
WIMPs don't play by our rules. They barely interact with the world of regular matter, so they're hard to detect. But when they play with each other, sparks fly. Intense flashes that we just might be able to see.
As the theory goes, WIMPs will self-annihilate. If WIMP A and WIMP B get too close together, poof, they explode and they create gamma rays.
Gamma rays are high-energy light, making them easy to spot. Scientists point their detectors at the center of the Milky Way, where they believe the WIMP collision rate should be especially high.
We have a 4 million solar mass black hole there. There are billions of stars there. That's where most of the mass of the galaxy is densest. So any WIMPs orbiting the galaxy will feel this natural attraction towards the center and fall toward it.
The Fermi Large Area Telescope scoured the center of our galaxy for more than 10 years. It detected lots of gamma rays, but scientists couldn't tell if they came from colliding WIMPs.
The galactic center is a mess. It's like downtown of a city, right? That's where everything is, where all the hustle and bustle is. There are stars exploding there, just tons of stars, gas, magnetic fields, a black hole, a lot of sources of gamma rays, so it's very difficult to tease out the signal.
Downtown Milky Way was a washout. So the scientists turned their attention to planets living in less noisy zip codes, where WIMP collisions should be easier to spot.
One place where we might see evidence for WIMP collisions is actually the cores of exoplanets.
Turns out exoplanets might be the best dark matter detector we have.
You can use giant planets orbiting distant stars as laboratories to understand dark matter.
We know gravity should attract WIMPs. The more gravity, the more dark matter particles come together. Scientists suggest that WIMPs congregate inside the cores of the Milky Way's largest gas planets. In these supersized gas giants, WIMPs could collide, annihilate, and release gamma rays. In these supersized gas giants, WIMPs could collide, annihilate, and release gamma rays.
If there are these WIMPs that are collecting in the centers of massive exoplanets, the annihilation of that dark matter can heat those exoplanets up.
If you have a WIMP-heated exoplanet, and that's just fun to say, this thing is going to be warm. It's going to be warmer than the heat of space, which is very cold. So what you need is an infrared telescope, something that sees an infrared light and is sensitive enough to be able to measure the temperatures of these things.
But a dedicated telescope like this won't launch until 2028. For some dark matter hunters, that's too long to wait. They argue that WIMPs do have one characteristic that should allow us to detect them right here on Earth.
The key to detecting WIMPs is in their name. It's the WI. They're weakly interacting. They're not interacting. They do interact. It's just very weak with matter. And that means that there are the rare occasions where it will smack into a particle of normal matter, and then there are effects that we can observe.
Scientists in Gran Sasso in central Italy watch for a spark of energy generated when a WIMP hits an atom of regular matter. Their detector, a tank of supercooled xenon built thousands of feet beneath the Earth's surface.
The beauty of putting this detector under a mountain is that you've got all of this rock and soil and everything else, which is blocking a lot of background noise.
When you're looking for a WIMP interaction, you're looking for something that's very rare and something very subtle. So you don't want other things going on. You don't want other particles coming in and messing up your experiment.
These weakly interacting massive particles will pass right through that mountain. And then if they smack into a xenon atom, we can look at it and go, ah, that was a dark matter particle.
Detecting a WIMP could be definitive proof that dark matter exists. In 2020, the scientists spotted something in the results. But was it the elusive evidence or a ghost among the stars? Scientists believe they can prove dark matter is real by detecting WIMPs. An experiment buried deep beneath an Italian mountain spotted unusual activity in a tank of regular matter, pure liquid xenon.
So a WIMP detector, like the Xenon 1T, waits for a little WIMP, tiny, tiny little particle, to hit an atom of normal matter. And that creates a vibration. And we can see this entire block of xenon shake just a little bit from that little subatomic collision.
The intensity of the vibration from the particle collision is critical. In theory, a WIMP striking a xenon atom should generate a powerful shock. The vibrations Xenon 1T detected were too weak.
When a WIMP comes through, it smashes into the atom. It seemed like here something was just sort of rattling the electrons in the outside of the atom. So whatever is causing these detections was likely something much smaller than a WIMP.
Let's take these results at face value. If they're correct, it's telling us that the dark matter isn't a WIMP, but something much, much smaller and something much, much lighter.
The results suggest that what hit the xenon was actually a much smaller theoretical particle called an axion.
Axions are really weird particles, incredibly light. In fact, almost zero mass is possible for an axion.
An axion is no bigger than 150 billionth the size of an electron. Compared to a WIMP, an axion is like a soccer ball compared to our sun.
The sheer tininess of axions makes them seem like an unlikely candidate for dark matter. If dark matter is real, it makes up 85% of the matter in the universe. To account for all that mass, we would need an almost unfathomable number of axions. 140 trillion of them, in fact. That's 140 with 93 zeros after it. If axions exist, space must be swimming with them. They must be packed into every corner of the cosmos. When regular matter clumps together, it forms stars. So, to prove dark matter exists, maybe we should be looking for dark stars. There's no reason they can't exist. There's even a name for them. Ghost stars.
They're very weird objects. These ghost stars are like nothing we would ever see in the night sky.
We've never seen a ghost star. They are theoretical objects made of hypothetical axions. But, in theory, ghost stars should form like any other star, pulled together by gravity. They would be gigantic, super dense objects floating through space. They could reach the mass of tens of millions of suns. But because they are made of dark matter, ghost stars would produce no energy and emit no light. They would be transparent to both light and matter.
If you were right next to it, you wouldn't even notice it, right? If we sent a probe through it, it'd sail right through it. And once it passed through, it would be pulled back by its gravity.
85% of the matter in our universe could consist of transparent orbs made of infinitesimally small dark matter particles. But do these invisible stars exist? The evidence is thin, but. Rewind back to that LIGO detection in 2019. The gravitational wave detector picked up the signal of two massive objects colliding. We call the event GW 190521. Most scientists agree this was a black hole collision. But could it have been clashing ghost stars?
If there are ghost stars out there and they can interact with each other gravitationally, they may collide. And when they do, they would emit gravitational waves, and it would look a lot like two black holes colliding. In fact, it would look, theoretically, very much like GW 190521.
One collision, two explanations. Primordial black holes or ghost stars. LIGO can't tell them apart. Do these ideas bring us closer to proving the existence of dark matter? Or are we just hurtling further down a weird physics rabbit hole?
Primordial black holes, ghost stars, axions. This is all very exotic physics. We can't take for granted that any of this is real or that it's not real. We just don't know.
Dark matter is irritating. Oh, we know it's out there. We see its effects, right? But we can't see the dark matter. And that's frustrating. And it's like a lot of young fields in astronomy. We have way more ideas than we do hard observations.
We have ideas, we have theories, but without direct observations, we just can't back them up with solid proof. The more we look, the harder it is to find dark matter. Maybe it's primordial black holes from the early universe. Maybe it's a sea of particles that flow right through us every day. Or maybe it's gigantic, transparent ghost stars. Perhaps it's the combined mass of Santa's sleigh and the Easter Bunny's basket. Or maybe all our physics is based on questionable math. "85% of the stuff in the universe is missing in action. The search for this dark matter looks hopeless."
This problem of dark matter is really a tough one. Everything that we've predicted and then gone and looked for, we're not finding it.
It's starting to become a huge embarrassment. Surely something so fundamental to our cosmology should be detectable, and yet it remains elusive.
We're stumbling blindly around the limits of our understanding. As of right now, there are 0 direct observations. Maybe dark matter doesn't exist after all. Instead of searching for an invisible substance affecting the universe with its gravity, maybe it's gravity we don't quite understand.
If you're looking at a galaxy and it's spinning way too quickly, either there's a new ingredient in the galaxy like dark matter that holds it all together, or you're misunderstanding the laws of physics.
To describe the effects of gravity, we use the nearly 350-year-old math of Sir Isaac Newton. Maybe, to explain the excess gravity we see in the universe, it's not extra matter we need, it's better math.
Although we understand very well how gravity works here on Earth and in our solar system, perhaps when you get up to galactic scales, it actually behaves just slightly differently. And if that were the case, you can kind of tweak that idea until it fits the data we see of how galaxies are spinning around without needing dark matter.
Questioning the math of a legend of physics might sound like sacrilege, but to solve the dark matter conundrum, it has been done. It's called Modified Newtonian Dynamics, or MOND. Modeling galaxies with this math produces very different results.
On its surface, MOND is not a bad idea.
In the same way that we would normally program a computer to include dark matter in our simulations, you can take that out and instead program it with a different law of gravity, with MOND. And then you can set up a kind of spinning mass of gas, and it does seem to be possible with MOND to get things that settle down and look a bit like a real galaxy.
Changing the law of gravity accurately recreates the superfast spin astronomers see through their telescopes. No need for dark matter. It doesn't exist. Case closed? Not by a long shot. With anything bigger than a galaxy, this artificial physics breaks down.
MOND does really well on galaxy scales, but when you zoom out and you go to larger and larger structures on our universe, like clusters of galaxies and big structure, you see that MOND by itself can't reproduce all our observations. There's something missing.
Dark matter.
Dark matter, dark matter, dark matter.
Dark matter.
In MOND, you still have to invoke the existence of material you can't see.
It basically introduces some of its own dark matter as well, which kind of negates the point of having MOND in the first place.
MOND doesn't replace dark matter. The universe still needs something to hold it together. We just don't know what it is. But there are plenty of new ideas flying around.
In my theory, the dark matter is a superfluid.
It's a radical new theory of dark matter. Particles, not acting individually, but flowing as one invisible mass around the galaxies.
A superfluid is like an ordinary fluid that flows, but in this case, it flows without any resistance or viscosity. If I pour honey, it will...
As the superfluid dark matter flows around the universe, eddies and waves form, large enough to engulf entire galaxies. The gravity of the fluid holds the stars together. But, like most theories on dark matter, there's no direct evidence.
If these waves are on the size of galaxies, then we have to find detectors that can detect those types of huge waves. They don't exist at the moment.
Which brings us back to square one. We just can't prove that dark matter is real. Primordial black holes, ghost stars, WIMPs, a superfluid sloshing about the cosmos, or maybe we're just using the wrong math. What's your money on?
If I had to wager $20 on what dark matter is,
I would never place money on what dark matter is. I just think we have no idea.
My money is on dark matter itself is real, but it's not the whole picture.
I would say left socks in dryers. I would say remote controls that fall into sofa cushions and disappear.
I would love there to be dark matter ghost stars, planets, even dark matter people.
I'm going all black. I think no current ideas are correct. I think dark matter is something that we haven't thought of yet.
Does dark matter exist? Watch this space.
Some of which are now obscure white dwarfs on the opposite side of the Milky Way galaxy. This process cooked up all of the elements that make up Earth. The interiors of stars that were in the process of collapsing were the source of the nitrogen that is in our DNA, the calcium that is in our teeth, the iron that is in our blood, and the carbon that is in our apple pies. We are composed of the stuff of the stars. The supernova's explosion can produce some of the universe's most exotic elements. As a result of the numerous supernova explosions that took place just before the solar system formed, the Earth contains a relatively abundant supply of gold and uranium. Other planetary systems may have different concentrations of these extremely rare elements. Is it possible that there are worlds whose inhabitants wear niobium pendants and protactinium bracelets with pride but consider gold nothing more than a laboratory curiosity? If gold and uranium were as rare and unimportant on Earth as praseodymium, would our quality of life be better? The beginning and development of life are most closely related to the birth and growth of the universe's first stars and galaxies. To begin, the very matter of which we are composed, the atoms that make it possible for there to be life, were generated in giant red stars a very long time ago and very far away. There is little room for doubt that red giants and supernovae are the furnaces and crucibles in which matter was forged, because the relative abundance of the chemical elements in the cosmos matches the relative abundance of the atoms generated in stars. The Sun is a star that belongs to the second or third generation. All of the matter in it and the matter around you has been through at least 1 or 2 cycles of stellar alchemy in the past. Second, the discovery of specific types of heavy atoms on Earth proves that an enormous supernova exploded in the neighborhood before the Sun, planets, and other solar system components came into existence. However, it is highly unlikely that this is merely a coincidence. It is more likely that the shock wave produced by the supernova compressed interstellar gas and dust, which in turn triggered the condensation that led to the solar system's formation. Third, when the Sun began to shine, its ultraviolet radiation poured into the Earth's atmosphere, and its surface's warmth caused lightning to form. These different energy sources served as the spark that ignited the complex organic molecules that eventually led to the beginning of life. Fourth, almost all of the energy that sustains life on Earth comes from the Sun. Plants are responsible for absorbing photons and transforming them into chemical energy. The plants are parasitized by the animals. Methodically harvesting sunlight through the use of plants as reluctant intermediaries constitutes farming. Solar energy provides the majority of our power. Last but not least, the hereditary shifts known as mutations provide the essential building blocks for evolution. Cosmic rays are high-energy particles ejected almost at the speed of light in supernova explosions. These particles contribute to the production of mutations, which nature then uses to select its new inventory of life forms. The spectacular demise of ancient, extremely massive suns is one of the driving forces behind the development of life on Earth. Imagine going to some location very deep within the Earth, such as a gold mine or a lava tube with a Geiger counter and a piece of uranium ore in your possession. A lava tube is a cave carved through the Earth by a river of molten rock. The sensitive counter clicks when subjected to gamma rays or high-energy charged particles like protons and helium nuclei. The count rate and the number of clicks per minute significantly increase when we place it close to the uranium ore undergoing spontaneous nuclear decay and emitting helium nuclei. The count rate drops significantly after the uranium ore is placed inside a heavy canister made of lead because the lead has taken in the radiation from the uranium. However, there are still some clicks that can be heard. A portion of the counts that are left is overcome by the natural radioactivity that is present in the cave walls. However, there are more clicks than can be explained by the radioactivity. Some are brought on by high-energy charged particles that have broken through the roof. We are currently listening to cosmic rays created in a previous era, deep within the reaches of space. For the entirety of our planet's existence, it has been pounded by cosmic rays, most of which are composed of electrons and protons. In a galaxy thousands of light-years away, a star annihilates itself, producing cosmic rays that spiral through the Milky Way galaxy for millions of years, until, quite by accident, some of them strike the Earth and our genetic material. These cosmic rays are thought to have played a role in the evolution of life on Earth. It's possible that cosmic rays were responsible for the initial stages of the development of the genetic code, the Cambrian explosion, or the evolution of our ancestors into bipedal stature. A guest star was discovered by Chinese astronomers on July 4, 1054, within the constellation of Taurus, also known as the Bull. A star that had never been seen before became more brilliant than any other star in the sky. In the American Southwest, halfway around the world, there is a high culture abundant in astronomical knowledge. The traditions of the past witnessed this dazzling new star. We know that in the middle of the 11th century, some Anasazi, the ancestors of the Hopi of today, lived under an overhanging ledge in New Mexico because carbon-14 dating of the remains of a charcoal fire revealed this fact. One apparently drew a picture of the new star on the cliff overhang, where it would have been protected from the elements. Its location concerning the waning crescent moon would have been the same as depicted. In addition, there is a handprint, which may be the artist's signature. An astronomer centuries later had the uncanny experience of being reminded of a crab when looking at the explosion remnants through his telescope. This remarkable star is located 5,000 light-years away and is now known as the Crab supernova. The Crab Nebula is all left of a massive star that went supernova millions of years ago. On Earth, the explosion could be seen with the naked eye for 3 months. Even though it was easy to see during the day, you could read it at night. In any given galaxy, there will be a supernova approximately once every century on average. A typical galaxy will live for about 10 billion years when 100 million stars have blown themselves apart. This is a significant number, but it still accounts for only about 1 star in 1,000. Tycho Brahe observed and described a supernova in the Milky Way in 1572, following the event in 1054. Shortly after that, in 1604, Johannes Kepler described another supernova in the Milky Way. Astronomers have been chomping at the bit for centuries, but unfortunately no supernova explosions have been observed in our galaxy since the invention of the telescope. This has caused them much frustration. It is now common practice to spot supernovae in galaxies other than ours. The following passage from a paper written by David Helfand and Knox Long and published in the issue of the British journal Nature dated December 6, 1979, is one of my candidates for the sentence that would most thoroughly astound an astronomer working in the early 1900s. On 5th of March 1979, an extremely intense burst of hard X-rays and gamma rays was recorded by the 9 interplanetary spacecraft of the Burst Sensor Network and localized by time-of-flight determinations too. There is also, contrary to what you might anticipate, a relatively insignificant Magellanic Cloud. On the other hand, E.P. Mazets and colleagues from the IOFA Institute in Leningrad, who observed this source with the gamma-ray burst detector aboard the Venera 11 and 12 spacecraft while they were traveling to Venus, argue that what is being observed is a flaring pulsar that is only a few hundred light-years away. Their findings were published in the same issue of Nature, but Helfand and Long do not insist that the gamma-ray outburst is associated with the supernova remnant, even though their positions are very similar. They carefully consider a wide range of possibilities, including the possibility that the origin is somewhere within the solar system. It could be the byproduct of an extraterrestrial starship's long journey back to its home planet. The rekindling of the stellar fires in N49 points to a more straightforward explanation. We are certain that supernovae are real phenomena. The future of the inner solar system is not looking good as the Sun continues to evolve into a red giant. On the other hand, there is no danger of a supernova exploding and turning the planets into a molten mess. This calamity befalls planets that orbit stars that are significantly more massive than the Sun. The lifetimes of stars with higher temperatures and pressures than the Sun are significantly shorter due to the rapid depletion of their stores of nuclear fuel. The Sun's lifetime is approximately 93 billion years. It only takes a few million years for a star with tens of times the Sun's mass to convert hydrogen into helium in a stable manner, before the star shifts its focus to nuclear reactions that are more unusual. Therefore, there is almost certainly not enough time for the evolution of advanced life forms on any of the accompanying planets, and it will be extremely unlikely that beings elsewhere will ever be able to know that their star will become a supernova. If people survive long enough to learn about supernova, it is highly unlikely that their star will ever explode. The formation of a massive iron core through the fusion of silicon is an essential step that must take place before a supernova can occur. The equal and opposite electrical charges cancel each other out, transforming the star's interior into a single giant atomic nucleus, which occupies a much smaller volume than the precursor electrons and iron nuclei. This process takes place under enormous pressure and results in the free electrons in the stellar interior being forcibly melded with the protons of the iron nuclei. A violent implosion occurs at the core, followed by a rebound of the exterior, leading to an explosion known as a supernova. A supernova can emit more light than the total radiance of all of the other stars in the part of the galaxy in which it is located. Those recently hatched massive blue-white supergiant stars in Orion are on track to become supernovae within the next few million years, continuing the cosmic fireworks in the Hunter constellation. The incredible supernova explosion causes the majority of the matter from the precursor star to be propelled into space. This includes trace amounts of hydrogen-helium and significant quantities of other atoms, such as carbon, silicon, iron, and uranium. The remnants consist of a core of hot neutrons that are held together by nuclear forces, a single massive atomic nucleus with an atomic weight of approximately 1056, a sun that is 30 kilometers across, a tiny, shrunken, dense, withered stellar fragment, and a rapidly rotating neutron star. The core of a massive red giant collapsing to form a neutron star spins faster as it does so. The neutron star at the heart of the Crab Nebula is an enormous atomic nucleus that spins 30 times per second and is roughly the size of Manhattan. Its robust magnetic field, amplified during the collapse, captures charged particles to a greater extent than Jupiter's much more modest magnetic field. Electrons circulating in a rotating magnetic field give off beam radiation that can be detected at radio frequencies and in visible light. If the Earth happens to be in the path of the light from this cosmic lighthouse, then we will see it blink once for every rotation. Because of this characteristic, astronomers refer to it as a pulsar. Pulsars, which flash and tick like a cosmic metronome, keep time significantly more accurately than even the most accurate standard clock. The timing of the radio pulse rate over a longer period for some pulsars, such as PSR 00329 plus 54, suggests that these objects may have one or more small planets as companions. A planet can survive the transformation of a star into a pulsar, and it is also possible that a planet could be snatched up later. I can't help but imagine what the sky would look like if I were standing on such a planet. Neutron star matter weighs about the same as an average mountain per teaspoonful. Because of this, if you were to take a small amount of neutron star matter and let it go, which would be nearly impossible, it could pass through the Earth as easily as a falling stone through air, carving a hole for itself completely through our planet and emerging out the other side, possibly in China. People who live there might be going about their day-to-day activities when all of a sudden a neutron star the size of a pebble emerges from the ground, floats in the air for a short while, and then sinks back down into the ground, providing at least a momentary distraction from the monotony of the day. If a piece of neutron star matter were to be dropped from nearby space while the Earth was rotating beneath it as it fell, it would repeatedly plunge through the rotating Earth, punching hundreds of thousands of holes before the motion was stopped by friction with our planet's interior. Before it comes to rest at the Earth's center, our planet's interior may momentarily resemble Swiss cheese. However, the subterranean flow of rock and metal will heal the wounds as it moves towards the planet's center. It is probably for the best that large chunks of neutron star matter have never been discovered on Earth. On the other hand, there are numerous bumps present. The formidable force of the neutron star is latent in the nucleus of each atom. It is concealed in every teacup and dormouse, as well as every breath of air and apple pie. The neutron star instills an appreciation for the unremarkable aspects of life. As we have seen, a star with the same lifespan as the Sun will end its days as a red giant and then a white dwarf. A star with twice the Sun's mass on the verge of collapse will transform into a supernova and a neutron star. But a more massive star that is still around after its supernova phase will have an even more remarkable end in store for it. Its gravity will turn it into a black hole. This is because its mass will be 5 times that of the Sun. Imagine for a moment that we had access to a magic gravity machine, a tool that would allow us to manipulate the planet's gravitational pull at the turn of a dial. At first, the dial is positioned at 1G, and everything acts in the manner that we have come to be accustomed to anticipating. All of the living things on Earth, including plants and animals, as well as the architecture of our buildings, have either evolved to or been designed for BMG. If gravity were significantly weaker, there might be tall, spindly shapes that would not be thrown over or crushed by the weight of their own bodies. If the force of gravity were significantly higher, all living things, including plants, animals, and buildings, would need to be compact, stocky, and strong to avoid toppling over. But light would still travel in a straight line even in an environment with a fairly strong gravity field, just as in everyday life. Imagine a typical gathering of people from Earth attending the tea party described in Alice in Wonderland. As gravity is reduced, the weight of objects drops. When they get close to 0 GA, even the slightest movement causes our friends to float and tumble up into the air. Tea or any other liquid, when spilt into the air, will form pulsating spheres because the surface tension of the liquid will overcome the force of gravity. There are tea balls scattered all over. The tea maker will start working if we give the number 1G another try. Everyone becomes immobile when we slightly increase the gravity, from 1G to 3 or 4 Gs, because even moving a pore requires significant effort in this environment. Before we continue to dial in higher gravities, we remove our friends from the territory controlled by the gravity machine. The light emanating from a lantern moves in the same manner when subjected to accelerations of a few Gs as it does when subjected to accelerations of 0 G. At 1000 Gs, the beam is still straight, but trees have become squashed and flattened. At 100,000 Gs, rocks are crushed by their own weight because of the force exerted by the beam. Ultimately, nothing is left alive except for the Cheshire Cat, who was granted a miraculous exemption. Something even stranger takes place when the gravitational acceleration approaches 1 billion Gs. The direction in which the beam of light has been traveling, which has been directly upward into the sky until this point, is beginning to curve. Even light is perturbed when subjected to extremely high magnitude gravitational accelerations. If we strengthen gravity, the light will be drawn down to the ground closer to where we are. The cosmic Cheshire Cat has disappeared, leaving only its gravitational grin behind. When the gravity is high enough, nothing, not even light, can escape. There is nowhere to go. A location like this is referred to as a black hole. It is a cosmic Cheshire Cat, mysteriously indifferent to its surroundings and a complete enigma. When the black hole's mass density and gravitational pull reach a certain threshold, it evaporates and vanishes from our universe. Because no light can pass through it, we refer to it as black. Inside, things are attractively well lit because the light is kept down where it can't escape. Even though a black hole cannot be seen from the outside, the gravitational presence of a black hole can still be felt. If you are not paying attention while on an interstellar journey, you may be drawn into it irreversibly, and your body is stretched into an uncomfortably long and thin thread. In the unlikely event that you made the journey alive, however, the process of matter accumulating into a disk surrounding the black hole would be a sight to remember. Thermonuclear reactions occurring deep within the solar interior keep the sun's outer layers stable and put off the inevitable collapse of the sun's gravitational field for billions of years. The pressure exerted by the electrons that have been removed from white dwarf's nuclei is what keeps the star intact. Neutron stars can defy gravity due to the intense pressure caused by their neutrons. But no known force can prevent the implosion of an old star with a mass more than several times that of the Sun if it has been left behind after supernova explosions and other violent events. The star undergoes a remarkable contraction, spins, turns red, and finally vanishes. A star with 20 times the Sun's mass will eventually contract until it is the size of Greater Los Angeles. At this point, the crushing gravity will reach 1010 Gs, and the star will disappear from our universe after passing through a self-generated crack in the space-time continuum. In 1783, an English astronomer named John Mitchell conceived the concept of black holes. But because it was such an odd concept relatively recently, people paid more attention to it. Then, much to the surprise of many astronomers, evidence was discovered that pointed to the existence of black holes in space. The atmosphere of Earth blocks X-rays from reaching the surface. To determine whether or not astronomical objects emit light with such short wavelengths, it is necessary to lift an X-ray telescope into the air. The United States of America launched the first X-ray observatory into orbit from a launch pad located in the Indian Ocean off the coast of Kenya. This observatory was given the Swahili name Uhuru, meaning freedom. Uhuru discovered an extremely brilliant X-ray source in the constellation of Cygnus, also known as the Swan, in 1971. This source was found to be turning on and off 1,000 times every second. The origin, which we call Cygnus X1, is quite modest. Regardless of what caused the flicker, information about when to turn on and off can only travel across Cygnus X1 as fast as the speed of light, approximately 300,000 kilometers per second. Therefore, the maximum width of Cygnus X1 can be no more than 300 kilometers. Something on the order of the size of an asteroid shines as a brilliant source of X-rays that can be seen from interstellar distances. What is it trying to say? Cygnus X1 is located in the exact same region of the sky as a hot blue supergiant star. This star, which shines in visible light, reveals that it has a massively close but unseen companion that pulls it gravitationally in one direction at first, and then in the other. Cyg X1 is located in the exact same location. It is estimated that the mass of the companion is approximately 10 times that of the Sun. Identifying the companion inferred in visible light with the source detected in X-ray light is tempting because the supergiant is an unlikely source of X-rays. But this identification must be corrected. A black hole is the only possible explanation for an invisible object that weighs 10 times as much as the Sun and can be compressed into a volume no larger than an asteroid. The X-rays may be produced by friction in the disk of gas and dust that has accreted around Cygnus X1 due to its supergiant companion. The stars V861 Scorpii, GX3394, SS423 and Circinus X2 are all candidates for the role of black hole in their respective systems. The remnant of a supernova known as Cassiopeia A can be found in the constellation Cassiopeia. Its light should have arrived on Earth in the 17th century when there were a lot of astronomers. But the explosion was not reported by anyone. It is possible that, as I.S. Shklovsky hypothesized, a hidden black hole there consumed the exploding stellar core and put out the fires of the supernova. The shards and pieces of data that may be the spoor or the trail of the fabled black hole can be checked using space-based telescopes. These telescopes are how this can be accomplished. Consideration of the curvature of space can be of assistance in developing an understanding of black holes. Imagine a two-dimensional flat surface, flexible and lined like a piece of graph paper made of rubber. When we drop a relatively light object, the surface will deform and become puckered. The marble's motion around the pucker can be compared to the orbit of a planet around the Sun. Einstein is credited with providing us with this interpretation, which describes gravity as a distortion in the space fabric. Using this as an example, we can see how the presence of mass can distort space into a third dimension of the physical world. Imagine that we are located in a three-dimensional universe that is locally warped into a fourth physical dimension that we cannot perceive directly due to the presence of matter. The severity of the pucker, distortion, or warp in space increases in proportion to the magnitude of the local mass, which determines the strength of the local gravity. According to this illustration, a black hole is comparable to a bottomless pit. What exactly takes place if you go under? Because all of your mechanical and biological clocks would have stopped. Falling in would take infinite time when viewed from the outside. However, when viewed from your perspective, it would appear that all of your clocks are operating normally. If there was some way for you to survive the gravitational tides and the radiation flux, and if the black hole was rotating, which is a likely assumption, then it is possible that you could emerge in another part of space-time, somewhere else in space, some other time. Wormholes in space, similar to the ones found in apples, have been given serious consideration, even though their existence has not been established. Would it be possible for gravity tunnels to serve as an interstellar or intergalactic subway, making it possible for us to travel to previously inaccessible locations much more quickly than we could have done using more traditional methods? Are there any possibilities that black holes could act as time machines, taking us to the far past or future? The fact that ideas of this nature are being debated, even in a semi-serious manner, demonstrates how absurd the universe may be. In the most profound sense, we can be considered children of the universe. Please picture yourself standing in the middle of a cloudless summer day with your arms stretched before you and think about how dangerous it is to look directly at the sun. We can sense its power even from 93 million miles, 150 million kilometers. What sensations would we experience if we were to stand on its bubbling, self-illuminating surface or be submerged in its core of nuclear fire? The sun keeps us warm and enables us to eat and see. It brought forth life on Earth. Its might is incomprehensible to human experience. The dawn is greeted by the joyful chirping of various species of birds. Even single-celled organisms can navigate towards sources of light. Our ancestors were not naive, as evidenced by their worship of the sun. Despite this, the sun is a fairly average, even unremarkable star. Does it not make sense to revere the sun and the stars if we must worship a power greater than ourselves? An element of wonder can be found dormant within every astronomical investigation. In some cases, it is buried so deeply that the investigator is oblivious that it even exists. The galaxy is an uncharted continent teeming with strange beings of stellar dimensions waiting to be discovered. During our preliminary exploration, we came across some of the locals and took some of their measurements. A few of them are familiar to us in some ways. Others are strange in ways that surpass even our most unrestrained imaginations. But this is just the beginning of our investigation into the area. Discoveries made in the past have led researchers to believe that many of the galactic continent's most fascinating inhabitants are still undiscovered. Planets, globular clusters, and Magellanic clouds with stars in orbit around them are all almost certain to be found near the galaxy. The Milky Way is also in the vicinity. Such worlds would provide a breathtaking view of the Milky Way as it rose into view. The Milky Way is an enormous spiral form that is made up of 400 billion stellar inhabitants, collapsing gas clouds, condensing planetary systems, luminous supergiants, stable middle-aged stars, red giants, white dwarfs, planetary nebulae, novae, supernovae, neutron stars, and black holes. It would be obvious from such a world, just as it is starting to become obvious from our own, how the profound connection between life and the cosmos determines our matter and form and a significant portion of our personalities. To form a federation to fight the Lydians. Anaximander of Miletus was a friend and colleague of Thales, one of the first to conduct an experiment. Anaximander was also a prominent figure in ancient Greek philosophy. He accurately determined the length of the year and the seasons by observing the shifting shadow cast by a stick that was held vertically. Men have been using sticks to club and spear one another for a long time. Time was measured with one of these by Anaximander. He is credited with being the first person in Greece to construct a sundial, a map of the known world, and a celestial globe that displayed the patterns of the constellations. He believed that the sun, the moon, and the stars were made of fire and could be seen through moving holes in the sky's dome. This is an idea that is quite old. He held the remarkable view that the earth is not supported or suspended from the heavens, but rather remains at the center of the universe. He reasoned that since it was equidistant from all places on the celestial sphere, no force could move it. He believed that the earth was the center of the universe. He argued that we are so helpless when we are born, that if the first human infants had been put into the world on their own, they would have died as soon as they were exposed to the outside world. Anaximander concluded that humans evolved from other animals with newborns that were more capable of taking care of themselves. He hypothesized that life began by itself in the muck, and that fish covered in spines were the first animals to evolve. Some of these fishes' descendants eventually moved onto land, where they underwent the process of metamorphosis, changing from one form into another. This allowed them to evolve into other kinds of animals. He believed there were infinite worlds, all inhabited and gone through cycles of destruction and regeneration. Nor, St. Augustine lamented in a regretful tone, did he, any more than Thales, attribute the cause of all this ceaseless activity to a divine mind. In the year 540 BC or thereabouts, on the island of Samos, there came to power a tyrant named Polycrates. After working as a caterer for a while, he moved on to a career as an international pirate. The arts, sciences, and engineering fields benefited greatly from Polycrates' philanthropic support. But he oppressed his own people. He made war on his neighbors. He quite rightly feared invasion. As a result, he constructed a massive wall approximately 6 kilometers in length and encircled the city that served as the capital of his kingdom. He ordered a massive tunnel to transport water from a remote spring through the fortifications. It is 1 kilometer long, and it goes through a mountain. 2 cuttings, one dug from each end, eventually met in the middle and almost created a perfect circle. The fact that the undertaking was finished in only about 15 years is both a testimonial to the state of the art in civil engineering at the time and an indication of the extraordinary practical capability of the Ionians. But there is another, more ominous side to the enterprise. It was partly constructed by enslaved people in chains, many of whom were captured by the pirate ships of Polycrates. Those ships were responsible for the majority of the construction labor. It was during this time that Theodorus, the age's most accomplished engineer, was active. Among the Greeks, Theodorus was credited with creating the key, the ruler, the carpenter's square, the level, the lathe, bronze casting, and central heating. Why are there no memorials or statues dedicated to this man? Those who dreamed and conjectured about natural laws conversed with those who worked in technology and engineering. they frequently consisted of the same individuals. Both the theoretical and the practical aspects merged into one another. At the same time, Hippocrates established his renowned medical tradition on the neighboring island of Kos, which is now largely forgotten due to the Hippocratic Oath. Hippocrates insisted that the school of medicine he founded had to be based on the contemporary principles of physics and chemistry, so that it could be both useful and successful. However, there was also a theoretical component to it. Hippocrates wrote this in his book On Ancient Medicine. Men think epilepsy is divine, simply because they do not understand it. However, if they called everything divine, which they do not comprehend, why would there be no end to divine things? The Ionian influence and the experimental method eventually made their way to the mainland of Greece, Italy, and Sicily over time. At one point in history, very few people had faith in the existence of air. Naturally, they were aware of breathing and believed the wind was the divine wind that the gods breathed. On the other hand, the concept of air as a corporeal but imperceptible substance did not exist. The first experiment to be recorded while being conducted on air was carried out by a physician named Empedocles, who was active around 450 BC. According to a few versions of the story, he fancied himself to be a god, but people only regarded him as divine because he was so intelligent. He thought that the speed of light was extremely fast, but not infinitely fast. He taught that there had been a significantly greater variety of living things on Earth in the past, but that many different races of beings must have been unable to beget and continue their kind. Because of this, every species that has ever lived has been shielded from danger and kept alive thanks to its members' ingenuity, bravery, or swiftness from the beginning of their existence. Empedocles, along with Anaximander and Democritus, see below, clearly anticipated some aspects of Darwin's great idea of evolution by natural selection in his attempt to explain the lovely adaptation of organisms to their environments. Empedocles' attempt can be found in the following passage. The so-called clepsydra, known as the water thief, was a kitchen ladle used during Empedocles' experiment. It was a common household implement used by people for many years. A water-filled brazen sphere with a wide opening neck and numerous tiny holes in the base is presented here. When you pull it out while keeping the neck open, water creates a little shower by pouring out the holes in the bottle. However, if you pull it out properly, with your thumb covering the neck, the water will remain within the sphere until you lift your thumb. This will take place until you lift your thumb. Nothing will happen if you attempt to put something in it while the neck is covered. There must be something tangible in the path of the water. This kind of substance is invisible to our eyes. Is there any way to tell? Empedocles contended that the substance in question could only be air. If I were so foolish as to keep my finger on the neck, a force that we cannot see could exert pressure, making it impossible for me to fulfill my desire to fill a container with water. Empedocles had made a discovery that was previously unknown. He reasoned that for matter to exist in the form of air, it must be extremely finely divided and therefore invisible. It is said that Empedocles committed suicide by jumping into the molten lava that filled the summit caldera of the massive volcano Etna during an episode of apotheosis. But there are times when I like to think that he lost his footing amid a bold and innovative endeavor in observational geophysics. Democritus, who was born in the Ionian colony of Abdera in northern Greece, was the one who took this oblique suggestion, this whiff, of the existence of atoms and developed it significantly further. To some extent, Abdera was a town full of jokes. In the year 430 BC, if you told a story about someone from Abdera, you could count on getting a good laugh out of your audience. It was similar to Brooklyn in many ways during that era. Democritus believed that every aspect of life should be appreciated and comprehended, and that doing so was equivalent to having fun. He once said, "A life without festivity is like a long road without an inn." Democritus may have been born in Abdera, but that doesn't mean he was a fool. He believed that many worlds formed independently out of the diffuse matter found in space, developed, and eventually disappeared. At a time when no one knew about impact craters, Democritus believed that worlds occasionally collided. He also believed that some worlds wandered alone through the darkness of space, while others were accompanied by several suns and moons, that some worlds were inhabited, while others lacked plants, animals, or even water, and that the most basic forms of life emerged from a kind of primordial ooze. Democritus lived in a time when no one knew about impact craters. He taught that perception was a purely physical and mechanistic process, such as the reason, for example, that I think there is a pen in my hand, that thinking and feeling were attributes of matter put together in a sufficiently fine and complex way, and not due to some spirit that was infused into matter by the gods. And that perception was the reason, for example, that I think there is a pen in my hand. Democritus is credited with the invention of the word atom, which comes from the Greek for unable to be cut. Atoms were the most fundamental particles, and our efforts to disassemble them into smaller parts were ultimately fruitless. According to what he said, everything is just a complex collection of atoms put together, even us. Nothing exists, he asserted, but atoms and the void. When Democritus sliced an apple, he believed the knife had to travel through the empty spaces between the atoms. If there were no such things as empty spaces or voids, the apple could not be cut because the knife would run into atoms that were impossible to penetrate. Let's say we started by cutting a slice from a cone. Now, let's look at the difference in the cross-sections of the two pieces. Are there any differences in the exposed areas? Not at all, Democritus replied. Because of the cone's slope, one side of the slice will have a slightly less extensive cross-section. If the two areas were the same, we would not have a cone but rather a cylindrical shape. Regardless of how skilled the knife user is, the two pieces will always have different cross-sections. Why? Because when viewed on an extremely small scale, the texture of matter has an element of irreducible roughness. Democritus believed that the world of the atoms could be represented by a particularly fine scale of roughness. His arguments were not the same as those we use today. They were subtle, elegant, and derived from life in general. And the conclusions that he came to were basically accurate. In a separate thought experiment, Democritus considered the possibility of determining the volume of a cone or a pyramid by stacking a very large number of very small plates that gradually shrank in size from the base to the apex of the structure. He outlined the difficulty that can be found in the mathematical theory known as the theory of limits. He was on the verge of discovering differential and integral calculus, a fundamental tool for understanding the world that, as far as we can tell from written records, was discovered in the time of Isaac Newton. He was knocking on the door of differential and integral calculus. Calculus could have been invented by the time of Christ if Democritus's work had been almost entirely recovered. Long before astronomy reaped any benefit from the improved sciences of optics, he saw, as we may say, through the eye of reason, full as far into infinity as the most able astronomers in more advantageous times have done since. Thomas Wright marveled in 1750 about Democritus's belief that the Milky Way was made up primarily of unresolved stars. The mind of Democritus soared further and further away from the milk of Hera, and further still from the backbone of night. It would appear that Democritus was a rather peculiar individual. He placed a high value on friendship, thought that happiness should be the primary aim of one's life, and devoted a significant portion of his philosophical research to studying the roots and characteristics of enthusiasm. He traveled to Athens intending to pay Socrates a visit, but he needed to be more bold to introduce himself. Hippocrates counted him as one of his closest friends. He was in awe of the world because of its beauty and sophistication. He thought that being poor under a democratic government was preferable to being wealthy under an autocratic one. He thought that the dominant religions of his time were corrupt, and that there was no such thing as an immortal soul or God. Nothing exists but atoms and the void. It is unknown whether Democritus faced any consequences due to his opinions. However, he was from Abdera. However, during his period, the tradition of tolerating unconventional viewpoints deteriorated and broke apart. People began to suffer consequences for harboring strange beliefs. Democritus can now be depicted on Greece's 100 drachma note. However, his observations were disregarded, and his impact on history was negligible. The mystics were making progress towards victory. An Ionian experimentalist, Anaxagoras, flourished around 450 BC and resided in Athens during his lifetime. He was wealthy and apathetic towards his wealth, but had a strong interest in science. When asked what the point of life was, he responded with, "The investigation of the sun, the moon, and the heavens," which is the response that one would expect from a genuine astronomer. He carried out a deft experiment in which he demonstrated that adding a single drop of a white liquid, such as cream, to a large pitcher containing a dark liquid, such as wine, did not noticeably lighten the pitcher's contents. He concluded that there must be changes that can be deduced through experiments but are far too subtle to be directly perceived by the senses. Democritus was a much more revolutionary thinker than Anaxagoras was. Both of them were committed materialists, not in the sense that they placed a high value on possessions, but rather in the sense that they believed that matter alone was responsible for the structure of the world. Anaxagoras was a philosopher who disbelieved in the existence of atoms and held that there was a unique mental substance. He held the very Ionian belief that the presence of hands conferred a higher level of intelligence on humans than on other animals. He was the first person to state unequivocally that the moon shines as a result of reflected light, and as a result, he developed a theory regarding the phases of the moon. Because of the severity of the threat posed by this doctrine, its description had to be passed around as a covert document known as an Attic samizdat. Explaining the phases of the moon or eclipses using the relative geometry of the Earth, the moon, and the self-luminous sun at the time was unacceptable because it did not conform to the prevalent prejudices. Aristotle, who lived 2 generations later, was content to argue that those things occurred because it was the nature of the moon to have phases and eclipses. This explanation is nothing more than verbal juggling, and it explains nothing. The majority of people held the belief that the sun and the moon were deities. According to Anaxagoras, the sun and the stars were both made of fiery stones. Because of their great distance from us, we do not feel the heat that the stars produce. In addition, he believed that the moon possessed mountains and inhabitants, both of which were incorrect. According to his theory, the sun was so enormous that it was even bigger than the Peloponnesus, which occupies approximately the southwestern third of Greece. This estimate was considered excessive and ridiculous by his detractors. Anaxagoras was brought to Athens by Pericles, who was in charge of the city at the time of its greatest glory, but was also the person whose actions led to the Peloponnesian War, which was ultimately responsible for destroying Athenian democracy. Anaxagoras was considered to be one of Pericles' most trusted advisors. The two shared a passion for philosophy and science. Within this capacity, Anaxagoras made a significant contribution to the rise to greatness of Athens. However, Pericles encountered political challenges. Because he was too powerful to be attacked directly, his adversaries focused their attention on those close to him instead. Because Anaxagoras had taught that the moon was made of ordinary matter, that it was a place, and that the sun was a red-hot stone in the sky, he was found guilty of the religious crime of impiety and sentenced to imprisonment for it. This was because of his teachings. Bishop John Wilkins made the following observation regarding these people of Athens in the year 1638. Those zealous idolaters counted it a great blasphemy to make their god a stone, whereas notwithstanding they were so senseless in their adoration of idols as to make a stone their god. It appears that Pericles was responsible for Anaxagoras's release from prison, but unfortunately it was too late. The Ionian tradition persisted in Alexandrian Egypt 200 years later, even though the tide was turning in Greece at the time. It is common practice in history and philosophy books to refer to the great scientists from Thales to Democritus and Anaxagoras as presocratics. Their primary purpose was to maintain the philosophical status quo until the arrival of Socrates, Plato, and Aristotle, and perhaps to exert some influence on them. Instead, the ancient Ionians represent a distinct and, in many ways, contradictory tradition, albeit one that is significantly more in line with contemporary scientific understanding. Everyone who lived between the Ionian awakening and the Italian Renaissance suffered an irreparable loss because their influence was only strongly felt for 2 or 3 centuries. Pythagoras, a contemporary of Polycrates who lived in the 6th century BC, is considered the most influential person connected with Samos. Tradition has it that he was the first person in the history of the world to deduce that the Earth is a sphere. He is said to have lived in a cave on the Samian Mount Kirkis and was the first to do so. Maybe he made his point by drawing an analogy between the moon and the sun. Or maybe he saw the Earth's curved shadow on the moon during a lunar eclipse. Or maybe he noticed that when ships leave Samos and recede over the horizon, their masts vanish last. Pythagorean theorem was either found by him or his disciples. It states that the square of the longest side of a right triangle equals the sum of the squares of the shorter sides. Pythagoras did not merely demonstrate this theorem by citing specific instances. Rather, he devised a line of reasoning in mathematics that could be used to demonstrate the proposition in a more general sense. Pythagoras is largely responsible for the modern tradition of mathematical argument, which is fundamental to the scientific method. He was the first to use the word cosmos to refer to a well-ordered and harmonious universe, and a world humans could understand. Many Ionians thought observation and experimentation, the 2 mainstays of modern scientific methodology, could reveal the universe's underlying harmony. Pythagoras, on the other hand, utilized an entirely different approach. He taught that one could discover the rules of nature through one's own introspection. He and those who followed him did not believe in experimentalism on a fundamental level. They were experts in mathematical theory, and they were mystics in every sense of the word. In a statement that could be construed as being less than charitable, Bertrand Russell asserts that Pythagoras founded a religion, the main tenets of which were the transmigration of souls and the sinfulness of eating beans. His religion took the form of a religious order which in some places took control of the state and instituted a saint's rule. In other places, however, the state was not conquered. But those who had not been converted yearned for beans and eventually rebelled. The Pythagoreans took great pleasure in the indisputable evidence that could be derived from mathematical demonstrations. They envisioned a universe in which the sides of right triangles perfectly obeyed straightforward mathematical relationships. This was a world that was open to the human intellect. It stood in stark contrast to the chaotic reality of the everyday world in which we live and work. They believed that through their mathematics they had caught a glimpse of a perfect reality, a realm of the gods, and that the world we know is merely an imperfect reflection of this perfect reality. Prisoners were imagined to be tied in such a way that they saw only passers-by's shadows and believed them to be real in the famous parable of the cave written by Plato. These prisoners had no idea that a more complex reality would be available if they turned their heads. The Pythagoreans would significantly impact Plato and, later on, Christianity. They did not advocate for the open discussion of opposing viewpoints or viewpoint confrontation. Instead, they adhered to a rigidity in their practices, which, like all orthodox religions, prevented them from recognizing and correcting their mistakes. Cicero stated in writing that, when conversing, the demand should be less for the weight of authority than for the force of argument. They stop using their own judgment and take what they perceive to be the verdict of their chosen master as if it were the final answer, which is a positive hindrance to those who want to learn but are often negatively affected by the authority of those who profess to teach. When questioned as to the grounds of any assertion that they advanced in debate, it is said that the Pythagoreans were accustomed to responding, "The master said so," with "the master," referring to Pythagoras. In point of fact, I am not inclined to approve of the practice traditionally ascribed to the Pythagoreans. Because of the force of an opinion already decided, authority prevailed despite the lack of support from reason. Pythagoreans were particularly interested in regular solids, three-dimensional objects with symmetrical sides composed of the same regular polygon. The cube has 6 identical squares for its sides and is the simplest example. However, there are only 5 regular solids despite infinite regular polygons. A well-known example of mathematical reasoning which serves as the proof for this statement can be found in Appendix 2. Their familiarity with a solid known as the dodecahedron, which has 12 pentagons for sides, gave off an ominous vibe. It had some esoteric connection to the cosmos. Earth, fire, air, and water were thought to be the 4 elements that made up the world at the time. And these elements were somehow associated with the other 4 regular solids. They reasoned that since there were only 4 regular solids, the 5th one must correspond to a 5th element that could only be the stuff that made up the heavenly bodies. The concept of a 5th essence is where the English word quintessence comes from. The dodecahedron was not supposed to be discussed with regular people at all. Pythagoreans believed that everything, including all other numbers, could be calculated using only whole numbers because they were obsessed with these numbers. When it was discovered that the square root of 2, the ratio of the diagonal to the side of a square, was irrational and that 2 could not be accurately expressed as the ratio of any 2 whole numbers, regardless of how large these numbers were, a crisis in doctrine ensued. Pythagorean theorem was used, ironically, in the process of making this discovery, which is reproduced in Appendix 1. The concept of irrational originally referred to the inability of a number to be written as a ratio. But for the Pythagoreans, it came to mean something menacing, a hint that their worldview might not make sense, which is the other meaning we associate with the word irrational today. Instead of discussing these significant mathematical discoveries with others, the Pythagoreans attempted to stifle knowledge of the dodecahedron and its existence. The information was not to be shared with the outside world. Even in the modern era, scientists continue to oppose the popularization of science. They believe scientific knowledge should remain within the confines of the cult and should not be tainted by public understanding. Pythagoreans believed that the sphere was perfect, meaning that every point on its surface was the same distance from its center. Circles were another ideal shape. In addition, Pythagoreans were adamant that planetary motion was circular and occurred at a constant rate. The non-circular motion was in some way flawed and unsuitable for the planets, which, being free of the Earth, were also deemed perfect. They believed that moving slower or faster at different places in the orbit would be unbecoming. The work of Johannes Kepler provides a crystal-clear illustration of the Pythagorean tradition's benefits and drawbacks. Early Christians readily accepted the Pythagorean concept of a perfect and mystical world unseen by the senses. This concept was also an essential component of Kepler's early education. On the one hand, Kepler was convinced that mathematical harmonies exist in nature. He wrote that the universe was stamped with the adornment of harmonic proportions, and that simple numerical relationships must determine the motion of the planets. On the other hand, Kepler was convinced that the motion of the planets could not be explained by any other mechanism. On the other hand, following the Pythagoreans, he had long believed that the only acceptable motion was circular and uniform. After finding time and time again that the observed motions of the planets could not be explained using this method, he tried again. On the other hand, unlike many Pythagoreans, he was a proponent of observation and experimentation in the real world. After a while, his extensive observations of the apparent motion of the planets compelled him to give up the concept that the planets travel in circular paths and instead acknowledge that they move in ellipses. Kepler was both inspired in his search for the harmony of planetary motion and delayed for more than a decade by the attractions of Pythagorean doctrine. Kepler was inspired to search for the harmony of planetary motion. The ancient world was characterized by a widespread contempt for the sensible. Plato advised astronomers to think about the heavens rather than observe them to avoid wasting time. Aristotle says, "The lower sort are by nature enslaved people, and it is better for them than for all inferiors that they should be under the rule of a master." Aristotle said this because he believed the lower sort are by nature enslaved people. The enslaved person is allowed to participate in the daily activities of his master, while the artisan has a less intimate connection with his master and only achieves excellence in direct proportion to the amount of time he spends serving as an enslaved person. The more scathing variety of mechanics have their own distinct form of servitude. as Plutarch stated, it does not necessarily follow that, if the work delights you with its grace, the one who wrought it is worthy of esteem. He explained why this was the case. The philosopher Xenophon believed that what are called the mechanical arts carry a social stigma and are rightly dishonored in our cities. Due to attitudes like these, the brilliant and potentially fruitful Ionian experimental method was largely disregarded for the next 2,000 years. Experiments are the only way to choose between competing hypotheses and make progress in scientific research. With experiments, science can advance. Even in modern times, the anti-empirical taint left by the Pythagoreans can be found. However, why? Why do I have such a strong aversion to participating in this experiment? Benjamin Farrington, a historian of science, has put forward a theory to explain the fall of ancient scientific achievement, which is as follows. The mercantile tradition, which resulted in the development of Ionian science, also resulted in the development of an economy based on slavery. The acquisition of wealth and power was contingent upon one's ownership of enslaved people. The fortifications that belonged to polycrates were constructed by people who were enslaved. Athens had a sizable population of people who were held as enslaved people during the time of Pericles, Plato, and Aristotle. Benjamin Farrington, a historian of science, has put forward a theory to explain the fall of ancient scientific achievement, which is as follows. The mercantile tradition, which resulted in the development of Ionian science, also resulted in the development of an economy based on slavery. The acquisition of wealth and power was contingent upon one's ownership of enslaved people. The fortifications that belonged to polycrates were constructed by people who were enslaved. Athens had a sizable population of people who were held as enslaved people during the time of Pericles, Plato, and Aristotle. All courageous Athenians talk about how democracy only applies to a select group of people with privilege. Most of the time, enslaved people are responsible for performing manual labor. However, conducting experiments in the name of science requires manual labor, which slaveholders try to keep as far away from as possible. This is because only slaveholders, politely referred to as gentlemen in some societies, have the leisure time to conduct scientific research. As a result, only some people engaged in scientific endeavors. The Ionians could construct machines that were both functional and beautiful. Nevertheless, the fact that there were people available to be enslaved was detrimental to the economic motivation for the development of technology. Therefore, the mercantile tradition contributed to the Great Ionian Awakening around 600 BC. The practice of slavery may have been the reason for the decline of the Ionian civilization some 2 centuries later. There are a lot of ironies in this situation. Many different regions are experiencing the same trend. The work of Kuo Shouqing, who utilized an observational baseline of 1,500 years and improved astronomical instruments and mathematical techniques for computation, represented the pinnacle of indigenous Chinese astronomy around 1280. He did this by using improved mathematical techniques for computation and by improving astronomical instruments. It is generally accepted that Chinese astronomy went through a significant decline at some point. Nathan Seveen thinks that part of the reason lies in the increasing rigidity of elite attitudes, so that the educated were less inclined to be curious about techniques and less willing to value science as an appropriate pursuit for a gentleman. The profession of astronomer eventually evolved into a hereditary office, which is a practice that is incompatible with the progression of the subject. In addition, the responsibility for the evolution of astronomy remained centered in the imperial court and was largely abandoned to foreign technicians, primarily the Jesuits. The Jesuits were the ones who had introduced Euclid and Copernicus to the astonished Chinese. However, after the censorship of the latter's book, they had a vested interest in concealing and suppressing heliocentric cosmology. It's possible that the prevalence of the slave economy in Ionia contributed to the demise of science in Indian, Mayan, and Aztec civilizations, the same reason that it fell into disuse in Ionia. The fact that the educated classes in the contemporary Third World tend to be the children of the wealthy who have a vested interest in the status quo and who are not accustomed to working with their hands or challenging conventional wisdom is a major contributor to the political instability that plagues this region. the scientific process needs to advance at a more rapid pace. Both Plato and Aristotle had no problem living in a society based on slavery. They provided rationales for the system of oppression. They were of service to despots. They taught the disconnection of the mind from the body, which was a natural enough ideal in a society based on slavery. They also taught the separation of matter and thought, and the separation of the earth and the heavens. These divisions were to dominate the thinking of Westerners for more than 20 centuries. Plato, who believed that all things are full of gods, connected his political philosophy and his conception of the cosmos through the analogy of slavery. He advocated for destroying all of Democritus's books. Much like they made significant strides towards advancing the field of science by recognizing the contributions made by Pythagoras and Plato to the idea that the cosmos is knowable and that there is a mathematical basis for nature. However, by concealing unsettling facts, adhering to the belief that scientific knowledge should be reserved for a select few, shunning the practice of experimentation, embracing mysticism, and being content to live in slave societies, these individuals have set the human enterprise back. The Ionian approach, which was in some cases transmitted through scholars at the Alexandrian Library, was finally rediscovered after a long mystical sleep during which the tools of scientific inquiry lay rusting. The Western Hemisphere experienced a reawakening. Experimentation and open inquiry were given their respectful place in society once more. The reading of long-lost books and sections of text was resumed. This ancient Greek tradition inspired Leonardo da Vinci, Christopher Columbus, and Nicholas Copernicus, who independently retraced parts of this tradition. There is a lot of courageous free inquiry going on in our time, although not in politics and religion, and there is a lot of Ionian science. But in addition to this, there are horrifying superstitions and potentially lethal ethical ambiguities. Ancient inconsistencies have left us with problems. The Platonists and the Christians who succeeded them believed that the heavens were perfect and divine, whereas the earth was corrupted and unpleasant somehow. The fundamental concept that the earth is a planet and humans are citizens of the universe was disregarded and lost. Aristarchus, born in Samos 3 centuries after Pythagoras, was the first to argue for this idea. Aristarchus was one of the Ionian scientists who lived at the end of their time. At this point in history, the great library of Alexandria had become the epicenter of intellectual progress and enlightenment. Aristarchus was the first to propose that the sun, not the earth, is at the center of the planetary system and that all planets, rather than the earth, revolve around the sun. He also proposed that the sun is the center of the solar system. Typically, his writings on this subject must be recovered to proceed. He reasoned that because the earth casts such a large shadow on the moon during a lunar eclipse, the sun must be considerably more massive than our planet and located on the outskirts of our solar system. After that, he may have concluded that it is illogical for such a massive object as the sun to revolve around such an insignificant object as the earth. He positioned the sun in the middle, set the earth to rotate once per day on its axis, and set the earth's orbit around the sun to occur once yearly. It is the same concept that we associate with the name of Copernicus, whom Galileo called the restorer and confirmer, rather than the inventor of the heliocentric hypothesis. Even though the foundations had been laid by Aristarchus, people were still determining the correct arrangement of the planets for most of the 1,800 years between him and Copernicus. Around the year 280 BC, it became perfectly clear. The concept incensed several Aristarchus contemporaries during his time. Cries called for him to be condemned for impiety, similar to the cries about Anaxagoras, Bruno, and Galileo. The resistance to Aristarchus and Copernicus, a form of geocentrism in everyday life, is still with us. We still talk about the sun rising and setting. Even though it has been 2,200 years since the time of Aristarchus, our language continues to operate under the assumption that the Earth does not rotate. The vast distances that separate the planets from one another, such as the 40 million kilometers that separate Earth and Venus at their point of closest approach, and the 6 billion kilometers that separate Earth and Pluto, would have astounded the ancient Greeks, who were incensed by the idea that the Sun might be as big as the Peloponnesus. Considering the solar system was significantly closer to home and more local, it was only natural. If I place my index finger in front of my eyes and look at it with both eyes, it appears to be moving in the background in the distance. The closer my finger gets to the object, the more motion I appear to see. Based on the amount of this apparent motion, also known as parallax, I can calculate the distance to my finger. If I spread my eyes further apart, the movement of my finger will appear to be much more pronounced. The longer the baseline from which we make our two observations, the greater the parallax will be, and the more accurately we can measure the distance to more distant objects. However, we live on a platform that is constantly moving, and that platform is the Earth. Every 6 months, the Earth travels the 300,000 kilometers that separate one end of its orbit from the other. We can determine very large distances at the same immobile celestial object 6 months apart. Aristarchus had a hunch that the stars were actually faraway suns. He positioned the Sun among the permanently positioned stars. The fact that there was no detectable change in stellar parallax as the Earth moved gave rise to the hypothesis that the stars were located far from the Sun. Before the telescope's development, even the most nearby stars had a parallax that was too minute to be picked up by the instrument. In the 19th century, someone first attempted to measure the parallax of a star. Straightforward Greek geometry made it abundantly clear that the distance between the stars was measured in light years. Even though the Ionians will have to use this alternative technique at some point in the future, there is another method for determining the distance to the stars that they could discover. It is common knowledge that things appear more diminutive when viewed from a greater distance. Perspective is an artistic and photographic technique based on the inverse proportionality between apparent size and distance. Therefore, the further away we are from the Sun, the more diminished in size and brightness it appears to be. How far away would we have to be from the Sun before it would appear as if it were a star in both size and brightness? Or would an equal piece of the sunshine with the same intensity as a star? To investigate this question, Christian Huygens carried out an early experiment that was very much in the Ionian tradition. After drilling a few holes in a brass plate, Huygens held the plate up to the Sun and questioned it himself about which hole appeared as bright as he recalled the brilliant star, Sirius, to have been the previous night. The hole was approximately 1/5 of 1/800,000th of the Sun's apparent size. Therefore, according to his reasoning, Sirius must be 28,000 times farther from us than the Sun, equivalent to approximately half a light year. After looking at a star for many hours, it is difficult to remember how bright it was, but Huygens could recall the information very accurately. If he had known that Sirius had a higher intrinsic brightness than the Sun, he would have been able to find an almost perfect answer. The distance between Sirius and the Sun is 8.8 light years. It hardly makes a difference that Aristarchus and Huygens utilized imprecise data and derived imperfect answers from their research. They provided such a detailed explanation of their procedures that it became possible to derive more precise answers as more accurate observations became available. The question, "What are the stars?" fascinated me as a young boy growing up in Brooklyn. Between the time of Aristarchus and Huygens, humans provided an answer to this riddle. The answer is that the stars are enormous suns located in interstellar space and separated by light years. The most important thing we can take away from Aristarchus is the realization that neither we nor our planet occupies a special place in the natural order. This realization has since been used downward to the planets and upward to the stars and sideways to many different subsets of the human family, with a great deal of success, but always against it. It is responsible for significant advancements in astronomy, physics, biology, anthropology, economics, and politics. Is the widespread social implications of it one of the primary motivations behind efforts to suppress it? The influence of Aristarchus's legacy can be felt well beyond the scope of the astronomical realm. William Herschel, a musician and astronomer to George III of England, finished a project to map the starry skies at the end of the 18th century. He discovered what appeared to be equal numbers of stars in all directions in the plane or band of the Milky Way. Reasonably, he deduced that we were at the galaxy's center. In the months leading up to World War I, a man from Missouri named Harlow Shapley developed a method for determining the distances to globular clusters, which are beautiful spherical arrays of stars that look like a swarm of bees. A star that was noticeable due to its variability but always had the same average intrinsic brightness was the stellar standard candle that Shapley had discovered. In the same way that we can estimate the distance to a lantern of known intrinsic brightness based on the feeble light that reaches us in a field, Shapley was able to calculate how far away these stars are by comparing the dimness of these stars when they were discovered in globular clusters with their actual brightness, as determined by nearby representatives. This is, in a sense, the method that Huygens developed. Shapley discovered that the globular clusters were not centered around the solar neighborhood, but rather about a distant region of the Milky Way, in the direction of the constellation Sagittarius, also known as the Archer. It seemed to him that there was a strong possibility that the nearly 100 globular clusters used in this investigation would somehow revolve around the Milky Way's enormous barycenter and pay homage to it. In 1915, Shapley mustered the bravery to suggest that our solar system was located on the periphery of our galaxy rather than near its center. Herschel had been led astray due to the copious amount of dust that obscured his view in the direction of Sagittarius. He was unaware of the enormous number of stars that lay beyond. It is now very clear that we live approximately 30,000 light-years from the galaxy's center, on the outskirts of a spiral arm, in a region with a relatively low density of stars. Some may inhabit a planet located in the core of the globular cluster, or one that orbits a central star in one of Shapley's globular clusters. These beings might feel sorry for us because we only have a few stars visible to the naked eye, while their skies will be ablaze with stars. In comparison to the meager few thousand stars that can be seen from Earth, there would be millions of brilliant stars visible near the center of the Milky Way galaxy. Even if the sun went down, we would never experience nighttime. Although, in the 18th century, Thomas Wright of Durban and Immanuel Kant of Königsberg each had a premonition that the exquisite luminous spiral forms viewed through the telescope were other galaxies, astronomers believed that there was only one galaxy in the cosmos, and that galaxy was the Milky Way. This belief persisted well into the 20th century. Kant made the explicit suggestion that the galaxy M31, which is located in the constellation Andromeda, is an additional Milky Way which is made up of an enormous number of stars, and he proposed calling such objects by the evocative and haunting phrase, island universes. Some researchers entertained the notion that the spiral nebulae were not isolated universes in the far reaches of space, but rather nearby interstellar gas clouds that were condensing and possibly on the verge of forming solar systems. To determine how far apart the spiral nebulae are, a class of intrinsically much brighter variable stars was required to serve as a new standard candle. Such stars were discovered to be alarmingly dim in M31 by Edwin Hubble in the year 1924. It became apparent that M31 was located at a prodigious distance, now estimated to be slightly more than 2 million light-years. But for M31 to be located at such a great distance, it can't be a cloud of mere interstellar dimensions. Instead, it must be much larger, and, in its own right, an enormous galaxy. And the other, less bright galaxies must be even further away than that. 100 billion of them must be strewn across the darkness to the edges of the known universe. Since the beginning of human history, we have pondered where we fit into the greater cosmos. Where are we right now? Since the beginning of our species, when our ancestors occasionally looked up at the stars for no apparent reason, among the Ionian scientists of ancient Greece and even in our own time, this topic has fascinated us. Who exactly are we? We discover that we live on an insignificant planet that orbits a humdrum star that is lost between two spiral arms on the outskirts of a galaxy. This galaxy is a member of a sparse cluster of galaxies tucked away in some forgotten corner of a universe where there are far more galaxies than people. This viewpoint is a brave continuation of our propensity for constructing and testing mental models of the skies, and it depicts the sun as a crimson hot stone the stars as celestial flames and the galaxy as the backbone of night. Since Aristarchus, each new stage we have traversed in our quest has brought us further and further away from the center of the cosmic drama. More time is required to properly digest all of these recent discoveries. The discoveries that Shapley and Hubble made occurred during the lifetimes of a great number of people who are still alive today. In their hearts are those who still pine for a universe in which the Earth serves as the century, focus and fulcrum. Some people privately deplore these great discoveries, view every step as a demotion, and consider every step a demotion. However, to interact with the cosmos, we must first understand it. This is true, even if it dashes our hopes of achieving some undeservedly privileged position. A necessary first step towards bettering the neighborhood is to understand the area in which we live. It is helpful to have knowledge of the characteristics of other neighborhoods as well. If we want our planet to be recognized as having significance, there is something that we can do to make that happen. The boldness of our inquiries and the comprehensiveness of our responses give our world its significance. We began our exploration of the cosmos with the question, what are the stars? This question has been asked since the dawn of our species and is passed down from generation to generation with the same sense of awe and curiosity. The spirit of discovery resides within each of us. We started out as nomads, and to this day we still consider ourselves nomads. We have lingered on the outskirts of the universe's vast ocean for far too long. At long last, everything is in place for us to set sail for the heavens. Both the moon and the sun are located at a great distance. However, their gravitational influence is real and can be felt here on Earth where they originated. The beach brings to mind the vastness of space. After aeons of jostling, rubbing, abrasion and erosion, fine sand grains, which are more or less uniform, have been produced from larger rocks. This process has been driven by waves and weather for a long time, so the moon and the sun are far away. The beach also causes us to reflect on the passage of time. The age of the world predates that of the human species by a significant margin. The number of grains in a handful of sand is approximately 10,000, greater than the number of stars seen with the naked eye on a dark night. However, the number of stars visible to the human eye represents only a minute portion of the total number of stars. We can only make out a sparse scattering of the stars closest to us at night. In the meantime, the wealth of the cosmos is unfathomable. The total number of stars in the universe is greater than the sum of all the grains of sand found on Earth's beaches combined. A constellation is an arbitrary grouping of stars composed of intrinsically dim stars that seem bright because they are nearby and intrinsically brighter stars that are somewhat more distant from us. Despite the efforts of ancient astronomers and astrologers to put pictures in the skies, a constellation is nothing more than an arbitrary grouping of stars. To a high degree of accuracy, no 2 points on Earth are located at a different distance from any stars. Because of this, the patterns of the stars within a particular constellation do not change even if we travel from Soviet Central Asia to the Midwest in the United States. In astronomical terms, the United States of America and the Soviet Union correspond to the same location. The stars that make up any constellation are all located so far away from Earth that we can never comprehend them as a three-dimensional arrangement for as long as we are rooted here. A light year is approximately 10 trillion kilometers long. As a reminder, the average distance between the stars is only a few light years. We must travel over distances comparable to those that separate the stars. More specifically, we must venture across the light years for the patterns of the constellations to shift. After that, it will appear that some nearby stars have moved out of the constellation while others have moved in, and the overall arrangement of the constellation will change dramatically. Our technology is yet to be capable of undertaking such massive interstellar journeys, at least not within a time frame that is considered reasonable. But our computers can be taught the three-dimensional positions of all of the nearby stars, and we can ask to be taken on a little trip, for example, a circumnavigation of the collection of bright stars that constitute the Big Dipper, and watch the constellations change before our very eyes. Follow the dots drawings of the night sky typically connect the stars that make up various constellations. As we shift our position, we can see that the apparent shapes of the objects are being severely warped. The people who live on the planets that orbit around faraway stars see very different constellations in the night sky than we do here on Earth. Their night skies are like Rorschach tests for other people's minds. Someday in the next few centuries, a spaceship from Earth may travel such vast distances at some remarkable speed and see new constellations that no human has ever seen, except with a computer like this one. The appearance of the constellations shifts not only in space but also in time. This occurs not only when we move to a new location but also when we wait for a long enough period. There are times when the stars move as a group or cluster, and other times when a single star may move relatively quickly compared to its neighbors. These stars eventually move on to a new constellation, leaving behind the one they were previously a part of. If one of the stars in a binary star system were to explode, it would free the other star from the gravitational bonds that held them together. The freed star would then launch into space at the same speed as its previous orbit, creating an effect similar to a catapult in the sky. In addition, stars are born, progress, and eventually expire. If we wait long enough, we will see new stars appear while the old ones disappear. The patterns in the sky are gradually dissolving and shifting. Even during the brief existence of the human species, which spans only a few million years, ideas have been evolving. Consider the current arrangement of the Great Bear or the Big Dipper. Our computers can also transport us through time as well as space. When we run the Big Dipper backwards into the past, taking into account the movement of its stars, we find that its appearance was quite different a million years ago. During that time, the Big Dipper appeared shaped like a spear. If you somehow found yourself transported back to an unknown era in the distant past, you could determine the epoch by observing the constellations in the sky. For example, if the Big Dipper is shaped like a spear, you are in the Middle Pleistocene. We can also request that the computer move a constellation forward in time. Take the sign of Leo the Lion. The zodiac is a band of 12 constellations that wrap around the sky in the sun's apparent annual path as it travels through the heavens. The belief that the zodiacal constellations such as Leo are primarily animals is where the word zoo comes from. Even a million years from now, the constellation Leo will not resemble a lion nearly as much as it does now. Our distant descendants may refer to it as the constellation of the radio telescope. But in a million years, the radio telescope will be as archaic as the stone spear. 4 prominent stars frame the non-zodiacal constellation of Orion, the Hunter, and a diagonal line of 3 stars represents the Hunter's belt. The 3 stars that are fainter than the others and hang from Orion's belt are what the traditional astronomical projective test identifies as the Sword of Orion. Stars are formed in large clouds of gas known as nebulae, such as the one in the Orion constellation, which can be seen as the middle star in the sword. The constellation Orion contains a large number of young and hot stars, many of which are in the process of rapidly evolving into supernovae as their lives come to an end. They have a lifespan of tens of millions of years during which they are born and die. If we were to run Orion quickly into the distant future on our computer, we would see a startling effect: the births and spectacular deaths of many of its stars, which would light up and go out like fireflies in the night. Within the solar neighborhood, also known as the immediate surroundings of the Sun in space, one can find the star system Alpha Centauri, which is the closest to the Sun. It is a triple system consisting of 2 stars that revolve around each other and a third star, Proxima Centauri, that orbits the first 2 at a distance that is not easily discernible. The name Proxima comes from the fact that the star is closest to the Sun at certain points in its orbit. Most stars in the night sky are part of double or multiple star systems. Our solitary Sun is a peculiarity in the cosmos. Beta Andromeda is the second brightest star in the constellation Andromeda, located 75 light-years away. On its way to Earth, the light that reveals it to us now has traveled through interstellar space for 75 years, during which time it has been invisible to us. In the highly improbable event that Beta Andromeda blew itself up on Tuesday, we would not know about it for another 75 years. This is because information traveling at the speed of light takes 75 years to traverse the enormous interstellar distances between the stars. When the light that we now see from this star began its long journey, a young Albert Einstein was beginning his career as a patent clerk in Switzerland. On Earth, he had recently published his seminal work, The Special Theory of Relativity. The fabric of space and time is woven together. When we want to look back in time, we must look back into space first. Light travels at an extremely rapid speed. However, space is empty, and the distance between the stars is great. Compared to other astronomical distances, a distance of 75 light-years or less is relatively short. It is approximately 30,000 light-years from the Sun to the galactic core of the Milky Way galaxy. It is approximately 2,000 light-years from our galaxy to the nearest spiral galaxy, M31, in the constellation Andromeda. When the light that reached Earth from M31, which we see today, first arrived, there were no humans on our planet. However, our ancestors rapidly evolved into the form we have today. It takes 8 or 10 billion years for light to travel from Earth to the most distant quasars in the universe. We can see them as evidence that the Earth accumulated more material before the Milky Way. This circumstance is not unique to astronomical objects. However, because only astronomical objects are so distant, the importance of the limited speed of light becomes apparent in this context. When you look at a friend who is across the room and 3 meters 10 feet away, you do not see her as she is now, but rather as she was 100 millionths of a second ago. To determine the travel time, we divided the total distance by the average speed used in this calculation. However, the difference between now and now minus 100 millionth of a second is so minute that it is impossible to distinguish between them. When we look at a quasar that is 8 billion light-years away, the fact that we are seeing it as it was 8 billion years ago may be very significant. For instance, some believe that quasars are explosive events that are only likely to occur early in the history of galaxies. If this is the case, the further away the galaxy is, the earlier in its history we can observe it, and the more likely we will see it as a quasar. In fact, if we look at distances greater than 5 billion light-years, we will see an increase in the number of quasars. The 2 Voyager interstellar spacecraft, which are currently traveling at 1/10 the speed of light, are the most powerful machines that have ever been launched from Earth. They would have to travel a distance equivalent to that of the nearest star, which would take 40,000 years. Do we have any plans to leave Earth and travel the vast distances all the way to Proxima Centauri in a reasonable amount of time? Is there anything we can do to get closer to the speed of light? What exactly makes the speed of light so magical? We are capable of going much faster than that. If you had strolled through the bucolic countryside of Tuscany in the 1890s, you might have run into a long-haired adolescent who had dropped out of high school while traveling to Pavia. His teachers in Germany had warned him that he would never amount to anything, that his questions were disruptive to classroom discipline, and that he would be better off dropping out of school altogether. Therefore, he up and left, taking pleasure in the independence of northern Italy, where he could ruminate on topics completely unrelated to the topics he had been coerced into learning in his highly structured Prussian classroom. His name was Albert Einstein, and his musings were responsible for the revolution in the world. Bernstein's People's Book of Natural Science was a popularization of science that described on its first page the astounding speed at which electricity travels through wires and light travels through space. This book profoundly impacted Einstein, who was captivated by it. He pondered the possibilities of what the world would be like if it could travel on waves of light, achieving and maintaining travel at the speed of light. What an interesting and entrancing thought it must have been for a young boy to have while walking along a road in the countryside where the sunlight was dappled and rippled. If you traveled with a light wave, there was no way to tell if you were actually riding one. If you began your journey on the highest point of a wave, you would remain there and eventually forget that you were even riding a wave. When traveling at the speed of light, a strange phenomenon takes place. The more Albert Einstein contemplated such questions, the more unsettling he found them. If you could travel at the speed of light, paradoxes would pop up everywhere you went. Without consideration, a few ideas were taken at face value and treated as facts. Einstein's questions were straightforward and could have been asked many decades earlier. For instance, when we say that two events are occurring simultaneously, what exactly do we mean by that? Imagine that I am coming towards you on a bicycle right now. As I approach the intersection, I come dangerously close to hitting a horse-drawn cart. I have to swerve to avoid getting run over, but just barely. Now think about the event again, but this time, imagine that the cart and the bicycle are moving at speeds approaching the speed of light. If you are standing at the edge of the road, you will notice that the cart moves perpendicular to the direction in which you are looking. You can tell I'm approaching you because the sunlight reflects off me. Would the sum of my speed and the speed of light be sufficient to ensure that the image of me reaches you a significant amount of time before the image of the cart? Should I see you make a sharp turn once you spot the delivery cart coming? From my vantage point, the cart and I should be able to approach the intersection simultaneously. But this might not be possible from your perspective. Could I come dangerously close to colliding with the cart while you watched me veer around nothing and continue to pedal merrily in the direction of the town of Vinci? These are interesting questions with a lot of nuance. They challenge what is already known. There is a good explanation for why no one considered them before Einstein. Einstein produced a fundamental rethinking of the world and a revolution in physics from such simple questions. There are some rules or commandments of nature that must be obeyed for the world to be comprehended, and if we are to avoid such logical paradoxes when traveling at high speeds, we must adhere to certain guidelines. These guidelines were formalized by Einstein in the form of the special theory of relativity. Whether an object is moving or not, the speed at which light, either reflected or emitted, travels from it remains the same. The speed of light is not to be increased by adding your own speed. Additionally, no material object may move faster than the speed of light. Thou shalt not travel at or beyond the speed of light. This commandment also applies to travel. Nothing in the laws of physics would prevent you from traveling as close to the speed of light as you like. Traveling at 99.9% of the speed of light would be fine. However, regardless of how diligently you work, you will never be able to acquire that final decimal point. There must be a cosmic speed limit for the world to make sense from a logical standpoint. If not, you could achieve any desired speed by adding velocity to a moving platform. Around the turn of the century, many Europeans believed they had privileged frames of reference. They believed that German, French, or British culture and political organization were superior to those of other countries. They also believed that Europeans were superior to other people who had the good fortune to be colonized. Their contemporaries disregarded or ignored the social and political application of Aristarchus and Copernicus's ideas. Albert Einstein fought against the idea of privileged frames of reference in politics and physics when he was young. No place could be considered at rest, and no perspective on the cosmos was superior to any other perspective. This was because the universe was filled with stars moving in all different directions at breakneck speeds. This is the definition of the concept known as relativity. Despite its mystical overtones, the concept at its core is quite straightforward. When viewed from the universe's perspective, every location is on par with every other location. Regardless of who is describing it, one thing is certain. The laws of nature are always the same. If this is the case, and it would be incredible if there was something unique about our inconsequential location in the universe, then it follows that no one can travel faster than the speed of light. This is because light has a finite speed. It is possible to hear the crack of a bullwhip because the whip's tip is moving at a speed greater than the speed of sound. This results in the creation of a shockwave as well as a small sonic boom. The origin of a thunderclap is very similar. It was once believed that aeroplanes could not fly at a speed greater than the speed of sound. It is now common practice to travel at a speed greater than sound. On the other hand, the light barrier is not the same as the sound barrier. It is not merely an issue of engineering, such as the problem that the supersonic aeroplane helps to resolve. It is a basic rule of nature, on the same level as the law of gravity. In addition, there are no phenomena that we have encountered in our lives, such as the snap of a bullwhip or the clap of thunder for sound, that point to the possibility of moving through a vacuum at a speed greater than the speed of light. On the other hand, there is an extensive range of experience in precise quantitative agreement with special relativity. Some examples of this kind of experience include nuclear accelerators and atomic clocks. Because sound is transmitted through some material medium, typically air, the simultaneity problems only apply to sound to a much lesser extent than they do to light. When a close friend speaks to you, you feel the motion of the air molecules. Light, on the other hand, can travel through empty space. In a vacuum, the free movement of molecules of air is not constrained in the same way that it is in an atmosphere. We can receive light from the sun despite the vast distance that separates us from it. However, no matter how carefully we listen, we cannot hear the crackling of sunspots or the rumbling of solar flares. Before the theory of relativity was developed, people believed that light traveled through a unique medium present throughout all of space and was referred to as the luminiferous ether. On the other hand, the well-known Michelson-Morley experiment provided conclusive evidence that there is no such thing as the ether. Rumors have been that certain things can move faster than light. The concept of the speed of thought is brought up in conversation occasionally. This is a ridiculous idea, especially when one considers that the speed at which impulses travel through the neurons in our brains is roughly comparable to that of a cart. The fact that humans are smart enough to come up with relativity proves that we think well, but I do not believe we can take pride in our ability to think quickly. However, the electrical impulses that make up today's computers travel at a speed very close to light. The theory of special relativity, which Einstein finished developing in his middle 20s, has been supported by every experiment that has been carried out to verify it. Someone will come up with a theory tomorrow that explains everything we already know, is consistent with everything we already know, avoids privileged reference frames, and makes it possible to travel faster than light. Someone will come up with this theory, but I have serious doubts about that. Our common sense and Einstein's prohibition against traveling faster than the speed of light are incompatible. But why should we put our faith in common sense regarding this issue? Why should the laws of nature be constrained by our experience traveling at 300,000 kilometers per second when we only travel at 10 kilometers per hour? The theory of relativity places restrictions on the capabilities of humans. However, it is optional for the universe to be completely harmonious with the aspirations of humans. The theory of special relativity makes it impossible for us to build a spaceship capable of traveling faster than the speed of light. This tantalizing evidence hints at an additional approach that is not expected. Let's follow in the footsteps of George Gamow and imagine a world in which the speed of light is not its actual value of 300,000 kilometers per second, but rather something much more modest, like 40 kilometers per hour, and this speed is strictly enforced. Because there are no crimes or penalties for breaking the laws of nature, nature is self-regulating and merely arranges things so that its prohibitions are impossible to violate. Imagine riding a motor scooter and getting closer and closer to the speed of light. There are a lot of sentences in relativity that start with the word imagine. Einstein referred to this type of activity as a Gedanken experiment, which literally translates to thought experiment. As your speed increases, you will eventually be able to see around the corners of objects moving past you. When you are fixedly facing forward, things behind you will appear in your field of vision when you are looking forward. From your vantage point, the world appears very strange when you travel close to the speed of light. Eventually, everything appears to be crammed into a small circular window just in front of you. When viewed from the perspective of a stationary observer, the light reflected off you turns blue when you return and red when you depart. Your normally invisible infrared emission will be shifted to the shorter wavelengths associated with visible light if you move towards the observer at almost the speed of light. As you move closer to the observer, this will cause an eerie chromatic radiance to envelop you. The breathtaking effect of traveling near the speed of light is called time dilation. When you travel close to the speed of light, you become compressed in the direction of motion. Your mass increases, and the passage of time slows down as you experience it. But when viewed from the perspective of an observer moving alongside you, perhaps there is a second seat on the scooter, none of these effects are seen to take place. These odd and puzzling predictions of special relativity are true, but only in the most fundamental sense that anything in science can be true. They are dependent on the relative motion of you and the object. However, they are not optical illusions. They exist in the world. Because they can be demonstrated with elementary mathematics, primarily algebra, from the first year on, any educated person should be able to comprehend them easily. They are also in agreement with the results of many different experiments. When compared to clocks that are kept in stationary locations, timepieces that are carried on aeroplanes are less accurate. Accelerated particles would collide with the walls of the apparatus if nuclear accelerators were not constructed to allow for an increase in mass in conjunction with an increase in speed. If nuclear accelerators were constructed differently, there would be more room for experimentation in nuclear physics. To calculate speed, divide the distance traveled by the amount of time. Because it is not possible to add speeds near the velocity of light, as it is something that we are used to doing in the working world, it is necessary to abandon the common conceptions of absolute space and time, which are independent of your relative motion. Because of this, you contract. This is the cause of a slowing of the passage of time. If you traveled at the speed of light, you would hardly age, but your friends and relatives who remained on Earth would continue to age at the typical rate. What a striking contrast there would be between you and your friends when you returned from your relativistic journey. For example, they might have aged several decades while you would have barely changed at all. An elixir of life is traveling at the speed of light. The theory of special relativity enables us to travel to the stars thanks to the fact that time passes more slowly as we get closer to the speed of light. To what extent, however, does the realm of practical engineering permit the possibility of approaching the speed of light? Is it possible to build a starship? Tuscany was not only the incubator of some of the thinking of the young Albert Einstein, but also the home of another great genius who lived 400 years earlier, Leonardo da Vinci. Leonardo da Vinci was delighted to climb the Tuscan hills and view the ground from a great height as if soaring like a bird. This made him imagine he was soaring through the air like a bird. He is credited with producing the earliest drawings of landscapes, towns, and fortifications as seen above. In addition to the wide range of fields in which Leonardo was interested and successful, such as painting, sculpture, anatomy, geology, natural history, military engineering, and civil engineering, he was driven by a strong desire to design and build a machine capable of flight. He tried to draw pictures, make models, and even build full-size prototypes, but his ideas were unsuccessful. There was no engine available at the time that was both sufficiently powerful and lightweight. On the other hand, the designs were exceptionally clever and inspired future engineers. Leonardo's mood suffered as a result of these setbacks. However, it was not at all his fault. He found himself unable to escape the 15th century. A similar situation occurred in 1939 when a group of engineers known as the British Interplanetary Society designed a ship that would use technology from that year to transport people to the moon. It was in no way similar to the design of the Apollo spacecraft, which successfully completed this mission 30 years later, but it did suggest that an expedition to the moon might one day be a feasible engineering possibility. At this time, we have preliminary designs for ships that will transport people to other star systems. It is only assumed that these spacecraft will indirectly depart the planet. Instead, they are built in orbit around the Earth, and from there they embark on their lengthy journeys through interstellar space. One of them was given the name Project Orion, derived from the name of a constellation. This was a constant reminder that the ship's ultimate destination was among the stars. Each explosion served as a sort of put-put, a scissable nuclear motorboat in space that Orion intended to use the explosions of nuclear weapons. And these odd and puzzling predictions of special relativity are true, but only in the most fundamental sense that anything in science can be true. They are dependent on the relative motion of you and the object. However, they are not optical illusions. They exist in the world. Because they can be demonstrated with elementary mathematics, primarily algebra, from the first year on, any educated person should be able to comprehend them easily. They are also in agreement with the results of many different experiments. When compared to clocks that are kept in stationary locations, timepieces that are carried on aeroplanes are less accurate. Accelerated particles would collide with the walls of the apparatus if nuclear accelerators were not constructed to allow for an increase in mass in conjunction with an increase in speed. If nuclear accelerators were constructed differently, there would be more room for experimentation in nuclear physics. To calculate speed, divide the distance traveled by the amount of time. Because it is not possible to add speeds near the velocity of light, as it is something that we are used to doing in the working world, it is necessary to abandon the common conceptions of absolute space and time, which are independent of your relative motion. Because of this, you contract. This is the cause of a slowing of the passage of time. If you traveled at the speed of light, you would hardly age, but your friends and relatives who remained on Earth would continue to age at the typical rate. What a striking contrast there would be between you and your friends when you returned from your relativistic journey. For example, they might have aged several decades while you would have barely changed at all. An elixir of life is traveling at the speed of light. The theory of special relativity enables us to travel to the stars thanks to the fact that time passes more slowly as we get closer to the speed of light. To what extent, however, does the realm of practical engineering permit the possibility of approaching the speed of light? Is it possible to build a starship? Tuscany was not only the incubator of some of the thinking of the young Albert Einstein, but also the home of another great genius who lived 400 years earlier, Leonardo da Vinci. Leonardo da Vinci was delighted to climb the Tuscan hills and view the ground from a great height as if soaring like a bird. This made him imagine he was soaring through the air like a bird. He is credited with producing the earliest drawings of landscapes, towns, and fortifications as seen above. In addition to the wide range of fields in which Leonardo was interested and successful, such as painting, sculpture, anatomy, geology, natural history, military engineering, and civil engineering, he was driven by a strong desire to design and build a machine capable of flight. He tried to draw pictures, make models, and even build full-size prototypes, but his ideas were unsuccessful. There was no engine available at the time that was both sufficiently powerful and lightweight. On the other hand, the designs were exceptionally clever and inspired future engineers. Leonardo's mood suffered as a result of these setbacks. However, it was not at all his fault. He found himself unable to escape the 15th century. A similar situation occurred in 1939 when a group of engineers known as the British Interplanetary Society designed a ship that would use technology from that year to transport people to the moon. It was in no way similar to the design of the Apollo spacecraft, which successfully completed this mission 30 years later, but it did suggest that an expedition to the moon might one day be a feasible engineering possibility. At this time, we have preliminary designs for ships that will transport people to other star systems. It is only assumed that these spacecraft will indirectly depart the planet. Instead, they are built in orbit around the Earth, and from there, they embark on their lengthy journeys through interstellar space. One of them was given the name Project Orion, derived from the name of a constellation. This was a constant reminder that the ship's ultimate destination was among the stars. Each explosion served as a sort of put-put, a scissable nuclear motorboat in space that Orion intended to use the explosions of nuclear weapons, and only in the vast emptiness of interplanetary or interstellar space would it have been possible to produce the vast quantities of radioactive debris that it was predestined to produce due to its design characteristics. Before the United States and other nations signed an international treaty prohibiting the detonation of nuclear weapons in space, the United States was making significant progress on the Orion project. What a terrible shame this is. The Orion starship is the most effective application of nuclear weapons. The British Interplanetary Society has been working hard on a new concept called Project Daedalus. It presupposes the existence of a nuclear fusion reactor which would be considerably less dangerous and more effective than the fission power plants that are currently in operation. Fusion reactors still need to be created, but their development is widely anticipated to occur within the next few decades. Orion and Daedalus may travel at a speed equivalent to 10% of the speed of light. Less than a human lifetime would be required to journey to Alpha Centauri, located 4.3 light-years away. The trip would take 43 years. These vessels could never get close enough to the speed of light for the effects of special relativistic time dilation to be noticeable. Even if we make optimistic projections about how quickly our technology will advance, it does not appear likely that Orion, Daedalus, or other ships of their kind will be constructed before the middle of the 21st century. However, we could already construct Orion if we so desired. Something else is required for journeys beyond the stars in the immediate vicinity. It was possible to use the Orion and the Daedalus as multi-generational ships, which means that the people who eventually arrived at a planet orbiting another star could be the distant descendants of those who had set out on the journey centuries earlier. Or scientists will devise a foolproof method of human hibernation, allowing individuals to be preserved in liquid nitrogen and brought back to life hundreds of years later. Compared to starships that travel close to the speed of light, these non-relativistic starships are simpler in design, construction, and operation, although they would have enormously high costs. Humans can travel to other star systems, but doing so will require significant effort. It is not an objective for the next 100 years, but rather for the next 1,000 or 10,000 to achieve rapid interstellar travel, with the ship's velocity approaching the speed of light. However, this could happen in theory. There has been some discussion regarding the possibility of an interstellar ramjet. The diffuse matter, primarily made up of hydrogen atoms and floating between the stars, is sucked up by R.W. Bussard, accelerated inside a fusion engine, and expelled out the back of the ship. The hydrogen would be used as both a fuel and a reaction mass. However, in the vacuum of deep space, there is only about 1 atom for every 10 cubic centimeters, equivalent to a grape's volume. A frontal scoop that is hundreds of kilometers across is required for the ramjet to function properly. When the ship reaches relativistic speeds, the hydrogen atoms will move towards the spaceship at the speed of light, which will cause them to collide with the ship. These artificially produced cosmic rays have the potential to incinerate both the spaceship and its occupants if adequate safety measures are not taken. One solution that has been proposed uses a laser to remove the electrons from the interstellar atoms, thereby causing them to become electrically charged while they are still quite a distance away. This is followed by applying an extremely powerful magnetic field, which directs the electrically charged atoms into the scoop and away from the rest of the spacecraft. This represents engineering on a scale that has never been seen on Earth. When we talk about engines, we're talking about the size of small worlds. But before we move on, let's consider what such a ship would be like. When we fall towards the ground, we feel the force of the Earth's gravitational attraction, which manifests as acceleration in our bodies. If we were to fall out of a tree, as many of our proto-human ancestors must have done, our rate of descent would increase by 10 meters, or 32 feet per second for every second that passed. This would cause our fall to be exponentially more dangerous. This acceleration, which exemplifies the gravitational pull that keeps us rooted to the Earth's surface, is referred to as 1g for the Earth's gravity. We feel perfectly at ease with accelerations of 1g because we have spent our entire lives accustomed to 1g. If we lived in an interstellar spacecraft that could accelerate at 1g, we would be in an environment completely unaltered from its natural state. One of the most important aspects of Einstein's later general theory of relativity is the equivalence between gravitational forces and the forces we would feel in an accelerating spaceship. If we maintain a constant acceleration of 1g throughout our time in space, we will approach the speed of light after 1 year. Suppose that such a spacecraft begins its journey traveling at a speed of 1g, gradually getting closer and closer to the speed of light until it reaches the halfway point of its journey, at which point it is turned around and begins traveling at a speed of 1g in the opposite direction until it reaches its final destination. Most of the journey would be completed at speeds exceeding the speed of light, resulting in a significant slowdown with time. Barnard's star, located approximately 6 light-years away, is a mission objective that is relatively close by, and a sun that may have planets. According to the clocks on board the vessel, it could be reached in approximately 8 years. The center of the Milky Way galaxy could be reached in 21 years, and the Andromeda galaxy could be reached in 28 years. People who remained on Earth would, of course, have a unique perspective on the events. They would calculate an elapsed time of 30,000 years to reach the galaxy's center rather than the standard 21 years. When we arrived home, a few of our close friends would await us there. In theory, such a journey would allow us to circumnavigate the known universe in about 56 years of ship time. This would be possible because we would get closer to the speed of light as we increase the decimal points. If we traveled tens of billions of years into the future, we would find that the sun has died and the Earth has been reduced to cinders. Traveling through space at relativistic speeds makes the universe accessible to more advanced civilizations, but only to those civilizations currently on their way there. No mechanism would allow information to travel back to those left behind at a rate greater than the speed of light. Likely, the designs for Orion, Daedalus, and the Bussard ramjet are further removed from the actual interstellar spacecraft that we will one day construct than Leonardo's models are from the supersonic transports that are in use today. However, if we do not destroy ourselves, we will eventually travel to the stars. When the planets in our solar system have been thoroughly explored, humans will turn their attention to the planets orbiting other stars. The ability to travel through time and space is connected. We can only rapidly travel into space if we simultaneously rapidly travel into the future. But what about things in the past? Can we make changes to what happened in the past? Could we alter the course of events so they didn't turn out like the history books say they did? We move forward gradually, one day at a time, every single day. We could travel through time much more quickly if we had relativistic space travel. On the other hand, many physicists think that traveling through time is impossible. They claim that even if you had a machine that allowed you to go back in time, you still wouldn't be able to change anything about the outcome of the situation in any way that would be significant. You are a contradiction because it is obvious that you already exist. After all, you cannot have been born if you went back and stopped your parents from getting together. This is an argument in which the premise is challenged because the conclusion seems absurd. It is similar to the proof of the irrationality of the square root of 2 and the discussion of simultaneity in special relativity. However, other physicists believe that two alternate realities could coexist, each of which is a reality in its own right. These realities are the one in which you were born and the one in which you were never born. Even though we can only ever experience one dimension of time, time may have many possible manifestations. Imagine for a moment that you could travel through time and alter it. For instance, you could talk Queen Isabella out of her support for Christopher Columbus. If this were the case, one line of reasoning goes, you would have started a new chain of historical occurrences, which the people you left behind in our timeline would have no way of knowing about. If this method of time travel were feasible, then every alternative history that can be conceived of would be a possibility. The majority of what we know about history can be summed up as a convoluted mass of social, cultural, and economic forces that are difficult to disentangle from one another. Numerous, insignificant, unpredictable, and random occurrences that occur continuously and frequently do not have long-range consequences. However, those that take place at pivotal junctures or forks in the road have the potential to alter the overall trajectory of history. Some circumstances in which seemingly insignificant alterations can bring about significant results. The further back in time an occurrence occurs, the more likely its influence will be significant. This is because the lever arm of time increases as time passes. A polio virus is a very small microorganism. Every day we come into contact with a great number of them. Thankfully, only one of them infrequently infects a single one of us, which causes this terrible illness. Polio affected Franklin D. Roosevelt, who became the 32nd President of the United States during his time in office. As a result of the disease's incapacitating effects, Roosevelt may have developed greater compassion for those who were disadvantaged as a result of it, or perhaps he became more driven to achieve success. The Great Depression of the 1930s, World War II, and the development of nuclear weapons could have had very different outcomes if Franklin D. Roosevelt had a different personality or had never aspired to become President of the United States. The course of history will now be different. However, a virus is extremely insignificant, with a width of only 1/1,000,000th centimeter. It is not even close to being significant. On the other hand, let us assume that our time traveler successfully convinced Queen Isabella that Christopher Columbus's geography needed to be corrected and that, based on Eratosthenes' estimation of the circumference of the Earth, Columbus could never reach Asia. Within a few decades, additional Europeans would have arrived from Europe and sailed to the western part of the New World. Around 1500, the discovery of America was more or less inevitable due to advancements in navigational technology, the allure of the spice trade, and competition among rival European powers. Without European colonization in the Americas, there would be no Nation of Columbia, no District of Columbia, no Columbus, Ohio, and no Columbia University. However, history's general direction might have remained the same. If a time traveler wanted to significantly impact the outcome of the future, they would have to alter the course of multiple events in the past at specific points in time. Exploring worlds that were never created makes for a lovely fantasy piece. By traveling there, we can better understand how history unfolds. This allows history to evolve into an experimental science. How different would the world be if a person who seems to have played a pivotal role in history had never lived, such as Plato, Paul, or Peter the Great? Imagine for a moment that the ancient Ionian Greeks' rich scientific heritage would have been able to flourish had it been preserved. That would have required many social forces to have been different during that period, including the prevalent belief that slavery was natural and appropriate. What if, instead of fading away after 2,500 years, the light that first appeared in the eastern Mediterranean region continued to shine? What if the scientific method, the dignity of crafts and the mechanical arts and the pursuit of scientific knowledge had been vigorously pursued 2,000 years before the advent of the Industrial Revolution? What if the potential of this fresh way of thinking had been recognized and appreciated by a greater number of people? There are times when I wonder if we have yet to beat back time by 10 or 20 centuries. Leonardo da Vinci's contributions would have been made 1,000 years ago, and Albert Einstein's would have been made 500 years ago. Leonardo da Vinci and Albert Einstein would never have existed on such a different version of Earth. Too many aspects of the situation would have been very different. There are hundreds of millions of sperm cells in every ejaculation. However, only one of these cells has the potential to fertilize an egg and give rise to a member of the next generation of human beings. However, the sperm successful in fertilizing an egg must be determined by the tiniest and least significant of several internal and external factors. If even a minor event that occurred 2,500 years ago had gone differently, none of us would be here today. If we had lived somewhere else, billions of other people would be here. If the Ionian spirit had prevailed, I believe that we, a different we, of course, would probably already be exploring the stars by this point. It's been a long since our first survey ships returned from Alpha Centauri, Barnard's star, Sirius, and Tau Ceti. Large fleets of interstellar transports would be built in Earth's orbit, including uncrewed survey ships, liners for immigrants, and immense trading ships to traverse the seas of space. These ships would be able to travel to and from other star systems. These vessels would have glyphs and other forms of writing on board. If we looked more closely, we might have been able to tell that Greek was being used. On the prow of one of the earliest starships, perhaps a dodecahedron would be emblazoned with the inscription, Starship Theodorus of the planet Earth. Things have progressed at a more glacial pace throughout our world's history. We are continuing to prepare for the arrival of the stars. However, in another century or two, when the entirety of the solar system has been mapped out, we will also have organized our planet. We will have the motivation, the resources, and the technical know-how to travel to other star systems. We will have investigated various other planetary systems from great distances, some comparable to ours, while others dissimilar to ours. we will be able to determine which stars to travel to. The children of Thales and Aristarchus, Leonardo and Einstein, will then skim across the light years, accompanied by our machines and their descendants. There appear to be many planetary systems, however, we still count them all. Jupiter, Saturn and Uranus are the 3 planets closest to us out of the 4 in our solar system's neighborhood. Each possesses a moon system that closely resembles the planetary systems that orbit the Sun regarding the relative sizes of the moons and the spacing between them. The statistics of double stars, which can have masses very different from one another, can be extrapolated to suggest that almost all single stars, such as the Sun, should have planetary companions. Because their respective suns are so bright, we still need to be able to directly observe the planets that orbit other stars. However, we can recognize the gravitational effect of an unseen planet acting upon a known star. Imagine such a star that has a large proper motion, meaning that it is moving over decades against the backdrop of more distant constellations, and that it also has a large planet, say with the mass of Jupiter, whose orbital plane is aligned by chance to be perpendicular to our line of sight. This would make it appear that the planet is moving in the opposite direction of the star. When the dark planet is, from our vantage point to the right of the star will be pulled slightly to the right. On the other hand, when the planet is to the left of the star's path will be altered or perturbed from a straight line to a wavy one. Both of these effects can be seen from our vantage point. Barnard's star, the single star located closest to our solar system, is the one to which this gravitational perturbation method can be applied. The 3 stars that make up the Alpha Centauri system have such complicated relationships with one another that it would be difficult to find a low-mass companion there. Even for Barnard's star, the investigation has to be conducted with great care. It entails looking for minuscule shifts in position on photographic plates that have been exposed to the telescope for several years. According to some standards, 2 of these searches for planets around Barnard's star have been successful. This indicates the existence of 2 or 3 planets of Jovian mass moving in an orbit that, according to Kepler's third law, is closer to their star than Jupiter and Saturn are to the Sun. Both planets orbit their stars in a way consistent with Kepler's third law. However, unfortunately, the 2 different sets of observations are not compatible with one another. There is a possibility that a planetary system revolving around Barnard's star has been found, but definitive proof will require additional investigation. Other techniques for discovering planets in orbit around stars are being researched and developed. One of these techniques involves artificially occulting the illuminating light from the star, either by placing a disk in front of a space telescope or employing the Moon's dark edge as such a disk. After this, the reflected light from the planet, previously obscured by the intensity of the nearby star, becomes visible. We should have definitive answers to which of the nearest 100 stars have large planets in close orbit around them within the next few decades. Infrared observations have unearthed several preplanetary disk-shaped clouds of gas and dust revolving around some of the nearby stars throughout the past few years. In the meantime, several thought-provoking theoretical studies have hinted that planetary systems are relatively common throughout the cosmos. Researchers have used computers to investigate the development of a flat condensing disk of gas and dust, which is thought to be the precursor to the formation of stars and planets. Randomly distributed throughout the cloud, small clumps of matter, which represent the first condensations in the disk, are injected. The movement of the lumps causes the accumulation of dust particles. When they reach a certain size, they gravitate towards cloud gas, primarily hydrogen, which continues even after the cloud is no longer present. When 2 moving lumps come into contact with one another, the computer program causes them to become stuck. This process will continue until all the gas and dust used in this manner have been utilized. The outcomes are determined by the conditions at the beginning of the experiment, specifically the distribution of gas and dust density as a function of distance from the cloud's center. But generating planetary systems that are recognizably similar to our own is possible for various plausible initial conditions. These systems have approximately 10 planets. terrestrials close to the star and Jovians on the exterior. In other situations, there may not be any planets. Instead, there may be a scattering of asteroids. Alternatively, there may be Jovian planets near the star. Alternatively, a Jovian planet may amass enough gas and dust to transform into a star, which would be the beginning of a binary star system. It is still too early to say for certain, but a splendid variety of planetary systems is to be found throughout the galaxy. And with high frequency, we believe that all stars must have originated from such clouds of gas and dust. The galaxy may contain 100 billion undiscovered planetary systems just waiting to be explored. There won't be another world that's quite like ours. Few will be friendly, while most will project an unfriendly demeanor. There will be many that are breathtaking. On some worlds, the sky will be filled with many suns during the daytime, an abundance of moons during the nighttime, or enormous particle ring systems stretching from horizon to horizon. There will be moons so close to their planet that they will appear to loom large in the heavens and cover half of the sky. And the view from some worlds will be of a vast gaseous nebula, all left over from an ordinary star that used to be there but no longer is. The home star of the fleet of interstellar transports exploring this minuscule region of the vast Milky Way galaxy will be a dim yellow star. This star may be so faint that it is only visible through a telescope, or so faint that it is barely visible to the naked eye. Either way, it will be present in all those skies abundant in faraway and exotic constellations. As we've seen, the concepts of space and time are intricately intertwined. Just like people, worlds and stars are born, live their lives, and eventually pass away. The average human lifespan can be measured in decades, while the sun's age is measured in terms that are 100 million times greater. Mayflies are transient, ephemeral creatures that complete their entire life cycle in a single day, and that is how a star can be compared to use. From the perspective of a mayfly, human beings appear to be unmoving, dull, and almost entirely immobile. They give almost no indication that they are ever engaged in any activity. A human being, when viewed from the perspective of a star, is nothing more than a minuscule flash. One of the billions of brief lives that are tenuously flickering on the surface of an unusually cold, anomalously solid, and exotically distant sphere of silicate and iron. On all those other planets in space, events are taking place right now that will significantly impact their destinies. This point in the history of our little planet is a historical branch point that is just as significant as the encounter between the Ionian scientists and the mystics that took place 2,500 years ago. What we do in this time with our world will propagate down through the centuries and powerfully determine the destiny of our descendants and their fate, if they have one, among the stars. Where did all of these atoms originate? All of them are made of stars, except hydrogen. Inside a star, hydrogen atoms are transformed into heavier atoms through cooking. A star can be thought of as a cosmic kitchen. Interstellar gas and dust, primarily composed of hydrogen, are where stars are formed. Hydrogen, on the other hand, was produced during the Big Bang, the explosion credited with starting the cosmos. You must develop the universe concept before making an apple pie from scratch. Suppose you cut an apple pie in half. Then, in the spirit of Democritus, you take one of the two pieces and cut it in half again. How many slashes do you have to make before you reach the level of an atom? The correct number is approximately 90 different cuts in succession. Naturally, no knife could be sharp enough, the pie would be too crumbly, and the atom would be too small to see without magnification. However, there is a solution to this problem. The nature of the atom was first comprehended during the 45 years centered on 1910 at Cambridge University in England. This was accomplished partly by firing pieces of atoms at other atoms and observing their deflection. The exterior of a typical atom is covered in something resembling a cloud of electrons. True to their name, electrons carry an electric charge within their bodies. The charge is referred to as negative for no particular reason. Electrons are responsible for determining the chemical properties of an atom, such as the icy texture of iron and the crystalline structure of a carbon diamond. The nucleus is typically made up of positively charged protons and electrically neutral neutrons, and it is located deep within the atom, far beneath the cloud of electrons. Atoms are tiny. If you line up 100 million of them, they wouldn't be much longer than the tip of your little finger. On the other hand, the nucleus is still 100,000 times smaller, which is one of the reasons why it took so much time to discover. Despite this, most of an atom's mass is located in its nucleus. The electrons are nothing more than clouds of moving fluff. The majority of an atom is composed of empty space. The vast majority of matter is made up of nothing. I am composed of individual atoms. My elbow, composed of atoms, rests on the table before me. Atoms have been used to construct the table. But if atoms are so tiny and empty, and nuclei are even smaller than that, how can the table keep me from falling through it? As Arthur Eddington liked to ponder, why are the nuclei that make up my elbow unable to pass through the nuclei that make up the table easily? How come I don't find myself on the ground, or plunge directly through the surface of the Earth? The electron cloud is the correct response. My elbow contains atoms with an outermost layer with a negative electrical charge. The same is true for each and every atom in the table. On the other hand, negative charges work to cancel each other out. The fact that atoms have electrons surrounding their nuclei and that electrical forces are strong is why my elbow does not slide through the table. The structure of the atom is essential to life as we know it. If you remove the atom's electrical charges, everything around you will disintegrate into an imperceptible powder. Without electrical forces, there would be nothing in the universe but diffuse clouds of electrons, protons, and neutrons and gravitating spheres of elementary particles. These featureless remnants of worlds would be all that would remain if there were no electrical forces. When we think about slicing an apple pie down to the level of a single atom and beyond, we are confronted with an infinite number of very small things. When we gaze into the depths of the night sky, we are confronted with an infinite expanse of the extremely massive. These infinities stand for a never-ending regression extending very far into the indefinite future. If you stand between two mirrors, say in a barbershop, you will see many different reflections of yourself. Each of these images is a reflection of the other. Because the mirrors are not perfectly flat and aligned, you cannot see infinite reflections. After all, because you are there, light cannot travel at an infinitely high speed through space. When we speak of infinity, we refer to a quantity greater than any number, regardless of how large the number may be. American mathematician Edward Kasner once asked his nephew, who was only 9 years old then, to name a number 10 times as powerful as 100 and consisted of 1 and 100 zeros. You too can imagine very large numbers and assign peculiar names to them. Could you test it out? It has a certain allure, particularly if you are 9 years old. If one Google seems like a lot, consider how many Googleplexes there are. It equals 10 to the power of a Google, which can also be written as a single number followed by a Google 0. Comparatively, the total number of atoms in your body is approximately 10 to the power of 28, and the total number of elementary particles in the observable universe is approximately 10 to the power of 80. Protons, neutrons, and electrons make up elementary particles. Even if all of the empty space in the universe were filled with neutrons, as an example, the total number of particles in the universe would still only amount to about 10^128. This is significantly more than a Google, but insignificantly less than a Googleplex. And yet these numbers, the Google and the Googleplex, do not even come close to approaching the concept of infinity. In fact, they are nowhere near it. The number 1 is the same distance away from infinity as a Googleplex. We could attempt to write a Googleplex, but that seems like a hopeless goal. The known universe can't accommodate a piece of paper large enough to have all of the zeros in a Googleplex written out explicitly on it, and the paper is. There is, thankfully, an easier and more condensed way to write a Googleplex, which is 1010 L0, and even infinity, which is written as, which is pronounced, infinity. The charred crust of a burnt apple pie is composed primarily of carbon. After 90 cuts, you will arrive at a carbon atom that has 6 protons, 6 neutrons, and 6 electrons in its nucleus, and a cloud of 6 electrons surrounding it. If we were to remove a portion of the nucleus, for example, one that contains 2 protons and 2 neutrons, we would be left with not the nucleus of a carbon atom, but rather the nucleus of an atom of helium. In nuclear weapons and conventional nuclear power plants, atomic nuclei undergo a process known as cutting or fission. However, carbon is not split apart. If you make the 91st cut of the apple pie and slice a carbon nucleus, you don't end up with a smaller piece of carbon. Rather, you end up with something else. An atom with completely different chemical properties. You can change the elements by cutting an atom into smaller pieces. Continue on with this. Atoms comprise subatomic particles known as protons, neutrons, and electrons. Is it possible to split a proton? If we bombard protons with other elementary particles at high energies, say other protons, we can glimpse more fundamental units hiding inside the proton. Physicists now propose that so-called elementary particles, such as protons and neutrons, are in fact made of even more elementary particles called quarks, which come in a variety of colors and flavors, as their properties have been termed in an emotionally moving attempt to make the subnuclear world a little more like home. Are quarks the tiniest and most fundamental particles that make up matter? Or do they consist of even smaller and more fundamental particles? If there is an infinite regression into more fundamental particles, will there ever come a time when our understanding of the nature of matter will be complete, or will it always expand? This is one of the most important scientific questions yet to be answered. Alchemy was the name given to the practice pursued in medieval laboratories to change one element into another. According to ancient Ionian speculation, many alchemists believed that all matter was a combination of 4 fundamental substances: water, air, earth, and fire. They believed it was possible to transform copper into gold by adjusting the proportions of fire to earth in a certain way. The field was teeming with charming frauds and conmen, such as Cagliostro and the Count of Saint-Germain, who pretended not only to be able to transmute the elements but also to hold the secret to immortality. They conned their victims out of a significant amount of money. Sometimes gold would be concealed in a wand with a false bottom, and then it would miraculously appear in a crucible after a particularly laborious scientific experiment. The practitioners of this questionable art were able to entice the European aristocracy with promises of wealth and immortality in exchange for large sums of money. However, there were other, more serious alchemists, such as Paracelsus and even Isaac Newton. Due to the expenditure, new chemical elements such as phosphorus, antimony, and mercury were found, so the money was completely well spent. These experiments are, in fact, directly responsible for giving rise to the modern field of chemistry. 92 naturally occurring atoms can be classified according to their chemical properties. They are known as the chemical elements, and until fairly recently, everything on our planet was made up of them, even though they are most commonly found combined into molecules. Hydrogen and oxygen are the 2 elements that make up the atoms of the water molecule. Nitrogen, N, oxygen, O, carbon, C, hydrogen, H, and argon, R, make up the majority of the atoms that make up air, and these elements exist in the molecular forms of nitrogen dioxide, N2, oxygen dioxide, O2, carbon dioxide, CO2, and argon. The Earth is an abundant place with a conglomeration of atoms with silicon, oxygen, aluminium, magnesium, and iron making up the majority. There is no chemistry involved in the creation of fire at all. It is a radiating plasma in which some electrons are stripped away from their nuclei due to the high temperatures. One of the ancient Ionian and alchemical elements is a molecule. 2 are mixtures of molecules, and the last is a plasma. None of these 4 things can be considered an element in the modern sense. Since the time of the alchemists, an ever-increasing number of elements have been discovered, with the most recently discovered elements typically being the rarest ones to be found. Many are well known, particularly those that predominantly compose the Earth or those that are essential to the existence of life. Some are solids, some are gases, and 2 are liquids at room temperature, bromine and mercury. It is customary for scientists to arrange them in ascending order of complexity. Hydrogen, element 1, is the simplest, and uranium, element 92, is the most complex. Other elements, such as hafnium, erbium, dysprosium, and praseodymium, are less familiar to us because we do not typically come into contact with them in our day-to-day lives. In general, the prevalence of an element increases in proportion to how well known it is. Iron is one of the most abundant elements on Earth, while yttrium is one of the least abundant. There are some notable exceptions to this rule, including gold and uranium, which are prized either because of arbitrary economic conventions or aesthetic judgments, or because they have remarkable practical applications. A relatively recent discovery is that atoms comprise 3 different types of elementary particles: protons, neutrons, and electrons. These 3 types of particles make up the atomic nucleus. It wasn't until 1932 that scientists found evidence of the neutron. The complexity of the material world has been reduced to an astonishing simplicity thanks to modern physics and chemistry. Combined in various configurations, 3 basic units are the building blocks of everything. As stated, and following what one might infer from their name, neutrons do not carry any electrical charge. The protons and the electrons carry a negative charge, but the protons have a slightly stronger charge. Electrons and protons have opposing electrical charges, creating an attractive force that keeps the atoms together. Because each atom maintains its internal electrical balance, the number of protons in the nucleus and electrons in the electron cloud must be equal. The atomic number, which is equal to the number of protons and is referred to as the electron count, is the only factor that determines the chemical composition of an atom. Pythagoras would have approved of the notion that chemistry is nothing more than the manipulation of numbers. If you are an atom with 1 proton, your name is hydrogen. If you have 2, your name is helium. If you have 3, lithium. If you have 4, beryllium. If you have 5, boron. If you have 6, carbon. If you have 7, nitrogen. If you have 8, oxygen. And so on until you have 92 protons, your name is uranium. Charges that are identical or have the same sign are extremely repellent. It's possible to think of it as a dedicated mutual aversion to their own kind, almost as if the world were densely populated by anchorites and misanthropes. Electrons have a repulsion towards electrons. Protons do indeed repel other protons. How, then, does a nucleus maintain its structure? Why does it not just disintegrate into pieces right away? Because there is another force in nature, not gravity, not electricity, but the short-range nuclear force, which, like a set of hooks that engage only when protons and neutrons come very close together, overcomes the electrical repulsion among the protons. Specifically, the short-range nuclear force is akin to a set of hooks that only engage when protons and neutrons come close together. Neutrons, which only contribute nuclear forces of attraction to the nucleus and have no effect on its electrical forces of repulsion, act as a glue that helps to keep the nucleus intact. Despite the hermit's desire for seclusion, their fellow hermits have been chained together, and each of them has been instructed to be friendly and talkative with everyone. The nuclei of a helium atom, which is exceptionally stable, comprise 2 protons and 2 neutrons. Carbon's nucleus is composed of 3 helium nuclei, oxygen's is composed of 4, neon's is composed of 5, magnesium's is composed of 6, silicon's is composed of 7, and so on. Every time we add 1 or more protons and sufficient neutrons to maintain the structure of the nucleus, we create a new element in the periodic table of chemical elements. The ancient alchemist's dream of turning mercury into gold can be realized if we remove 1 proton and 3 neutrons from the element mercury. In addition to uranium, the Earth does not have naturally occurring deposits of the other elements. They are created by humans, and almost immediately they disintegrate into their component parts. One is called plutonium, one of the most toxic substances science has ever discovered. Element 94. Regrettably, it crumbles to pieces in a rather sluggish manner. Where do the elements that occur in their natural state originate? We could make a separate creation for each different atomic species. The universe, however, is almost entirely composed of hydrogen and helium, the 2 most fundamental elements. In fact, helium was discovered on the Sun long before it was discovered on Earth. Hence, the origin of its name comes from Helios, one of the Greek sun gods. Are hydrogen and helium the progenitors of the other periodic table elements? It is necessary to bring pieces of nuclear matter close to engage the short-range nuclear forces to balance the electrical repulsion and the short-range nuclear forces. Only at extremely high temperatures, where the particles are moving so quickly that the repulsive force does not have time to act, which is at temperatures of tens of millions of degrees, is it possible for this to occur? In the natural world, such high temperatures and the accompanying high pressures are only ever found on the interiors of stars. We have looked at the Sun, the nearest star, in various wavelengths, ranging from radio waves to regular visible light to X-rays, originating only from the Sun's outermost layers. It is not exactly a red-hot stone, as Anaxagoras thought. Rather, it is a large ball of hydrogen and helium gas glowing due to its high temperatures, like a poker glows when it is brought to red heat. At the very least, Anaxagoras was partially correct. During violent solar storms, brilliant flares interfere with Earth's radio communications. Additionally, enormous arching plumes of hot gas, guided by the Sun's magnetic field, dwarf the Earth. Sunspots are cooler regions on the Sun's surface with increased magnetic field strength. They are sometimes visible to the naked eye at sunset. All of this churning, roiling, and turbulence is taking place on the surface, which is relatively calm. Temperatures of approximately 6,000 degrees are all that we observe. However, the Sun's dark interior, where the light comes from, has a temperature of 40 million degrees. The gravitational collapse of a cloud of gas and dust in interstellar space gives rise to the formation of stars and the planets that orbit around them. The collision of the gas molecules within the cloud's interior generates heat, eventually raising the temperature to the point where hydrogen can fuse into helium. This occurs when 4 hydrogen nuclei combine to form a helium nucleus, accompanied by the release of a gamma photon. The photon endures alternating bouts of absorption and emission at the hands of the matter above it as it slowly works its way towards the surface of the star, gradually losing energy at each stage of its epic journey. This ordeal lasts 1 million years before the photon finally emerges from the star's surface as visible light and is emitted into space. The light on the star has been turned on. The prestellar cloud's gravitational collapse has come to a halt for now. The high temperatures and pressures produced by the nuclear reactions occurring within the star's core currently support the weight of the star's outer layers. For the past 5 billion years, the Sun has maintained this level of consistency in its environment. In a controlled and ongoing explosion, the Sun is powered by thermonuclear reactions like a hydrogen bomb. These reactions convert approximately 400 million metric tons, 4 times 1014 grams, of hydrogen into helium every second. When we look up at night and observe the stars, everything we see is glowing due to nuclear fusion in the distance. An enormous glowing superbubble of extremely hot gas can be found in the direction of the star Deneb, located in the constellation of Cygnus the Swan. This superbubble was most likely produced by supernova explosions near the bubble's center, which are the deaths of stars. The shock wave from the supernova causes the interstellar matter to be compressed at the periphery, which in turn causes new generations of cloud collapse and star formation. In this sense, stars are said to have parents. However, much like it is sometimes the case with humans, a parent may pass away when the child is born. Massive cloud complexes like the Orion Nebula, where stars like the Sun are born in batches, have the characteristics of a nebula. These clouds give off an ominous and dark impression when viewed from the outside. On the other hand, the newborn stars within them cast a brilliant light throughout their interiors. Later, the stars leave their nursery to seek their fortunes in the Milky Way. Nebulosity still glows around these stellar adolescents, and their leftovers are still gravitationally bound to the amniotic gas they were born in. A good local example would be the Pleiades. As is the case in human families, the maturing stars travel very far from their birthplace, and as a result, the siblings rarely interact with one another. There are other stars in the galaxy, perhaps dozens of them, that are the Sun's brothers and sisters. They originated from the same cloud complex approximately 5 billion years ago. However, we are unable to identify the stars in question. They are on the opposite side of the Milky Way from where we are. The transformation of hydrogen into helium in the Sun's core produces photons of visible light that make up the Sun's brightness. This transformation also produces a more enigmatic and spectral radiance. Neutrinos are subatomic particles that, like photons, have no mass and move at the speed of light. The Sun emits a very faint glow of neutrinos. However, neutrinos are not the same thing as photons. They do not belong to the category of light. Neutrinos and protons, electrons, and neutrons all possess an intrinsic angular momentum known as spin, but photons do not. Neutrinos can travel through matter unimpeded, as evidenced by their ability to travel through the Earth and the Sun. The matter in between only prevents a minute portion of them from moving forward. During this brief examination of the Sun, 1 billion neutrinos travel through my eyeball. They pass through the back of my head unimpeded because, unlike regular photons, they do not get stopped at the retina as they travel through the eye. When I look down at the ground at night, towards where the Sun would be, if the Earth were not in the way, almost the same number of solar neutrinos pass through my eyeball. These neutrinos are pouring through an interposed Earth that is as transparent to neutrinos as a pane of clear glass is to visible light. This is the curious part. If our understanding of the solar interior is as comprehensive as we believe it to be, and if we also have an understanding of the nuclear physics that is responsible for the production of neutrinos, then we should be able to calculate with a reasonable degree of accuracy how many solar neutrinos we should receive in a specific area, such as my eyeball, in a specific amount of time, such as a second. Obtaining experimental confirmation that the calculation is correct is a lot more difficult. Because neutrinos travel through the Earth unimpeded, we can't capture any particular one. However, for many neutrinos, only a tiny portion will interact with matter, which may be detectable under certain conditions. Neutrinos have the potential to transform chlorine atoms into argon atoms that have the same total number of protons and neutrons. American physicists have poured a large quantity of cleaning fluid into the Homestake mine in Lead, South Dakota, to detect the predicted solar neutrino flux, which requires enormous chlorine. The mine is located in the Black Hills. A microchemical process removes the chlorine in preparation for the newly produced argon. The greater the amount of argon discovered, the greater the number of neutrinos inferred. The results of these experiments suggest that the Sun emits a lower level of neutrinos than what is predicted by the calculations. There is a genuine mystery that has not been resolved here. The low solar neutrino flux will likely not jeopardize our understanding of stellar nuclear synthesis, but it does mean something significant. The proposed explanations range from the idea that neutrinos break up while traveling between the Sun and Earth to the concept that the nuclear fires in the interior of the Sun are temporarily banked and that sunlight is being generated in our time in part by slow gravitational contraction. One of the most popular hypotheses is that neutrinos break up while traveling between the Sun and Earth. However, neutrino astronomy is still in its infancy. We are still in awe that we have developed a device capable of peering directly into the raging core of the Sun. As the sensitivity of the neutrino telescope continues to improve, it will become possible to investigate the possibility of nuclear fusion occurring deep within the interiors of nearby stars. The fusion of hydrogen, however, cannot go on indefinitely because there is a finite amount of hydrogen fuel in the interior of stars, like the Sun and other stars. The initial mass of a star is a critical factor in determining how it will ultimately fare at the end of its life cycle. When a star reaches the end of its life cycle, it does so in a manner that is strikingly dissimilar to that of the Sun. This is the case even if the star has lost matter to space and still has 2 or 3 times the mass of the Sun. However, the destiny of the Sun is quite spectacular. After 5 or 6 billion years from now, when all of the central hydrogen has reacted to form helium, the zone of hydrogen fusion will slowly migrate outward, becoming an expanding shell of thermonuclear reactions until it reaches a location where the temperatures are less than about 10 million degrees Celsius. After that, the process of hydrogen fusion will turn off by itself. During this time, the Sun's self-gravity will cause its helium-rich core to contract again, increasing the Sun's interior temperatures and pressures. The helium nuclei will be crammed together even more closely to the point where they will begin to adhere to one another. This will occur even though the nuclei's short-range nuclear forces will be repelled by one another's electrical attraction. The ash will be converted into fuel, which will in turn cause the Sun to begin a second cycle of fusion reactions. This process will generate carbon, oxygen, and additional energy for the Sun, allowing it to shine for a limited time longer than it would otherwise. A star is like a phoenix in that it is doomed to rise from its ashes after a certain amount of time. The Sun will transform significantly due to the combined effects of hydrogen fusion in a thin shell far from the solar interior and high-temperature helium fusion in the core. This will cause the Sun's exterior to expand and cool over time. It is predicted that the Sun will eventually evolve into a red giant star, with its surface visible from space being so far removed from its core that the Sun's gravity will weaken at its surface while its atmosphere blows away into space in a stellar gale. When the Sun reaches its full size and expands into a red giant, it will engulf and consume the planets Mercury, Venus, and most likely the Earth. After that, the Sun's interior will be home to the inner solar system. There will be one final day on Earth that is without flaw when it is billions of years in the future. After that, the Sun will gradually turn red and become bloated, presiding over a planet that will be scorching hot all the way to the poles. The ice caps in the Arctic and Antarctic will eventually melt, which will cause flooding along the coasts of the world. The high temperatures of the oceans will cause more water vapor to be released into the air, which will result in an increase in cloudiness, which will shield the Earth from sunlight and postpone the end of the world. However, the evolution of the Sun cannot be stopped. At some point in the not-too-distant future, our planet will be overtaken by a catastrophe of unfathomably massive proportions, resulting in the oceans boiling and the atmosphere dissipating into space. In the interim, humans will have developed into substantially different species. Our descendants will likely be able to control or influence the evolution of stars, or, as Robert Goddard envisioned, they could search for an uninhabited planet in some young and promising planetary system and move there. Another option is that they could pick up and move to Mars, Europa, or Titan. To a certain extent, the stellar ash that comes from the Sun can be recycled and used as fuel. When that time comes, the interior of the Sun will be composed entirely of carbon and oxygen, and further nuclear reactions will be unable to take place at the temperatures and pressures that are currently in place. After almost all of the central helium has been consumed, the collapse of the Sun's interior will continue at some point in the future. This will cause temperatures to rise again, setting off a final chain reaction of nuclear reactions and causing the solar atmosphere to expand slightly. The Sun will eventually expel its atmosphere into space in the form of one or more concentric shells of gas as it goes through the final stages of its life cycle. The Sun will slowly pulsate during this time, expanding and contracting once every few millennia. The shell will be inundated with ultraviolet light due to the hot, exposed solar interior, resulting in a beautiful red and blue fluorescence extending beyond Pluto's orbit. This may cause the Sun to lose half of its mass. When this occurs, the solar system will be filled with an eerie radiance that can only be described as the ghost of the Sun. When we turn our attention to the region of the Milky Way immediately surrounding us, we notice that many of the stars are encircled by glowing spherical shells known as planetary nebulae. They have nothing to do with planets, but some seem to be reminiscent of inferior telescopes of the blue-green disks of Uranus and Neptune. The only reason they appear as rings is that we see more of them at the periphery than the center, similar to how we see more soap bubbles. Every planetary nebula is evidence of a star that has reached the end of its life. Near the primary star, there might be a retinue of dead worlds, the husks of planets that were once teeming with life but are now devoid of atmosphere and oceans and are illuminated by a spectral kind of light. The remnants of the Sun, which will consist of the exposed solar core initially encased in its planetary nebula, will be a small hot star that will eventually cool off into space after having contracted to a density that is unheard of on Earth and is greater than 1 ton per teaspoonful. In the distant future, billions of years from now, the Sun will degenerate into a white dwarf before eventually transitioning into a dark and lifeless black dwarf, just like all those points of light we see at planetary nebulae centers. If two stars have roughly the same mass, their evolution will be relatively similar. But a star with a greater mass will burn through its nuclear fuel more quickly, transform into a red giant at an earlier stage, and be the first to begin the decline into a white dwarf. As a result, there should be many instances of binary stars, with one component being a red giant and the other being a white dwarf, and there are such cases. Some of these pairs are so close to one another that they touch. When this occurs, the glowing stellar atmosphere flows from the expanded red giant to the compact white dwarf. This glowing stellar atmosphere tends to fall on a particular region of the surface of the white dwarf. The intense gravity of the white dwarf causes the hydrogen to accumulate, which in turn causes it to be compressed to higher and higher pressures and temperatures. This continues until the stolen atmosphere of the red giant goes through thermonuclear reactions, at which point the white dwarf briefly flares into brilliance. A nova is the name given to this type of binary, and its origin is very different from that of a supernova. Supernovae are the result of the fusion of a single star, whereas novae are only the result of binary star systems. It is common for atoms created within the interiors of stars to be returned to the gas between them. The outer atmospheres of red giants are blown away into space, and planetary nebulae result from sun-like stars reaching their final stages of evolution before exploding. During a supernova, a significant portion of the stellar mass is violently ejected into space. The atoms returned are naturally those most readily made in the thermonuclear reactions in stellar interiors. Hydrogen fuses into helium, helium into carbon, carbon into oxygen, and after that, in massive stars, by the successive addition of further helium nuclei, neon, magnesium, silicon, sulfur, and so on are built, additions by stages, 2 protons and 2 neutrons per stage, all the way to iron. Iron is produced when 2 atoms of silicon, each with 28 protons and neutrons, combine at a temperature of billions of degrees to form a single atom of iron with 56 protons and neutrons. This process is known as the direct fusion of silicon. These are all well-known constituents of chemical substances. We are familiar with their names. The nuclear reactions in stars do not easily produce erbium, hafnium, dysprosium, praseodymium, and yttrium. However, rather than the elements we are familiar with in our day-to-day lives, elements returned to the interstellar gas, where they were swept up in a subsequent generation of cloud collapse and the formation of stars and planets. All elements that make up Earth, except hydrogen and a small amount of helium, were created through stellar alchemy billions of years ago in stars, some of which are now obscure white dwarfs on the opposite side of the Milky Way galaxy. This process cooked up all of the elements that make up Earth. The interiors of stars that were in the process of collapsing were the source of the nitrogen that is in our DNA, the calcium that is in our teeth, the iron that is in our blood, and the carbon that is in our apple pies. We are composed of the stuff of the stars. The supernova's explosion can produce some of the universe's most exotic elements. As a result of the numerous supernova explosions that took place just before the solar system formed, the Earth contains a relatively abundant supply of gold and uranium. Other planetary systems may have different concentrations of these extremely rare elements. Is it possible that there are worlds whose inhabitants wear niobium pendants and protactinium bracelets with pride but consider gold nothing more than a laboratory curiosity? If gold and uranium were as rare and unimportant on Earth as praseodymium, would our quality of life be better? The beginning and development of life are most closely related to the birth and growth of the universe's first stars and galaxies. To begin, the very matter of which we are composed, the atoms that make it possible for there to be life, were generated in giant red stars a very long time ago and very far away. There is little room for doubt that red giants and supernovae are the furnaces and crucibles in which matter was forged. because the relative abundance of the chemical elements in the cosmos matches the relative abundance of the atoms generated in stars. The Sun is a star that belongs to the second or third generation. All of the matter in it and the matter around you has been through at least 1 or 2 cycles of stellar alchemy in the past. Second, the discovery of specific types of heavy atoms on Earth proves that an enormous supernova exploded in the neighborhood before the Sun, planets, and other solar system components came into existence. However, it is highly unlikely that this is merely a coincidence. It is more likely that the shock wave produced by the supernova compressed interstellar gas and dust, which in turn triggered the condensation that led to the solar system's formation. Third, when the Sun began to shine, its ultraviolet radiation poured into the Earth's atmosphere, and its surface's warmth caused lightning to form. These different energy sources served as the spark that ignited the complex organic molecules that eventually led to the beginning of life. Fourth, almost all of the energy that sustains life on Earth comes from the Sun. Plants are responsible for absorbing photons and transforming them into chemical energy. The plants are parasitized by the animals. Methodically harvesting sunlight through the use of plants as reluctant intermediaries constitutes farming. Solar energy provides the majority of our power. Last but not least, the hereditary shifts known as mutations provide the essential building blocks for evolution. Cosmic rays are high-energy particles ejected almost at the speed of light in supernova explosions. These particles contribute to the production of mutations, which nature then uses to select its new inventory of life forms. The spectacular demise of ancient, extremely massive suns is one of the driving forces behind the development of life on Earth. Imagine going to some location very deep within the Earth, such as a gold mine or a lava tube with a Geiger counter and a piece of uranium ore in your possession. A lava tube is a cave carved through the Earth by a river of molten rock. The sensitive counter clicks when subjected to gamma rays or high-energy charged particles like protons and helium nuclei. The count rate and the number of clicks per minute significantly increase when we place it close to the uranium ore undergoing spontaneous nuclear decay and emitting helium nuclei. The count rate drops significantly after the uranium ore is placed inside a heavy canister made of lead because the lead has taken in the radiation from the uranium. However, there are still some clicks that can be heard. A portion of the counts that are left is overcome by the natural radioactivity that is present in the cave walls. However, there are more clicks than can be explained by the radioactivity. Some are brought on by high-energy charged particles that have broken through the roof. We are currently listening to cosmic rays created in a previous era, deep within the reaches of space. For the entirety of our planet's existence, it has been pounded by cosmic rays, most of which are composed of electrons and protons. In a galaxy thousands of light-years away, a star annihilates itself, producing cosmic rays that spiral through the Milky Way galaxy for millions of years, until, quite by accident, some of them strike the Earth and our genetic material. These cosmic rays are thought to have played a role in the evolution of life on Earth. It's possible that cosmic rays were responsible for the initial stages of the development of the genetic code, the Cambrian explosion, or the evolution of our ancestors into bipedal stature. A guest star was discovered by Chinese astronomers on July 4, 1054, within the constellation of Taurus, also known as the Bull. A star that had never been seen before became more brilliant than any other star in the sky. In the American Southwest, halfway around the world, there is a high culture abundant in astronomical knowledge. The traditions of the past witnessed this dazzling new star. We know that in the middle of the 11th century, some Anasazi, the ancestors of the Hopi of today, lived under an overhanging ledge in New Mexico because carbon-14 dating of the remains of a charcoal fire revealed this fact. One apparently drew a picture of the new star on the cliff overhang, where it would have been protected from the elements. Its location concerning the waning crescent moon would have been the same as depicted. In addition, there is a handprint, which may be the artist's signature. An astronomer centuries later had the uncanny experience of being reminded of a crab when looking at the explosion remnants through his telescope. This remarkable star is located 5,000 light-years away and is now known as the Crab supernova. The Crab Nebula is all left of a massive star that went supernova millions of years ago. On Earth, the explosion could be seen with the naked eye for 3 months. Even though it was easy to see during the day, you could read it at night. In any given galaxy, there will be a supernova approximately once every century on average. A typical galaxy will live for about 10 billion years when 100 million stars have blown themselves apart. This is a significant number, but it still accounts for only about 1 star in 1,000. Tycho Brahe observed and described a supernova in the Milky Way in 1572, following the event in 1054. Shortly after that, in 1604, Johannes Kepler described another supernova in the Milky Way. Astronomers have been chomping at the bit for centuries, but unfortunately no supernova explosions have been observed in our galaxy since the invention of the telescope. This has caused them much frustration. It is now common practice to spot supernovae in galaxies other than ours. The following passage from a paper written by David Helfand and Knox Long and published in the issue of the British journal Nature dated December 6, 1979, is one of my candidates for the sentence that would most thoroughly astound an astronomer working in the early 1900s. On 5th of March 1979, an extremely intense burst of hard X-rays and gamma rays was recorded by the 9 interplanetary spacecraft of the Burst Sensor Network and localized by time-of-flight determinations too. There is also, contrary to what you might anticipate, a relatively insignificant Magellanic Cloud. On the other hand, E.P. Mazets and colleagues from the IOFA Institute in Leningrad, who observed this source with the gamma-ray burst detector aboard the Venera 11 and 12 spacecraft while they were traveling to Venus, argue that what is being observed is a flaring pulsar that is only a few hundred light-years away. Their findings were published in the same issue of Nature. But Helfand and Long do not insist that the gamma-ray outburst is associated with the supernova remnant, even though their positions are very similar. They carefully consider a wide range of possibilities, including the possibility that the origin is somewhere within the solar system. It could be the byproduct of an extraterrestrial starship's long journey back to its home planet. The rekindling of the stellar fires in N49 points to a more straightforward explanation. We are certain that supernovae are real phenomena. The future of the inner solar system is not looking good as the Sun continues to evolve into a red giant. On the other hand, there is no danger of a supernova exploding and turning the planets into a molten mess. This calamity befalls planets that orbit stars that are significantly more massive than the Sun. The lifetimes of stars with higher temperatures and pressures than the Sun are significantly shorter due to the rapid depletion of their stores of nuclear fuel. The Sun's lifetime is approximately 93 billion years. It only takes a few million years for a star with tens of times the Sun's mass to convert hydrogen into helium in a stable manner, before the star shifts its focus to nuclear reactions that are more unusual. Therefore, there is almost certainly not enough time for the evolution of advanced life forms on any of the accompanying planets, and it will be extremely unlikely that beings elsewhere will ever be able to know that their star will become a supernova. If people survive long enough to learn about supernova, it is highly unlikely that their star will ever explode. The formation of a massive iron core through the fusion of silicon is an essential step that must take place before a supernova can occur. The equal and opposite electrical charges cancel each other out, transforming the star's interior into a single giant atomic nucleus, which occupies a much smaller volume than the precursor electrons and iron nuclei. This process takes place under enormous pressure and results in the free electrons in the stellar interior being forcibly melded with the protons of the iron nuclei. A violent implosion occurs at the core, followed by a rebound of the exterior, leading to an explosion known as a supernova. A supernova can emit more light than the total radiance of all of the other stars in the part of the galaxy in which it is located. Those recently hatched massive blue-white supergiant stars in Orion are on track to become supernovae within the next few million years, continuing the cosmic fireworks in the Hunter constellation. The incredible supernova explosion causes the majority of the matter from the precursor star to be propelled into space. This includes trace amounts of hydrogen-helium and significant quantities of other atoms, such as carbon, silicon, iron, and uranium. The remnants consist of a core of hot neutrons that are held together by nuclear forces, a single massive atomic nucleus with an atomic weight of approximately 1056, a sun that is 30 kilometers across, a tiny, shrunken, dense, withered stellar fragment, and a rapidly rotating neutron star. The core of a massive red giant collapsing to form a neutron star spins faster as it does so. The neutron star at the heart of the Crab Nebula is an enormous atomic nucleus that spins 30 times per second and is roughly the size of Manhattan. Its robust magnetic field, amplified during the collapse, captures charged particles to a greater extent than Jupiter's much more modest magnetic field. Electrons circulating in a rotating magnetic field give off beam radiation that can be detected at radio frequencies and in visible light. If the Earth happens to be in the path of the light from this cosmic lighthouse, then we will see it blink once for every rotation. Because of this characteristic, astronomers refer to it as a pulsar. Pulsars, which flash and tick like a cosmic metronome, keep time significantly more accurately than even the most accurate standard clock. The timing of the radio pulse rate over a longer period for some pulsars, such as PSR 0329 plus 54, suggests that these objects may have one or more small planets as companions. A planet can survive the transformation of a star into a pulsar, and it is also possible that a planet could be snatched up later. I can't help but imagine what the sky would look like if I were standing on such a planet. Neutron star matter weighs about the same as an average mountain per teaspoonful. Because of this, if you were to take a small amount of neutron star matter and let it go, which would be nearly impossible, it could pass through the Earth as easily as a falling stone through air, carving a hole for itself completely through our planet and emerging out the other side, possibly in China. People who live there might be going about their day-to-day activities when all of a sudden a neutron star the size of a pebble emerges from the ground, floats in the air for a short while, and then sinks back down into the ground, providing at least a momentary distraction from the monotony of the day. If a piece of neutron star matter were to be dropped from nearby space while the Earth was rotating beneath it as it fell, it would repeatedly plunge through the rotating Earth, punching hundreds of thousands of holes before the motion was stopped by friction with our planet's interior. Before it comes to rest at the Earth's center, our planet's interior may momentarily resemble Swiss cheese. However, the subterranean flow of rock and metal will heal the wounds as it moves towards the planet's center. It is probably for the best that large chunks of neutron star matter have never been discovered on Earth. On the other hand, there are numerous bumps present. The formidable force of the neutron star is latent in the nucleus of each atom. It is concealed in every teacup and dormouse, as well as every breath of air and apple pie. The neutron star instills an appreciation for the unremarkable aspects of life. As we have seen, a star with the same lifespan as the Sun will end its days as a red giant and then a white dwarf. A star with twice the Sun's mass on the verge of collapse will transform into a supernova and a neutron star. But a more massive star that is still around after its supernova phase will have an even more remarkable end in store for it. Its gravity will turn it into a black hole. This is because its mass will be 5 times that of the Sun. Imagine for a moment that we had access to a magic gravity machine, a tool that would allow us to manipulate the planet's gravitational pull at the turn of a dial. At first, the dial is positioned at 1G, and everything acts in the manner that we have come to be accustomed to anticipating. All of the living things on Earth, including plants and animals, as well as the architecture of our buildings, have either evolved to or been designed for BMG. If gravity were significantly weaker, there might be tall, spindly shapes that would not be thrown over or crushed by the weight of their own bodies. If the force of gravity were significantly higher, all living things, including plants, animals, and buildings, would need to be compact, stocky, and strong to avoid toppling over. But light would still travel in a straight line even in an environment with a fairly strong gravity field, just as in everyday life. Imagine a typical gathering of people from Earth attending the tea party described in Alice in Wonderland. As gravity is reduced, the weight of objects drops. When they get close to 0 GA, even the slightest movement causes our friends to float and tumble up into the air. Tea or any other liquid, when spilt into the air, will form pulsating spheres because the surface tension of the liquid will overcome the force of gravity. There are tea balls scattered all over. The tea maker will start working if we give the number 1G another try. Everyone becomes immobile when we slightly increase the gravity, from 1G to 3 or 4 Gs, because even moving a pore requires significant effort in this environment. Before we continue to dial in higher gravities, we remove our friends from the territory controlled by the gravity machine. The light emanating from a lantern moves in the same manner when subjected to accelerations of a few Gs as it does when subjected to accelerations of 0 G. At 1000 Gs, the beam is still straight, but trees have become squashed and flattened. At 100,000 Gs, rocks are crushed by their own weight because of the force exerted by the beam. Ultimately, nothing is left alive except for the Cheshire Cat, who was granted a miraculous exemption. Something even stranger takes place when the gravitational acceleration approaches 1 billion Gs. The direction in which the beam of light has been traveling, which has been directly upward into the sky until this point, is beginning to curve. Even light is perturbed when subjected to extremely high magnitude gravitational accelerations. If we strengthen gravity, the light will be drawn down to the ground closer to where we are. The cosmic Cheshire Cat has disappeared, leaving only its gravitational grin behind. When the gravity is high enough, nothing, not even light, can escape. There is nowhere to go. A location like this is referred to as a black hole. It is a cosmic Cheshire Cat, mysteriously indifferent to its surroundings and a complete enigma. When the black hole's mass density and gravitational pull reach a certain threshold, it evaporates and vanishes from our universe. Because no light can pass through it, we refer to it as black. Inside, things are attractively well